Hello guys, this is Kev and welcome to this comprehensive one-shot Kubernetes video in which I will explain you theoretical tutorials and projects with respect to Kubernetes. This is a comprehensive one-shot video and it took me around 2 months to complete it. It has individual topics in my playlist of Kubernetes, but this one-shot video consists of all of those videos compiled into one. This includes architecture of Kubernetes and all of the theories which is requisite and important in understanding how Kubernetes works in real life scenarios of work, and it includes multiple projects with respect to Kubernetes. That is DevSecOps project of Rivi, OWASP, SonarQube, and all of those security scanning and everything. And it also includes monitoring project. It includes environment like Minikube and kind for cluster creation, and it also has projects that is related to Kyverno, automation, GitHub actions, CICD. It has KEDA, Kustomize, Helm, and all of those projects as well as theory. Make sure to watch this video completely to have understanding of these concepts, and if you have any questions you can let me know in the comments. Anyways, without taking much of your time, let's begin. The topic is limitations of Docker with respect to Kubernetes. We will discuss what are the limitations of Docker and how it is not an enterprise level platform. Although Docker is an exceptional tool for packaging and running applications in isolated environments called containers, however, Docker, specifically standard Docker engine, operates primarily at the single host level. It handles the creation and execution of containers beautifully, but it lacks the built-in intelligence to manage those containers dynamically at scale. So it says like, for packaging and running applications, Docker is an exceptional tool. However, Docker operates on a single host level, which means on a single virtual machine or on a single instance, for example. So it has issues with storage if it only works on single host level, and also it handles creation and execution of containers beautifully, but it doesn't have the built-in intelligence to manage that containers dynamically at scale, which means it cannot scale up or scale down or manage those containers, which Kubernetes does. So here are some points to note. First is Docker is ephemeral in nature, that is volatile life cycles. The Docker reality: containers are designed to be stateless and temporary. If a container crashes or the underlying host fails, the container and its internal data are gone, which means containers are stateless and temporary. If a container crashes or its host fails, container and its data is gone. The problem: in production environment, manual intervention is required to recreate the container, patch storage, and restore service. So even if we use Docker, for example, in a single virtual machine or a single host, we would have to manually intervene to recreate the container, to attach the storage, and to restore the service if the container fails, which is inconvenience in itself, which Kubernetes solves. Second is single host nature, that is resource contention. The Docker reality: Docker typically runs on a single physical or virtual machine. As I said, Docker runs on a single virtual machine or a single physical server, that is, for example, Ubuntu or T2 Micro in an AWS. So that is a single virtual machine that you allow Docker to run your applications. The problem: there is no native intelligent cluster-wide scheduler. If one container consumes 90% of the host's CPU or RAM, other containers on that same host will starve. Docker cannot automatically look at the group of different servers and say, this server is too busy, let me launch the next container on that idle server over there. So to explain the problem, Docker is a single host platform or single host nature. It doesn't have intelligent cluster-wide scheduler, that is, it doesn't operate on multiple virtual machines or multiple servers. That means it doesn't operate on multiple instances. That means if it works on a single virtual machine, it would only have resources that are allowed in the single virtual machine. So the problem comes is if one container consumes 90% of that virtual machine or that host or that instance, 90% of the CPU or RAM, so other containers that are on that instance that needs resources too will not get that resources. So that other containers will stop, or that containers would not run. Only that 90% or that single container would run, because it doesn't have that much storage or capacity to manage, as it operates on single virtual machine or single host. The most important point to note is that Docker cannot automatically look at the metrics. It doesn't have that intelligence to look at or understand your application or the containers to say that this container is occupying a lot of space and other containers are not getting resources. So let's just create another instance, or let's just switch into that another instance or another virtual machine, so all containers are up and running. Instead, it would only run a single container and the other containers would not run. Now, third is lack of auto healing. The Docker reality. If a containerized application freezes, deadlocks, or crashes, the standard Docker engine does not natively monitor application level health to actively replace it. So Docker does not monitor application's health actively to replace or to create a new container. If a container freezes, deadlocks, or crashes, downtime occurs until human or external script notices the failure and manually restarts the container. Fourth is no native autoscaling and load balancing. Docker does not natively monitor incoming network traffic to spin up additional copies of container. So it is same. Docker does not monitor traffic and everything. So it cannot spike up or spin more containers if the traffic or the network traffic, incoming traffic increases, and it cannot scale down if the traffic is normal or it is not that much. The problem is the traffic spikes from 1000 to 1 lakh requests per second. Docker cannot automatically provision new containers and distribute the traffic evenly among them. So that was about the limitations and drawbacks of Docker. Now let's see how Kubernetes, the orchestrator, solves those problems and that limitations of Docker. To solve these exact enterprise limitations, we need container orchestrator. This is where Kubernetes KEDA comes in. Kubernetes does not replace Docker. Instead, it uses Docker or other container runtimes to run containers, while Kubernetes handles the management. Simply, Kubernetes does not replace Docker. It uses the features of Docker, that Docker operates or containerization or its platform to run containers, while Kubernetes as a service handles the management of those containers. That means the creation, the scaling, the monitoring of containers, which was the limitation in the Docker, and it is managed by Kubernetes. First is solution to ephemeral nature. Kubernetes uses pods, the smallest deployment units, and controllers like deployments. If a pod dies, Kubernetes automatically spins up an identical replacement instantly. It also manages persistent storage volumes that remain intact even when the container dies. So simply, in Kubernetes, the smallest deployment unit is pods. It is not same as containers. In Kubernetes, pod are the smallest deployment units and controllers like deployments. If a pod dies, Kubernetes will automatically spin up identical pod replacement instantly. It manages persistent storage volumes that remains intact even when the container dies. So in Docker, where the container dies or it was stopped or it had some issues in its host, etc., the container was useless. We needed to deploy the same container again or manually do it. It's not same in Kubernetes. Kubernetes uses pods that are like the smallest deployment units. So if a pod dies, Kubernetes creates identical of the same pod automatically. Also manages storage of the container if it dies. Second is solution to single host nature. Kubernetes operates on a cluster, a pool of multiple servers. The Kubernetes scheduler continuously monitors the resource usage, CPU or RAM of every server in a cluster. When we launch a new container, the scheduler automatically places it on the server with the most available resources. So simply you can understand cluster as a collection of instances or multiple servers or multiple virtual machines or multiple instances like Ubuntu free tier. So Kubernetes doesn't necessarily operate on a single instance. It operates on multiple instances that are called clusters, which is like a pool of multiple servers. So there's a concept in Kubernetes that is scheduler that continuously monitors the resource usage, that is CPU or RAM of every server in the cluster. So when we launch a new container, the scheduler automatically places it on the server with most available resources. Also, Kubernetes can add more resources, that is, increase the cluster size or downscale the cluster size too if the resources are above the need. And if we don't need some resources, it can also scale down the cluster, that is the number of servers, which was missing in the Docker, the platform. Solution to auto healing. Kubernetes uses liveness and readiness probes. It actively checks the health of our application. If a container stops responding or fails a health check, Kubernetes kills it and starts a brand new automatically. So Kubernetes has a concept of auto healing, which is completely missing in the Docker. So it uses liveness and readiness probes. It actively checks the health of the application. If containers stop responding or fails a health check, Kubernetes kills it and starts a brand new automatically. Solution to autoscaling. Kubernetes features the horizontal pod autoscaler HPA, in which we can set the rules. For example, if the CPU usage goes above 70%, scale up. So that will allow Kubernetes to automatically launch more containers to handle that load and use its built-in service resource to load balance the traffic across all active containers. We will understand this concept further in our later videos. However, in short, Kubernetes has HPA, horizontal pod autoscaler, in which we can filter out or we can give instructions in a YAML file, which would mean like if CPU usage goes above 70%, that means there is more incoming traffic in the containers. So the Kubernetes would automatically launch more containers to manage that load. In short, it would load balance the traffic across all active containers, so all containers are healthy. The topic is understanding the architecture of Kubernetes and its components. Here is the diagram and the architecture of the Kubernetes. Kubernetes splits its responsibilities into two distinct planes, that is control plane and data plane. Data plane is also known as worker nodes. Nodes simply are virtual machines or physical servers. For example, if you are running a Docker container, you would be running it in a virtual machine, that is an EC2 instance. That itself is a physical server or a virtual machine. So in Kubernetes, it is called as nodes or node if it is single. So there is a concept in Kubernetes, that is worker nodes, which is also known as data plane. Worker node performs the task, and there is the concept that is control plane, which is responsible for controlling the data plane or the worker nodes. So in control plane, these components make global decisions. So for control plane components make global decisions about the cluster. Simply, cluster is a collection of nodes. Nodes simply is a collection of virtual machines. A single node is a single virtual machine. So collection of these nodes or virtual machines is known as cluster in Kubernetes. So control plane is responsible for making the global decisions about the cluster. For example, scheduling and detecting or responding to the cluster events. So all decisions are made by the control plane, and worker nodes operate on those decisions controlled by the control plane. In Docker, we had the smallest unit, that was container. In Kubernetes, we have the smallest unit, that is pod. Pod is not exactly container, but it is a wrapper around the container. So that was a simple split between the Kubernetes architecture, which has control plane and the data plane. Data plane also known as the worker node. And we can observe in this architecture, control plane has API server, etcd, scheduler, kube control manager, and cloud control manager. These are the components in the control plane of the Kubernetes architecture. And in the data plane, we can observe that there exists container runtime, kubectl, and kube-proxy as a components. Now let's understand them deeply. First, the control plane or the master. It has a component that is kube API server. The API server is the only way into the cluster. If we want to tell Kubernetes to do something, we send a request to the API server. It is the public face of the system. So every request is communicated to Kubernetes via kube API server or API server. Simply, API server is responsible for the communication of Kubernetes and its components to the external world, or communication of request and it performing the task. What it does, it receives our commands like run 3 pods. It checks if we have permissions to make that request, that is authentication, and it ensures that the request is valid, that is the validation. So why it matters? No other component talks to each other directly. The scheduler wants to talk to the node, it goes to the API server. It is a central hub that keeps everything organized and secure. So as I mentioned, no other component talks to each other. It needs API server to communicate. If the scheduler wants to talk to the node, it goes to the API server. So API server is the central hub that keeps everything organized and secure. Now etcd Kubernetes is stateless, meaning the component themselves don't remember anything. All the memory lives in etcd. So Kubernetes is stateless, so it doesn't remember anything themselves. It needs etcd, or it has the memory, that is etcd. What it does? It is a specialized database that stores the entire state of our cluster. It records exactly how many pods are running, which nodes they are on, and what their IP addresses are. So etcd is like the specialized database that stores entire state of our cluster. It records exactly how many pods are running in our cluster. It records which nodes they are on in the cluster and what are their IP addresses inside the cluster. So it is a specialized database that is responsible for managing the storage of our cluster. So Kubernetes itself doesn't have the components or anything that is responsible for storage. So it needs etcd to manage that. Why it matters? If the API server is the receptionist, etcd is the massive filling cabinet behind. If the entire control plane crashes and restarts, it looks at etcd to remember what it was doing. If we lose etcd, we lose our entire cluster. So you can remember this point. If entire control plane, that includes all components in the control plane, crashes and it restarts, so it would look at etcd that manages or acts as a specialized database to remember what it was doing. So in short, if we lose etcd, we lose our entire cluster. Now kube scheduler. When we ask for a new pod that is not exactly a container but a wrapper over a container, the API server doesn't know where to put it. It asks the scheduler. We know that Kubernetes has a concept that says that is auto healing and auto scheduling and auto scaling. In order to have those features run properly, there must be a concept that is scheduler, that is responsible for scheduling and assigning smallest units, that is pods, in the right position, in the right manner, and then in the right time. So kube scheduler ensures that the hardware is used efficiently. So what it does, it looks at our available worker nodes, that is the servers, and checks their health and capacity. It asks which server has enough RAM and CPU to fit this new pod. So we know that the worker nodes or the nodes are like the virtual machines or servers. So kube scheduler checks the health and capacity of it, and it simply checks which server has enough RAM and CPU to fit the new pod. Why it matters? Without the scheduler, our pod would just sit in the pending state forever. It ensures our hardware is used efficiently, not putting all the heavy apps on one server while others sit empty. Now kube controller manager. In Kubernetes, we don't start an app, we declare a state. Example, I want 5 copies of this app running. The controller manager is the person who makes sure that the reality matches our wish. So in Kubernetes, there is a concept of controllers. What is a controller? Controller is a concept where there are certain controllers which has certain responsibilities. For example, if we need replicas or we want 5 copies or 10 copies of the pod running, so there must be a concept that makes sure the replicas are running. So the controller has controllers, that is replica set, or something that manages the replicas of the application, and there are other controller as well which has some other responsibilities to do. Simply, there are many controllers that serve a purpose for our pods, nodes or cluster. So one of them is to perform the replicas of the pods, that is a controller. To manage these controllers that serve different purposes for our pod, cluster or nodes, there is a concept of kube controller manager that manages these controllers. What it does, It runs control loops that constantly watches the cluster. If we ask for 5 copies but a server crashes and now only 4 are running, the controller manager notices the gap and tells the API server, hey, we are missing one. Tell the scheduler to find a new home for it. So again, we got a concept of API server here. So everything is communicated through the API server. So Kube control manager notices only 4 are running, but we ask for 5. So it asks the API server to fill this gap or accept this request and to find a new home or new position for that pod. Why it matters? This is what makes Kubernetes self-healing. It is a component that fixes problems automatically without we having to wake up at 3 a.m. Cloud Controller Manager. Modern Kubernetes often runs on clouds like AWS, Google Cloud or Azure. These clouds have their own features like load balancer or storage disk that aren't part of the Kubernetes itself. What it does, it acts as a translator between Kubernetes and the cloud provider. If our app needs a public IP address, this component talks to the AWS or Google and says, please give this cluster a real world load balancer. So Kubernetes doesn't have load balancing on itself. It has a concept of load balancer or managing disk, but it needs a cloud provider to fulfill those requests. And there are many cloud providers. Each cloud provider has their own features as their own names for the same features they offer. For example, load balancer or storage disk, they have different names and different you can say different syntax or different, simply they are different cloud providers, so they are not same. So Kubernetes must be having a component that respect all these cloud providers and support them to fulfill their request or fulfill what they offer to us, like load balancer and these services. So Cloud Controller Manager acts as a translator between Kubernetes and that cloud provider to fulfill the request. Why it matters? It keeps the core Kubernetes code clean. By separating this out, Kubernetes can run exactly the same way on a laptop as it does on a massive cloud provider. So the summary of the flow would be, we tell the API server, I want 2 pizza. The API server writes order 2 pizzas into the etcd ledger, so it keeps the data of it. The controller manager sees the ledger, says 2 but sees 0 in the kitchen. It tells the API server to create them. The scheduler looks at the available kitchens, that is the nodes, and picks the one with the best oven. The kubelet, the cook of the kitchen, sees the order and starts cooking. So that was about the control plane or the master node. Now let's understand the worker node or the data plane. These are the boots on the ground that do the heavy lifting. It has a component that is kubelet. This is the node agent. It is the most important component on the worker node. It receives pod specs or the instructions from the API server and ensures the containers described in those specifications are running and healthy. If a container crashes, the kubelet restarts it. We know that pod is the smallest unit in the Kubernetes. So kubelet is a concept or is a component in the worker node that makes sure the health of that pod and makes sure the pod is up and running. It communicates with the API server to fulfill those demands to make sure it is always healthy and running as per our needs. The container runtime CRI. To run containers, Kubernetes needs a motor. We know that the smallest unit in Kubernetes is pods. So simply pods are the wrapper over the container. So there is still the concept of containers in Kubernetes, which means containers are still present inside the pod simply. So if there is a concept of containers, there must be a concept of container runtime. Container runtime makes sure containers are running. If there is no container runtime specified for a container would not run. So Docker has only Docker shim as a container runtime that talks to the Docker to fulfill container request. However, Kubernetes doesn't only rely on Docker shim. It can use Docker shim, but it can also use the competitors of the Docker shim, that is Containerd or Creo. So the old way would be Kubernetes use Docker shim to the Docker. Modern way is Kubernetes uses container runtime interface CRI. It now talks directly to runtimes like Containerd or Creo. Docker is no longer required to run a Kubernetes cluster. It can also use other providers as well. Now kube-proxy. This is the network supervisor. It maintains network rules on nodes. These rules allow network communication to our pods from inside or outside of our cluster. So in order to have certain features or certain benefits of Kubernetes, that is auto-scaling, auto-healing, etc., there must be a concept of strong network communication. Simply, kube-proxy is a concept or a component in the worker node of Kubernetes that takes care of the IP addresses of the pod and load balancing of the pod. Load balancing means load must be balanced accordingly so each pod is healthy and doesn't get affected with the performance of other pods. So kube-proxy makes sure of the IP addresses and load balancing of the pods. Now the smallest unit, the pod. While Docker's smallest unit is container, the smallest unit in Kubernetes is the pod. Important distinction: we do not deploy a container in Kubernetes. We deploy a pod. A pod is a wrapper that can hold one or more containers, usually just one, that share the same network IP and storage volumes. So the workflow would be Kubernetes works on a declarative model. We don't tell it start this, we tell it this is what I want the world to look like. So the first would be the request user API server. We send a YAML file to the API server saying I want 3 replicas of my web app persistence. API server etcd. The API server saves this desired state into the etcd, that is like the standardized database scheduler. API server. The scheduler notices new pods are needed. It looks at the worker nodes, finds one with enough RAM and tells the API server put these on node A. Execution. Kubelet. Container runtime. The kubelet on node A sees the assignment. It tells the container runtime examine container D to pull the image and start the container. Monitoring. Controller manager. API server. The controller manager constantly checks, does etcd say 3? Are there 3 running? If one dies, it starts the cycle again to fix that. The topic is understanding Kubernetes distribution, KOps, that is Kubernetes operation, DNS, KTS.local versus actual production domain, and understanding Route 53 and its use with respect to domains. A Kubernetes distribution is a prepackaged version of the upstream Kubernetes source code, bundled with the necessary configuration, installation tools, and integrated third-party components like networking, plugins, and container runtimes to make it operational. While Kubernetes is open source, the vanilla code requires significant manual effort to secure and scale. Distributions like Amazon, EKS, Google, GKE, OpenShift, that is for Red Hat, or KOps provide a curated, tested, and supported environment to simplify lifecycle management. So a Kubernetes distribution simply is a prepackaged version of the upstream Kubernetes source code, which means Kubernetes in itself is open source platform. So distributors or cloud providers, that is Amazon, Google, or Red Hat, has used that Kubernetes open source and added a few features here and there and created their own version of Kubernetes, that is EKS for Amazon, GKE for Google, and OpenShift for Red Hat, etc. Though the core components of Kubernetes are present, have added a few plugins, CLI tools, etc. The main point here is that they have added accountability and responsibility management, which simply means that if you face any issues regarding your EKS for Amazon or Google, etc., for these providers, they would be providing you with the assistance to solve the issue. However, if you use the Kubernetes in itself without these providers, you would have to deal it yourself, or they would also solve the issues, but it would not be as reliable as Amazon, Google, or whatever the other platforms offer, because they would also charge you some amount for these services. Now let's understand the role of KOps or Kubernetes operations. KOps is an open source tool primarily used to provision, upgrade, and manage highly available production grade Kubernetes clusters on cloud providers, specifically AWS. It is often referred to as the kubectl for clusters. KOps is same as Kubernetes, that is open source tool which is used for provision, upgrade, and to manage highly available production grade Kubernetes clusters on cloud providers, especially AWS. So KOps is an open source tool which is primarily used for provision, upgrade, and to manage highly available clusters of the Kubernetes on cloud providers, specifically for the AWS. And one more thing to remember is, although we are discussing KOps, but there are other options as well that is offered by other providers. For example, OpenShift for Red Hat, etc. But we are discussing KOps, which is most common and most widely used. Now, importance and purpose of KOps or Kubernetes operations. Infrastructure as a code. KOps generates the underlying infrastructure, EC2 instances, ASGs, VPCs, IAM roles required to run the cluster. Automated lifecycle. It handles complex tasks like rolling updates to nodes, operating system patching, and scaling the control plane. Self-healing. If a master or worker node fails, KOps ensures the underlying auto-scaling group ASG replaces it to maintain the desired state. So KOps helps in infrastructure as code and to automate the lifecycle and for self-healing, which simply is management of our production grade Kubernetes clusters on cloud providers. Now, S3 as the state store. When managing hundreds of clusters, KOps or Kubernetes operations require a single source of truth for configuration. It uses a S3 bucket as its state store. Why it is used for centralized management. Every cluster's desired configuration, instance types, networking, security groups is stored as YAML in S3. Consistency at scale. An administrator can manage hundreds of clusters from any machine by simply pointing the KOps state store environment variable to that bucket. Disaster recovery. Because the state is external to the cluster, you can reconstruct an entire environment from the S3 metadata if the control plane is lost. S3 bucket with respect to KOps is to store our configuration information or configuration data. For example, instance types, networking, security groups, which is stored as YAML in the S3 bucket. Administrator can manage hundreds of clusters from any machine by simply pointing KOps state store environment variable to that bucket. It is also used in disaster recovery. If the control plane and its data is lost, we can reconstruct the entire environment from using S3 metadata. So it acts as a backup of our data and information with respect to clusters in Kubernetes. DNS strategy .KTS.local versus actual domains. KOps uses DNS for cluster discovery. How nodes find the API server. The choice between a gossip-based domain and a real domain dictates how the cluster is reachable. Feature discovery. KTS.local uses gossip protocol, that is nodes talk to find each other. Actual domain uses standard DNS lookups via a provider like Route 53. Complexity. KTS local complexity is 0. No registrar or DNS configuration needed. Whereas in actual domain, it is high. It requires a registered domain and a hosted zone. Reliability. KTS local is prone to latency or scaling issues in very large clusters, whereas actual domain is rock solid, highly scalable and standard. Accessibility. KTS local is best for local development or simple private VPCs, whereas actual domain is essential for production and multi-account setups. For production and multi-account setups and production-ready environment, or for production, we use actual domain, and for local development or testing phase that is apart from the production environment, we use actual domain or production.example.com. Whereas if we are testing or in the local development stage, we can use KTS local to configure and debug information and to debug our cluster. And for production, we use actual domain, and for local development and for testing our application or any stage apart from production, we can use KTS local to debug or polish our cluster information and its availability, scaling, etc. After we confirm these information while performing test, while preparing our clusters in KTS local, once we are sure that it is scalable and it is really great for production, then we can switch to actual domain and provide the production ready clusters. Now, the necessity of Route 53. If we choose to use an actual domain instead of KTS local, KOps requires a DNS provider to create necessary records, records for API, SRV records for etcd. So we discussed that for local development or any development other than production grade, we can use .local, ktest.local for testing and local development apart from production. But when we confirm and when we are sure that the cluster is ready for production, we use the actual domain. So here comes a part when we use actual domain. In AWS, the standard or most widely used choice is Route 53. In AWS system, Route 53 is the standard choice. During KOps create cluster process, KOps will query the Route 53 hosted zone for your domain, automatically create the public or private entries for your load balancers, configure the internal cluster components to use these endpoints for secure communication. TLS or SSL certificates are often mapped to these DNS names. So for production grade, we use Route 53 as a DNS provider. So what Route 50 does is it queries the Route 53 hosted zone for our domain. It creates public private entries for our load balancers. It configures internal cluster components for secure communication. These are often mapped to these DNS names via TLS or SSL certificates. The topic is understanding the concept of pods and deploying multiple pods with single node architecture on Minikube for a Node.js application that is resume matcher. Let's begin. First, let's understand why do we need pods? Why is a Docker file not enough? And why do we need pods over container? First, we must know that Docker file has its power and benefits. Also, containers also have their powers and benefits. They do their purpose and their work. However, Docker file cannot scale up the application, scale down the application, cannot create replicas. However, Docker Swarm, etc., which can do that, but Docker file, in short, containerization concept cannot fulfill creating replicas, healing, auto healing, scaling, and scaling down of the application. So to do that, we need a concept that is Kubernetes orchestration. So that takes the concept of containers and it manages the orchestration of scaling down, managing the health and life cycle of those containers that are now wrapped around a pod. So I hope it makes sense. So now what is a pod? Pod simply is a wrapper over your container. So we know that we can create a container by creating a Docker file and building an image around it. That's great. But it cannot be scaled up, scaled down. It is a static. And if it is deleted or it has some issues, your data will be lost. So in order to fix those problems or issues in a Docker file or in container or containerization, we use the concept of pods in Kubernetes. So you would be having your Docker file for your application while you created a container of it. That's great. So you would take those information and prepare a pod deployment file, that is deployment.yaml. That's whose only purpose is to manage the lifecycle of your pod. So while you create the deployment.yaml with respect to your Docker file of your application that was containerized, now your container has some powers, that is scaling down, healing, auto healing, and replicas of those pods. In deployment.yaml, we specify information with respect to our Docker file that is used to scale up, scale down, heal, and replicas or to replicate the pods. Now let's understand with respect to my application, that is resume matcher, how I managed to pull off single node multiple pod architecture to deploy this application, which was running really fine on Minikube. First, you can observe the Kubernetes folder inside the application folder of mine, that is resume matcher DevOps. You can observe that there are certain files, that is configuration YAML, DB secret, deployment, API secret, CXID, Ingress, Postgres admin, PVC, Postgres.yaml, Postgres PVC new.yaml, and service.yaml. So these were the YAML files that I created in order to manage the working of my application. But ConfigMap.yaml, I use this to map specific sensitive information like passwords, API keys that I don't want to hard code that into the deployment.yaml. So it is like a secret management thing. So configuration management or configmap.yaml will have all the information regarding the API keys, and it would be having a certain keyword that is used in the deployment.yaml that maps to this config map. So that would have some secrets API keys for my application to run. A DB secret, it is a database secret.yaml file. In this, I have created a secret file for storing the password for the database access of this application. So deployment.yaml has the purpose of scaling and all these features of the Kubernetes for my application. And Google API secret.ml is also a secret file to store API key as a secret, and also same for CXID, or that is some configuration files to work my application. It was secret file. And Ingress.yaml, this is for my future deployment if I would be doing or deploying it on a host name or DNS. So Ingress would help in achieving that, to map DNS with respect to the application. So pgadmin.yaml, it is for Postgres admin.yaml. I used database, that is Postgres. So that is YAML file to configure the Postgres admin access. And pgadmin pvc is persistent volume with respect to Postgres admin access. Both pgadmin and pgadmin pvc YAML files are to manage the access of Postgres admin UI and persistence volume to access that UI or the site, which I would be doing later in this video, to access the database of this application. Just know right now that pgadmin and pgadmin pvc are used to help me have storage and configuration to access UI or user interface of database Postgres and to see the database visibly in the UI format. So these two would help me achieve that. So now it is Postgres YAML and Postgres PVC new.yaml. So these both are to store actual persistent volume information and configuration of Postgres database information and data that is stored inside the database. So admin was to access the UI, and Postgres PVC and Postgres YAML are used to actually store that information inside the database of Postgres. PVC or persistent volume is used to not lose the data. If it's persistent volume, the data would not be lost and it would be stored. Since pods are temporary, they can lose data. So unless we use PVC or persistent volume claims, that data cannot be lost. So I use persistent volume claim YAML file to store that database information. And finally, it is service.yaml, while deployment.yaml is used for having or providing scalable, healing, replicas, all those Kubernetes features, while service.yaml is used to create stable IP, load balancing, and to expose the application. We must know that pods are temporary and their IP addresses can change every time they are recreated. So we need a service.yaml to act as a permanent bridge. So service.yaml would assign a single cluster IP address or DNS name that stays same even if all the underlying pods change. It is used in load balancing. When traffic hits a service, it would route to one of the healthy pods matching its selector labels. Basically, it is to access your application on ports. So services would give you information. So in service.yaml, we will fill information with respect to our application and its information. For example, my application is DB, Postgres, and application itself. So there are 3 pods that would be running. It must have some ports to access that information so I can use my application. So in order to do that, we need service.yaml to map those ports. So deployment.yaml would be used to have Kubernetes features of scaling, etc. And service.yaml is used to map ports to access. So my application has Postgres UI database, so I can log into the UI of Postgres admin and see the database. So I would also need to have service.yaml that mentions this information to map ports to access this PG admin, and also my application in itself. So this needs ports. So if my application needs to be accessed, it must be in certain ports. As pods can change its IP addresses each time it is created or restarted, we need service.yaml to have a stable IP address that is like a bridge, so we can access our application easily and efficiently. So that was about the YAML files I have implemented and created. Now let's understand deployment.yaml in detail. So YAML files are always in a YAML format, that is API version kind deployment, and I named it resume matcher, and app is resume matcher. I want replicas, that is 2. I used Postgres version 15 as an image for my containers and its database, and we can see image name, that is Kef Mohammad Khan 123 /resume matcher DevOps. So that would be the constant name of the image pushed on the Docker hub. So it would pull that image with this name in it. Container port is 3000. We can see environment, that is Google API key. So this is a secret key or API key that I have stored in other YAML as a secret. We can see secret key reference, that is Google API key, which I showed before, like Google API key was a YAML file. You can see key, that is API key. And now it is Google CXID, same secret key reference, Google CXID, which I showed you, Google CXID YAML file to reference CXID as a secret. Now DB type and DB user are both database related information. For DB type, I have used Postgres as I mentioned, and for DB user, it has secret key reference, that is DB secret. In that DB secret, I have created password and username for my database for the database of the application, and it has Postgres user DB password. And for secret key reference, DB secret also has Postgres password. So one more thing to remember is Postgres is a UI. I have used Postgres UI to access the application database. So it has two database related information in this deployment.yaml. For a simple DB type, it is DB secret that has information for actual database without UI in it. So actual database has certain password in it. So that also has a DB secret YAML file that has that information. Also Postgres is the UI related to access that raw database. So that also has username and password. That is also kept in a DB secret YAML file. And DB host and DB port is 5432. And resources, it is CPU 100M, memory 128 MI, limits 500 CPU and memory 512 MI. And volume mods is uploads, and it is app/upload, name logs, app/logs. So this would store the uploaded resumes information. So whenever a resume is uploaded, the user's information, that is name and their email, are stored in the database to know who has entered or who is accessing and utilizing the application. So it is named uploads. Now service, that is resume matcher service, it is on HTTP with TCP protocol at port 3000, target port 3000, node port 30080, that is type node port. That was about deployment.yaml, which is used for having Kubernetes benefits, that is deployment, replicas, scaling, healing, all these features, which was not utilized or not accessible in a single container or in containerization concept. So it is a concept container orchestration in Kubernetes where we have pods that has this deployment.yaml, which allows us to have these production grade benefits for our application, that is scaling, healing, replicating. So that was deployment.yaml. Now let's understand service.yaml. I've mentioned that there are certain concepts in a YAML file or in Kubernetes that are really important for our application management. One of them is service.yaml. Some others were PVC for persistent volume, Ingress for DNS, secrets for secret management, configuration map for managing API keys and secrets, etc. So one of the most important is deployment and service.yaml. Now let's understand the purpose and explanation of service.yaml. As I mentioned before, service.yaml has a purpose to map ports of the containers that would be running. For example, if my application has containers for Postgres admin UI access to have visualization of the database, so I would have to create a service.yaml, and inside that I would need to specify ports and information directing towards deployment.yaml and all those other YAML files, so application would be accessible on those specified ports instead of getting a random or other ports every time the pod or replicas are created. So if my application has Postgres UI database access required to have visualization of database, so I would need to map some ports in it in the service.yaml. Also for accessing the application in itself, we need to map ports. So service.yaml acts as blueprint to have stable IP addresses within the range specified in this service.yaml. So first is Postgres deployment plus service. As mentioned, I have used Postgres SQL as a database, and it has the UI or the website pg admin, so it must have certain ports to access that website or that UI of Postgres admin. So this deployment with respect to Postgres is required. So replicas is one, labels are DB, that is database, containers that has the name Postgres, image version is Postgres 15, the port mapping is 5432, environment is Postgres user, value resume, password, and Postgres database name, that is ResumeDB. These information are used for database access. And API version 1 kind service that is mapped to port 5432, target port 5432, and that is of ClusterIP. Also, it is mounted to the path var/lib/postgres/data. Now, ResumeMatcher deployment service. It has name ResumeMatcher, replicas are 2, labels are ResumeMatcher, and container is ResumeMatcher, and image is, as I mentioned, that image pushed on Docker Hub would be named KF123/ResumeMatcher DevOps. So it has this name. So container port is 3000, name, Google API key, all these information are in the secret, also mentioned in the deployment.yaml, and database, username and password information, and resources, that is request with CPU 100M, memory 128 MI, limits are 500 M, and memory, that is 512 MI. Volume mounts are named uploads, app/upload, logs, app/logs. Now we are matching that as a service, that is ResumeMatcher service, with name ResumeMatcher, with label ResumeMatcher, selector app ResumeMatcher, ports HTTP TCP, port 3000, NodePort 30080, type NodePort. So that was about deployment.yaml and service.yaml and its use case and how it is useful with respect to my application. Now let's understand the working of this process. So first I headed into the git bash terminal and switched the directory to the application directory, that is ResumeMatcher DevOps, and I performed minikube start and it started successfully. Then I performed kubectl get nodes to get information on nodes. So it's at minikube, that is a name, and it showed status ready, role was control plane, that is master node, and it had version 1.31.35.1. Then I switched into the Kubernetes directory performing cd Kubernetes, and I performed kubectl apply -f space dot to apply changes and to configure the YAML files that I created, which I mentioned before, like all these YAML files, secret files, deployment, etc. To apply and configure this, the command is kubectl apply space -f space dot. This command would apply the apply feature to all the YAML files it finds inside of directory or a folder. If I would not perform this command, the other command would be specifying each YAML file and then performing the apply. So to save time, I perform this kubectl apply -f space dot that would apply to all the YAML files inside the folder, that is Kubernetes. After its successful configuration, I performed kubectl get pods to see the availability and status of the pods. One more thing to remember here is, if you do not perform the image pull with respect to your application post in the Docker Hub, your pod status might show errors with respect to image pull. So to fix those and to have your pods running successfully without any errors, you must first build your image by Docker build and push that image to the Docker Hub with respect to the tags specified in the deployment.yaml and service.yaml, and then pull that back again. So your pods and the minikube also would have that image as a reference to run these pods. If it would not be the case, then it would show image pull and some other errors as well. So I performed this command before, that was pushing the image, building the image, and pulling back that image with respect to the name I specified in the deployment.yaml and service.yaml, that was guys Mohammed Khan 123/ResumeMatcher DevOps. So after I performed all this, I performed kubectl get pods, and it showed name of the pods that were running successfully with the status running. As I mentioned, I performed replicas 2 for ResumeMatcher, so it shows 2 for ResumeMatcher, and single replicas for pgadmin and for single replicas for db. Knowing pods are running successfully, I performed minikube service space ResumeMatcher service to access my application. After performing that, the ResumeMatcher service, that is the application, was running on the port 55471. As you can see, it was successfully running, and I performed the upload of my resume and it showed results that were of a successful match. Then I performed change directory to the Kubernetes, and I performed minikube service pgadmin-service to access the pgadmin or simply the UI of the database. After that, it was accessible on the port 54186. So this is the PG admin or Postgres database admin UI. I performed the login with respect to the credentials that I had specified in the YAML files. After login, I clicked on add new server and I filled information name in the general, and in the connection section, I filled the information with respect to the information that I specified of my database. That includes passwords, ports, the database name, username, etc. that were specified in the YAML files. So it would pull all those information and show me here in the Postgres admin database UI. So after successfully configuring all those information, I performed the upload of the resume again to check the availability of database and to see its workability with respect to the PVC and all those YAML files that I applied, and I performed access to my resumes table in the PG admin. The database information with respect to the user that was uploading the resume was successfully visible. For example, I uploaded my resume and it showed the name Kaif Mohammad Khan, and it also showed the location as well, but it uses the resume parsing algorithm which can't be 100% accurate, so it is still better than nothing to show no results, but I'm convinced that it at least showed the name clearly. So it showed my name and it showed clearly the email of mine. Also showed skills it passed or performed algorithms to know the skill set of this resume, which was engineer AWS cloud, and it also showed timestamp of when it was uploaded. So that was about this video. I explained you the concept of pods and why it is used and why it is different from containerization, and how orchestration manages all the features of Kubernetes, that is healing, etc. And we understood the concept of YAML files and different types of YAML files with respect to the application you are running, and I showed you how I performed admin database as well as accessing my application, and how I successfully managed to run this application as well as the database on single node multiple pod architecture, performing replicas, memory, auto healing, all these features with respect to the topic is understanding containers, pods and deployments with respect to Kubernetes. The container is the smallest unit. It is a lightweight standalone package that includes everything needed to run an application code, runtime, system tools and libraries. So when we remember container, we remember Docker, where we had the concept of container that was really significant. So we would be building a container by the Docker image, and we would write the Docker file to build the Docker image. So that Docker file acts like a blueprint for the application to build, run, and container would be the application in itself. The role of the container is to ensure the application runs identically regardless of the environment, that is developers, staging or production. So what is the limitation in the container? It has no concept of networking or storage persistence on its own within a cluster. It simply executes the process. So we know that the container doesn't have persistence on its own, meaning if it is deleted, it doesn't have the capabilities of auto healing to get back the same container or other production grade benefits that is offered by Kubernetes. So if the container has some error or it faces some issues, and if the container gets deleted for some reason, it has some issues in starting and restarting of the container, it has a strong possibility of losing all its information and its data. That is the biggest drawback of container. So it doesn't have the benefits that Kubernetes offers, which is auto scaling, auto healing and all those production grade. Also, other than running the Docker compose in the concept of containers and Docker file, when we build a Docker image and when we run it, we would be specifying certain ports, exposing the ports while building and running the container image. So that is also a task to perform every time you build and run an image, that is to perform Docker run and perform certain flags and ports every time you build or run the container. Whereas when we perform pods or perform deployments, that is actual production grade benefits as well as efficiency, it doesn't have those issues or those limitations or those inefficient commands. That was about container. Now let's understand pod, which is the wrapper. In Kubernetes, we do not deploy containers, we deploy pods. Up is the smallest deployable unit and acts as a wrapper for one or more containers. So if Docker had the concept of containers, Kubernetes has the concept of pod, which is similar to container, but it is not exactly container. So we know that Docker container has certain commands to expose the port and then build it. In pods, that limitation is solved also if a pod has more than one containers that would also share the same local IP address and storage volumes, which is a bit better than the container. Although container has its own benefits and its own purpose, but the concept of pod is one level of the container. In Kubernetes, pod is the smallest deployable unit and acts as a wrapper for one or more containers. So what is the relationship? Containers inside a pod share the same local IP address and storage volumes. Pods are ephemeral in nature, that is, pods are temporary. If a pod fails, finishes its task, or the node it sits on reboots, the pod is deleted. A standalone pod cannot self-heal. If it dies, it does not restart itself. So pods are also temporary. Also, if a pod fails, it finishes its task, or the node it sits on reboots, the pod is deleted. Meaning it is not same as what containers would be doing, or what containers offers with respect to it getting deleted. It is not same. The pods that are getting deleted are the specific pods that would get deleted. That is the exact pod. Meaning if the pod is deleted, fails, or whatever that is mentioned on this ephemeral line, the near identical pod is created if we have specified replica set of more than one in the deployment file. Meaning if this statement was same as containers are temporary, if a container fails, finishes its task, or whatever reboots or the container is deleted, that would be considered as permanently deleted until we create a container manually again. But it is not same in Kubernetes. If we specify replica set of more than one, that is 2 or 3 for the pods, even if the pod fails, finishes tasks, or it gets reboots or is deleted, then near identical pod would be created. So it would not be the same pod in the sense of exact same, but it would be a near identical with same features and everything. Only thing would be it is a new pod. It is not same, but it is exactly same. Hope you get my point. Also, a pod stand alone cannot self-heal. If it dies, it does not restart itself. So this is very important point. We have been comparing pod versus container a lot, but we do not know the actual difference between pod, container, and deployment. A pod is near similar to the container if it does not have the concept of deployment. Meaning, if you only take the concept of pod and only a concept of container, it would have not much of difference other than you building a container by performing flags and ports, and you building a pod without it and only specifying that information inside the pod.yaml. Hope you get my point. It would be near same. So it would be if a pod created with this mindset without deployment that has replica set controller to have replicas for auto healing, then single pod YAML file would be same as Docker container. Deployment concept, that is deployment.yaml, makes a difference by letting users use the concept of controllers, that is replica set, for us to have more than one replicas or however replicas we want of a pod. So if that pod gets deleted, a new near identical pod is created. So that is the auto healing concept offered by the deployment.yaml, not exactly pod.yaml. Pod.yaml, if it is named pod.yaml with the replica set concept, and you are saying this is also my deployment YAML, then it is true. But if you are saying you have a pod.yaml with no controller, that is replica set concept, then it is similar to container with it having flags or ports to run without you performing Docker run with the flagging of the ports. The pod cannot self-heal on itself. If it is inside the deployment YAML file that has controller, that is replica set, then it can self-heal. If it dies, the new near identical pod is created with respect to the specified replica set of the pods that we specify. That was about pod. Now let's understand the deployment, that is the controller. A deployment is a higher level object that manages pods. It defines the desired state of our application. The replica set. The deployment manages the replica set, which is the specific mechanism that monitors the number of running pods. Auto healing. If a pod is deleted or crashes, the deployment notices the discrepancy between the desired state, example 3 replicas, and the actual state 2 replicas, and automatically spins up a new pod. Rollouts and versioning. Deployments allows us to update our application version, rolling updates, or revert to a previous version, rollbacks without downtime. So as mentioned, pod in itself cannot self-heal and perform the task that Kubernetes screams about. So deployment is a high-level object that offers those benefits to the pods. So it defines the desired state of our application. So it has a concept of replica set that is a controller. While I explained the concept of controller and controller manager that is in the architecture of Kubernetes. So controller is one of it, and there are multiple controllers in Kubernetes. One of them is the replica set. So a replica set is a controller that manages replica set, which is the specific mechanism that monitors the number of running pods. Meaning, if you specify 3 replicas in the replica set, and if our pod gets somewhat errors or whatever, and the actual state is 2 replicas, so the replica set and the deployment would communicate to the API server of the Kubernetes, and it would spin up a new pod. Also, it offers rollouts and versioning as well. So that's the difference. Pod in a single concept without replica set in it and without a deployment file in it is similar to the container. If the pod gets deleted, it would be permanently deleted without auto healing. However, if the pod are specified inside a deployment YAML file with replica set controller and specifying certain replicas, then it would have the concept and the benefits of auto healing and rollouts and versioning. So that is a difference between containers, pods, and deployment. Now let's understand this table. Container management level is runtime. Key responsibility of container is to run the application code. Does it have self-healing? No. So pod has the management level of resource. Its key responsibility is to provide IP and storage to containers. Does it have self-healing on its own? No. Deployment management level is orchestration. The responsibility is to maintain the count and version of the pods. Does it have self-healing? Yes. So the topic is understanding Kubernetes services. In Kubernetes, a service is an abstraction that defines a logic sets of pod and a policy by which to access them. Because pods are ephemeral, they can be destroyed and recreated with new IP addresses. Services provide the stable networking required for reliable communication. We must know that pods are ephemeral in nature because it can be destroyed and recreated with new IP addresses. Meaning, even if we have created pods with replicas controller inside a deployment YAML, the new pods that are created after another getting destroyed will have the new IP addresses, which is not same as the before. New pod will not have the same IP address of the destroyed pod. So we need a services concept in Kubernetes that creates a bridge between those volatile IP addresses of destroyed and new pods and gives a stable IP address for accessing and troubleshooting our clusters. Core functions. Service discovery. Instead of tracking individual pod IP addresses, services use labels and selectors. The service monitors pods with specific labels and automatically updates its internal list of healthy targets. So services does not rely or depend on volatile IP addresses that are getting destroyed and that are created with new pods. So it depends on labels that we assign while creating a deployment.yaml, which specifies labels with respect to the pods that are created. So what will happen? It does not rely on volatile IP addresses and it will rely on those labels. So it redirects those volatile or new pod IP addresses with respect to the labels, and it gives new or fresh cluster, node, or load balancing IP addresses. So now what is load balancing? It is a service that acts as a single entry point, that is a virtual IP address. It receives incoming traffic and distributes it across all pods that match its selector, ensuring no pod is overwhelmed. Load balancing is a single entry point for a virtual IP address, meaning if you decided that your application is stable and it has no or minimal errors and you want to deploy it, so you would be using load balancing concept that would give your application a stable virtual IP address that has the capability of load balancing, meaning with respect to the number of pods inside your cluster, the load or the traffic that is received within the application or the single pod would be divided equally or would be divided with respect to no pods getting overwhelmed in this process. So that single virtual IP address is enough to access the application, but that virtual IP address is not professional, so we use Route 53 or other providers, that is GoDaddy, and put that virtual IP address of load balancing and create a custom and redirect that to the custom domain name service. Now, DNS resolution. In Kubernetes, it provides a DNS service. Any service created is assigned a DNS name. For example, my API service, allowing microservices to communicate using names instead of hard-coded IP addresses. So we know that IP addresses are volatile with respect to pods when it gets created and it gets destroyed. So there must be a concept that is DNS service that provides DNS service name, that is, for example, my API service. It allows microservices to communicate using names instead of hard-coded IP addresses that are volatile in nature. So now workflow. Selection. The service uses a selector to find all pods with matching labels. Endpoints. Kubernetes maintains an endpoints object that holds the real-time IP addresses of those matching pods. Routing. When traffic hits the service IP, the kube-proxy component on the nodes routes that traffic to the one of the pod IPs listed in the endpoints. So accessibility of your application or pods, it's through labels, and those labels are communicated by endpoint object that holds the real-time IP address of those matching pods, meaning those volatile and new real-time IP addresses are maintained by Kubernetes as endpoints. And when the traffic hits the service IP, the kube-proxy component on the nodes route that traffic to one of the pod IPs listed in the endpoints. So endpoints has the real-time IP addresses that are created, and it keeps those information real-time, and kube-proxy component of the nodes routes that traffic to one of the pod's IPs in those endpoints. Now, service types and accessibility. Kubernetes offers different levels of exposure depending on whether the traffic is coming from inside or outside the cluster. First is ClusterIP internal. Function, the default service type. It exposes the service on the internal IP within the cluster. Access, only reachable by other resources inside the same Kubernetes cluster. Use case, internal databases, caching layers, or private microservices. So Kubernetes offer different levels of exposure depending on the traffic, whether it is coming from inside or outside the cluster. The first was ClusterIP. ClusterIP, its function is for communication between the microservices, that is database, front end, back end. All the services communicate through ClusterIP, meaning inside the Kubernetes cluster. Now NodePort, that is internal or external. Its function, it exposes a service on a static port, typically 30,000 to 30,767 on each worker node's IP. Access, reachable from outside the cluster by calling node IP NodePort. Use case, development environments or scenarios where we want to route traffic to nodes manually without cloud managed load balancer. So NodePort is a static port that has range between 30,000 to 30,767 on each worker node. However, it is a volatile IP address, meaning you can still access the application using node IP address, which is still not secure, but you can access it. But that nodes change and that are volatile, so it can change anytime. But that is used in development environments or scenarios where we want to route traffic to nodes manually without cloud managed load balancer. So you can remember NodePort as it is an accessible IP address, but it is volatile. It can change from the range 30,000 to 30,767. So it is not efficient to access. So that issue is solved by load balancer that provides a static or a single public IP address that is not volatile. So now let's understand load balancer, that is external or cloud. Its function. Load balancer is specifically designed for cloud providers, that is AWS EKS, Google GKE, Azure AKS. It automatically provisions a native cloud load balancer, for example AWS ELB or NLB. Access, reachable via public IP address or DNS name provided by cloud vendor. Mechanism, it automatically builds upon NodePort and ClusterIP to route external public traffic down into the specific pods. But before I explain load balancer, let's again understand NodePort accessibility. I mentioned NodePorts are volatile. Even if we try to access it, we can, but we have to specify those allowing the traffic for outside the cluster, meaning we have to specify in the AWS that we are allowing the traffic on these ports for public. And if we perform that and it generates a node IP and we try to access it, we can access node IP, but it is volatile. It can range from 30,000 to 32,767, so can change anytime. So it is not efficient. So it is solved by load balancer. So load balancer is a service provided by cloud providers. It provides a reachable public IP address or a DNS name that can be provided by Route 53 with respect to using public IP address by the load balancer. Load balancer as a mechanism that automatically builds upon NodePort and ClusterIP to route external public traffic down into specific pods and balance those traffic so no single pod gets overwhelmed by the traffic. So it balances all the load across the pods, and load balancer provides a single public reachable IP address, and if we try to access that IP address, we can access the application, and that IP address is not volatile as the node port, and it is a single IP address, and we can use that single IP address on the code ID or route 53 after we create a DNS name, and we can provide that public IP address and we can access the application. Now, service type ClusterIP, accessibility internal only. It is service, no cloud requirement. Node port, it is external via node IP, direct access to worker nodes. It is not a cloud requirement, no. Load balancer, external via public IP, purpose, production grade public traffic. Cloud requirement, yes, cloud provider. So that the topic is understanding Docker Swarm versus Kubernetes, Docker container versus Kubernetes pod, what is a namespace, the role of kube-proxy, NodePort versus load balancer. Docker Swarm versus Kubernetes. While both are container orchestrators, they differ significantly in scale and capability. Docker Swarm, it is built into the Docker engine. It is focused on simplicity. It is easy to set up and great for smaller projects where we just need to run containers across a few machines without complex networking or auto scaling. Whereas Kubernetes or KEDA is built for complexity and scale. It offers advanced features like auto scaling, self-healing, restarting failed containers, and intricate networking. It is the industry standard for production grade enterprise environments. So we know that these both are container orchestrators, meaning Docker itself or containerization is just containerization concept, whereas we need orchestration of it that is better than containerization. So these both are orchestrators. Simply, these both are container orchestrators. Docker Swarm is for smaller projects or teams that are really small, not big organizations. They can implement Docker Swarm as it is simple and easy to set up, and we would just need to run few containers across the machines without complex networking or auto scaling. That is a concept in Kubernetes. Whereas in larger organization where there exists scalability and enterprise production grade environments, this is the industry standard because it is built for complexity and scale. Kubernetes offers features like auto scaling, self-healing, that is restarting the failed containers, and integrate networking. So this is a standard. And Docker Swarm is used for smaller projects or small teams, whereas for larger organizations that build complex and applications that would be having a lot of traffic and a lot of users handling it. So for bigger applications and bigger teams, there is a concept of Kubernetes. However, today's world, we always prefer Kubernetes as a skill, so it is just for knowing and understanding, whereas Docker Swarm is still used by some organizations, whereas Kubernetes is a standard right now. Even if it is a small organization, they would still need you to learn Kubernetes as a concept and for practical as well. So its feature, that is setup, Docker Swarm is fast and easy, whereas Kubernetes is complex and intensive. For scalability or scaling, Docker Swarm is manual in scaling, whereas Kubernetes is auto scaling based on traffic. For flexibility, Docker Swarm is limited to Docker ecosystem, whereas Kubernetes has highly customizable, supports various runtimes. That was about Docker Swarm versus Kubernetes. Now Docker container versus Kubernetes pod. The fundamental difference is how they are managed and isolated, meaning Docker container, this is the smallest unit in the Docker world. It is a single isolated process running our code and its dependencies, whereas Kubernetes pod is the smallest unit in Kubernetes. A Kubernetes pod is a wrapper that can hold one or more containers, meaning containers inside the same pod share the same network IP address and storage volumes. We can think of pod as a house and containers as room within that house. So the simple differentiation between these is that Docker is the smallest unit in Docker world and Kubernetes pod is the smallest unit in Kubernetes. Docker, it is a single process that is isolated, running the code and its dependencies, whereas Kubernetes pod is a wrapper that holds these containers that can be one or more. If there are more than one containers, that is two, they will share the same network IP and storage volumes inside a pod, and we can think of pod as a house and containers as room within that house. Also, a difference is Docker container is independent of YAML, whereas in pod we specify pod specification, which is exactly similar to the Docker file. So we write that in the YAML file, that would be pod.yaml or deployment.yaml. So Docker container doesn't have YAML as a concept for writing Docker file or everything, but Kubernetes pod is a concept where we write those information in the YAML format. Now, what is a namespace? In Kubernetes, a namespace is a virtual cluster within our physical cluster. It is used to organize and isolate resources. We can imagine that as a large office building that is the cluster, where namespaces are the different departments, that is HR, finance, engineering. Even though they share the same building, the HR team's files are kept separate from the finance team's files. This prevents naming conflicts. We can have a service named web app in the development namespace and another one also named web app in the production namespace without them interfering with each other. Namespace is a virtual cluster inside our physical cluster. Its main purpose is to isolate resources. For example, we can think of office building, that is a large office building, as the cluster that is the physical cluster or the main cluster. And we can think of namespaces as different departments inside that same office building, that is HR, finance or engineering. So these three can be different clusters, that is virtual clusters inside the main cluster. Even though they share the same building, that is the same main cluster, but HR team's files, that is the virtual clusters files or its data or its working, everything is separate from the other cluster inside that main cluster team's files or its data. So this prevents from naming conflict, and we can have same name services, for example web app in the development namespace or development cluster, and also the same name, that is web app, in the production cluster, that is namespace, without them interfering with each other. Now, the role of kube-proxy. Kube-proxy is a network proxy that runs on every node in our cluster. Its primary job is traffic routing. It maintains network rules on nodes. When a request comes in for a specific service that is like a database, kube-proxy decides which pod should receive that request. It acts as a distributed load balancer, ensuring that traffic reaches the correct container regardless of which node it is living on. Inside a cluster, there is a concept of the network proxy, meaning kube-proxy is that network proxy that runs on every node in that cluster. Its primary job is traffic routing, that would be maintaining networking rules on nodes. For example, when a request comes from a specific service, like it is a database, kube-proxy will decide which pod should receive that request. It acts as a load balancer, ensuring that traffic reaches the right or correct container regardless of which node it is living on. Basically, traffic routing and maintaining load balancer and networking rules on nodes inside the cluster. Now, NodePort versus load balancer. These are different ways to expose our application to external traffic, meaning NodePort exposes the service on a specific port, usually between 30,000 to 32,767 on every node's IP. If we have 5 nodes, we can access the app using any node IP port. It is primarily used for testing or internal services, whereas load balancer is the standard way to expose a service to the internet in a cloud environment, that is AWS or Azure. It creates a single external IP address provided by the cloud provider. It automatically routes traffic to the node ports across all our nodes, providing a professional, stable entry point for users. So in Kubernetes, there is a concept of Kubernetes services, which says that there would be different ways to expose our application to external traffic. There exists ClusterIP, NodePort, and load balancer. NodePort exposes the service on specific port with these range on every node's IP. It is primarily used for testing or internal services, meaning we test our application or services in Kubernetes before exposing it to the load balancer. We would be performing NodePort expose to test our application, and then we can expose that application if it is production ready by load balancer. Now, load balancer, this is the standard way to expose the service or the application to the internet in a cloud environment, that is AWS or Azure or other cloud platforms, where NodePort was having the range between 30,000 to 32,767, which is volatile and fluctuating, whereas here in load balancer, it creates a single external IP address provided by the cloud provider. It automatically routes traffic to the node ports across all our nodes, providing a professional, stable entry point for users. Simply, you can understand NodePort and load balancer by knowing that NodePort is a volatile range of port from 30K to 32K approximately. So if we were to expose the application within this range publicly, there would be a lot of conflict and there would be a lot of fluctuations in accessing the application through that service NodePort, because there is a range that is too much or too high, that is like 30,000 to 32,000. So accessing the application would be inefficient. So load balancer acts as a pipe or a filter that creates a single external IP address that is provided by the cloud provider, and it automatically routes that traffic from that single IP address to these node ports that are fluctuating, but it is real-time access. So that single IP address from the cloud provider will route the traffic across these node ports ranging from 30k to 32k. So that single external IP address we can use Route 53 or GoDaddy or other platforms, and we would be assigning that load balancer external IP address inside the web domain or DNS to expose the application. The topic is understanding drawbacks of services type load balancer and how Ingress changes the flow and how enterprise level capabilities are provided by Ingress. Drawbacks of services type load balancer. While a service of type load balancer works, it is inefficient for enterprise level scaling for two main reasons. That is cost and resource exhaustion. Every time we create a load balancer service, our cloud provider, that is AWS, GCP or Azure or other providers, provisions a network load balancer, that is NLB, and a static IP address. If we have 50 microservices, we pay for 50 load balancers. This is expensive and difficult to manage. Lack of layer 7 intelligence. Standard services operate mostly at the transport layer, that is layer 4. They can route traffic based on IP and port, but they cannot look inside the traffic route based on URL path, that is example /API//API versus /web, or manage SSL certificates for multiple domains on a single IP. We know that load balancer is one of the services provided by Kubernetes services. There are ClusterIP, NodePort and LoadBalancer. LoadBalancer is for balancing the load across the pod. The services load balancer type provided by Kubernetes only offers round-robin load balancing, not enterprise level benefits or scaling. These are offered by Ingress controller, for example, that is Nginx. So one of them would be cost and resource exhaustion. For every service type load balancer, we create network load balancer and a static IP address. And if suppose we have many microservices, that is example 50, we should be paying for the 50 load balancers, which would be expensive and difficult to manage. Whereas if we have Ingress that would manage that, and instead of many load balancers, there would be only a single load balancer with many services that is managed by Ingress controller. And Ingress, it doesn't have layer 7 intelligence, which means it cannot look inside the traffic to route based on URL path or to manage SSL certificates, which are required for HTTPS secure website for multiple domains on a single IP. That is also managed and provided by Ingress. Now, how Ingress changes the flow. Instead of giving services its own entry point, Ingress acts as a single front door for the entire cluster. So the workflow would be deployment of Ingress controller. We deploy a controller like Nginx, HA-proxy or traffic. This controller is backed by one single cloud load balancer. Creation of Ingress rules. The user or the developer creates an Ingress YAML file. This file contains the routing rules. For example, sending the traffic on example.com/shop, https://example.com/shop to the shopping service. The watcher mechanism. The Ingress controller constantly watches the Kubernetes API. The moment we apply our YAML, the controller detects it and automatically updates its internal configuration, for example, updating the nginx.config dynamically. So workflow for applying Ingress would be, we would first create Ingress YAML file that would have routing rules. For example, that would be sending the traffic for example.com shop. For example, sending traffic to certain domains and subdomains. Simply it contains the routing rules, and we apply that YAML file. And we would be assuming that that YAML file would be enough to create our Ingress configuration and to provide services of enterprise level. But it doesn't happen that way. It needs Ingress controller to manage those rules or routing rules provided in the Ingress YAML file. Then we would be deploying the Ingress controller. For example, there are many, that is Nginx, HA-proxy or traffic. These controllers are backed by one single cloud load balancer. So after we deploy the Ingress controller, the Ingress controller constantly watches the Kubernetes API. The controller automatically detects it and updates its internal configuration, that is, it updates the nginx.configuration dynamically. So before Ingress controller, we would be applying the YAML file of Ingress and it wouldn't do anything, or it wouldn't update or doesn't have anything. But after we deploy Ingress controller, the controller automatically detects and updates the configuration of it. Simply we can understand it by knowing that relationship between YAML file of Ingress and Ingress controller is same as your device and operating system. Without the operating system, your device wouldn't work. So it's same. Ingress controller is like the operating system. Without it, YAML file is of no use. So we apply for the YAML file and we deploy the Ingress controller. So it is simply like the operating system for the Ingress YAML file to make it work. Now, enterprise level capabilities provided by Ingress. When the Ingress controller processes our YAML, it provides features that a standard service cannot, which is content-based routing. We can host multiple applications behind a single IP address using host-based routing, which is app1.company.com and app2.company.com. Both point to the same IP but go to the different services. Path-based routing, that is company.com/login, https company.com/login goes to the authentication service, while company.com/search, that is https company.com/search goes to the search service. So we know that to save the cost to provide enterprise level benefits and services, there is a concept of Ingress, which is not where typical load balancer by Kubernetes services doesn't provide. So typically we would assume that we would need multiple load balancer to manage the services and routing. It is not like that, because Ingress controller provides host-based routing, which is if the domain that is app1.company.com and there is domain app2.company.com, both can have same single IP address but can go to different services with respect to their domain. So we save the cost of static load balancer service. And for path-based routing, it would be for the same IP, it would company.com/login goes to authentication service, while company.com/search would go to search service. SSL or TLS termination. Instead of managing SSL certificates on every single pod or service, we upload the certificate to the Ingress controller. It handles the decryption at the edge, saving CPU cycles for our internal applications, which would be advanced traffic control. Ingress controller like Nginx allow for rate limiting, preventing DDoS attack by limiting requests per second, authentication, requiring a login before the traffic even reaches our internal service, whitelisting, allowing only specific IP addresses to access certain parts of our application. So SSL certifications are required to secure our websites. SSL certificates provide HTTPS to the website. So instead of managing those certificates on every single pod or service, we upload the certificate to the Ingress controller and it handles all the decryption, saving CPU cycles for our internal applications. And it also provides rate limiting, authentication, whitelisting, blacklisting, all these benefits as well. Now the summary would be: feature, that is cloud cost. For service type load balancer, it is high, that is one load balancer per service, whereas in Ingress with controller it is low, that is one load balancer for many services. Feature, that is IP addresses. For the service type load balancer, it is multiple static IPs required, whereas for Ingress with controller it is single static IP. Feature, that is routing. For service type load balancer, it is simple port/IP routing, whereas for Ingress with controller it is complex URL or path routing. Feature, SSL management. It is for service type load balancer it is complex or individual, whereas for Ingress with controller it is centralized at the controller. Feature, that is logic layer. For service type load balancer it is layer 4 network. For Ingress with controller it is layer 7, that is application. The topic is RBAC or role-based access control in Kubernetes. Role-based access control in Kubernetes, or simply role-based access control or RBAC, means that any application, cluster, instance, etc. should not grant admin access to every user. Meaning by default these services give admin access to every user that is being created. To prevent that, we need role-based access control. It can be in any other platforms or dynamics, that is in instance, AWS, etc. However, with respect to Kubernetes, it is same. We need role-based access control to give certain users certain access that they only need it, not all access, so they can misuse or they can accidentally misuse that to cause damage to the services and the platform. What if we gave admin access to all? If every user in an organization that access cluster or manages it has all the access, meaning quality engineers, developers, DevOps engineers, and if it is a bigger organization, there might be other as well. So if all of these have same access, same control towards the cluster, there would be a lot of mess and it will be difficult to find who made the mistake or who made the blunder. Even if we find out that, it would be late and the damage would be done. To prevent these issues, that is security and deletion of important files or aspects of the cluster, we need role-based access control. Role-based access control is a concept where it grants certain users that only need or have certain responsibilities with respect to the task, and we give them that much access or control towards the cluster. Only admin or administrator will have all the access, and other users, that is developers, quality engineers, DevOps engineers, will have access to the cluster with respect to their responsibilities and how much access they need to fulfill their job and responsibilities. This prevents from security and deletion and management of the production grade environment in an organization. Let's now understand first, that is the identity layer or OAuth, OIDC, IAM. In production, we offload user management. We do not create users inside Kubernetes. The source of truth. We provide AWS, IAM, Okta or Google Workspace via OAuth 2 or OIDC. The login. When a user, for example KEF, authenticates via command line interface CLI, the cloud provider issues a JWT token. The mapping. The Kubernetes API server validates this token. It sees that KEF belongs to the AWS group, that is platform engineers. Kubernetes now recognizes KEF as a valid entry, but he has no permissions yet. So to implement role-based access control in Kubernetes, first we must know there is a concept of user management. It exists in Linux and other as well, but we know simply user management by user add or add user, which means like we do it in the CLI for user add or add user, which grants certain permissions and access to it. However, the best and efficient way to do it is via offloading that headache to other providers. For example, that is OAuth, OIDC or IAM, meaning instead of managing or creating every user manually inside the CLI via commands of Linux, we can offload it via these service providers. For example, we would be creating groups and users in these providers. For example, there would be existing groups and users in these providers, that is OIDC, OAuth or IAM, and we would just integrate that through CLI and manage Kubernetes. And you would be using any cloud provider first and then login in via CLI, and then the Kubernetes API validates this token. If it sees that KEF, that is a user that is logging in, belongs to the AWS group platform engineers, Kubernetes now recognizes KEF, that is a user, as a valid entry, but he has no permissions yet. But it is just a step for the login in or user creation or user management. We are offloading it via other providers where this group and this user exists or it is created, and we are just using that information to log in via CLI to manage our Kubernetes. I hope you get the point. Like if there exists a website, we are not always using that website for logging in, meaning there exist certain options in websites, that is Google or other. So we use simply Google, so it is easy for us to log in via it. So it is same as that. Instead of we manually creating users one by one in groups, we offload that user management that gives us clean interface as well with these providers, so we know how much access is required or it is given to the users, that is in the interface format of these providers, as well as we can go into CLI with the login and let users access it with respect to their permissions and role-based access control. But yet they don't have permissions for Kubernetes. It would be given in the next step. The authorization layer in role-based access control. Now that Kubernetes knows who is KEF or user is created, we apply role-based access control. This is a 3-tier system. First is the definition, the role. We can think of it as a job description. It is not tied to the person. It defines what can be done. First is role, where permissions for one specific namespace, that is production, payments. Cluster role is to give permissions that work across the whole cluster, for example viewing all nodes. So as the user is created, now we define role-based access control with respect to Kubernetes environment. We know that there exists the concept of namespace and cluster. Cluster is a collection of virtual machines or instances, whereas namespace is an isolated environment across the cluster. So if there exists the namespace production payments, it would be having certain permissions that would be called role. And when an user enters this namespace, it would be having those permissions with respect to it. And if there exist these permissions with respect to the cluster, it would be called cluster role. Now B is the subject or the user or group. This is the identity we got from the step 1. We prefer using groups. For example, system, masters or dev group. So we don't have to update Kubernetes every time a new person is hired. So the subject means we don't use single users to manually give permissions to it. Instead, we create groups that would have certain permissions and we add those users to this group. If this group would be having certain permissions like role-based access control, so members of this group will have access or control with respect to it. And when a new user is added to this group, it would be having those permissions and access control. So we don't have to update Kubernetes every time the new person is hired. Now see the binding, the connection. This is the action of assigning a role to a subject. Role binding, assigning the developer role to the engineering group in the staging namespace. If the user is in the engineering group, he automatically inherits those permissions. So all this ABC works together or they are interconnected as it is a 3-tier system, meaning the subject, the definition, the binding, all this connect together to form this statement. That is, if a user is in the engineering group, he automatically, that is, assign the developer role to the engineering group in the staging namespace. The definition that had cluster role and role, which means these are independent role that is in namespace. These are independent role-based access control with respect to these namespaces. For example, production payments will have certain permissions in it, whereas in cluster role, it would have certain permissions in it. For example, viewing all nodes. And in second, that is the user or the group, the certain groups will have certain permissions and the user is added to that group, and it is in the binding stage where these two are binded, and it would look like assigning the developer role to the engineering group in the staging namespace that covers the definition, the subject and the binding. So it would look like if the user is in the engineering group, he would automatically inherit those permissions. Tricky thing here is understanding role and cluster role. We can simply understand them as rules. Instead of role, we can remember them as rules. So in a namespace, there will be certain rules for a certain namespace, meaning it would have certain permissions and access control for that specific namespace. So it would be called role. And if it is with respect to a certain cluster, that means rules with respect to or permissions with respect to that specific cluster, it would be called cluster role. So we would be creating certain role and cluster role with respect to the namespace and the cluster for role-based access control. And users, we know that it is added in a group that has certain permissions. It automatically will have permissions for that user. And in C, we bind those A and B. So it would look like if a user is added in the engineering group, he would automatically inherit those permissions by the help of role binding. Now, the service layer, machine to machine. Users aren't the only one who need permissions. Application, that is pods, need them too. This is called service management. Service management SA is an identity created inside a Kubernetes for a pod. The connection. We use a role binding to attach role to the service account just like we did for a human user. Cloud offloading IRSA. If the pod needs to talk to the AWS S3, we annotate the service account with an AWS IAM role ARN. This bridges the KEDA's internal identity to the AWS external identity. So until now we understood the permissions with respect to the users having access, first access with respect to the cluster and doing actions according to it or in the namespace. Now we get the point that users need permissions, role-based access control, etc. But applications or the pod need them too, which is called service management. By default, there is a service account created inside a Kubernetes for a pod. We would be doing same what we did previously for the user. Now it would be with respect to the application or pod, meaning we will be using role binding concept to attach role to the service account just like we did for the human user. Cloud offloading IRSA. If a pod needs to talk to AWS S3, we annotate or update the service account file or service account with an AWS IAM role ARN, which would bridge the KEDA's internal identity to the AWS external identity, basically connecting both. So the flow would look like identity, OAuth or IAM. The user logs in, AWS says this is Kaif, he is the admin, he is the software developer, he is the DevOps engineer. It can be anything. Second would be mapping. EKS maps the AWS admin group to the KEDA group. That would be cluster admin, software engineer, DevOps group. Role-based access control. A cluster role banding exists that connects cluster admin, cluster software engineer, whatever group the built-in cluster admin, software engineer, DevOps engineer in the cluster role. The action would be if the user can now manage the clusters. Service, if the user deploys an app, he creates a service account and a role so the app can read its own configuration, then uses IAM offloading so the app can store logs in the S3 bucket. So this is what the flow would look like. Now summary would be: feature for the identity source. For user management, it is external IAM Okta or OAuth. For service management, it is internal KEDA service account. Feature auth method for user management humans, it is token or certification via kubectl, whereas for service management or apps, it would be mounted token inside the pod. Feature permission tool for user management humans, it is role-based access control, role or cluster role. For service management, it is same, role-based access control, role or cluster role. Feature cloud integration for user management or humans is EKS access entries or AWS auth, whereas for service management application, that is IAM roles for service accounts, that is IRSA. The topic is understanding custom resource definition, custom controller with respect to Kubernetes. Custom resource. A custom resource is an object that we create in Kubernetes that isn't part of the standard installation. It is essentially a piece of structured data, usually YAML, that represents a specific configuration or state we want to achieve. The analogy: if a standard pod is a default form provided by the government, custom resource is a custom form we design ourselves to track something specific. The purpose: it allows us to store and retrieve our own data using Kubernetes API kubectl. So the concept of custom resource definition and custom controller is to know that there exist default or standard resources provided by Kubernetes. For example, there exist replica set, there exist Ingress, there exist services, and there exist few more services or resources that are already part of the Kubernetes environment. So there are services like Argo CD, and this is not called resource part of the Kubernetes, but it is a useful custom resource that provides GitOps. So there exist a lot of custom resources that are already verified, and Kubernetes basically says that I have done my heavy lifting of adding standard resources, that is like replica set, services, Ingress, etc. Now if you want to add other resources, that is custom resources, do it yourself. So doing yourself is a part of creating custom resource definition, custom resource, and custom controller. Another example would be, we know that there exists a concept of Ingress, which exists to manage load balancer, meaning we don't need multiple load balancers and we can manage that by Ingress with a single IP. So that is the function provided by Ingress. Now there exists Ingress controller, that is the brain that lets it work, or which is responsible for working of it. So it is same as that. Instead of Kubernetes already doing the heavy lifting of creating those resources and we just access it by creating YAMLs, etc., we have to do it ourselves by creating custom resource definition, then custom resource, and then custom controller, which is the brain that manages it. So custom resource is an object or a service or a resource, and it is a structured data, usually in a YAML format, that represent specific configuration or state we want to achieve. For example, Istio, Argo CD, etc. And mechanism behind it is extending the Kubernetes API server. By default, it is limited to default resources, and we extend that API server with custom resources with respect to our needs or our applications or software or organizations need. Meaning custom resource definition is usually prepared by senior or platform engineers, and it is like an unseen process for developers or DevOps engineers, and they only access those resources created using custom resource definition. For example, if it is Istios, and DevOps engineers or developers access those custom resource definitions or those services or resources by YAML file of custom resource. So custom resource can be understood by remembering deployment file or Ingress YAML file. So this is same. Custom resource is also like a YAML file to utilize the service created by custom resource definition. Now let's understand what is custom resource definition. A custom resource definition is the blueprint or the schema for our custom resource. Kubernetes doesn't know what database object looks like until we give it a CRD. The function, it tells the Kubernetes API server, hey, from now on, if someone sends us a YAML file labeled database, it should have these specific fields like a version or storage size, and here is how we validate them. The result, once we apply a CRD, the Kubernetes API expands. We now run kubectl get databases without getting an error. So custom resource definition is the blueprint to create a custom resource and to extend Kubernetes API server. By default, there are resources offered by Kubernetes. We expand the Kubernetes API server with custom resources. For example, here we are expanding API server for database, and once we create custom resource definition file and we apply the command, we would get kubectl get databases without getting an error. And we can create custom resource definition for many services or resources, custom resources offered by various certified and verified providers. For example, there exists Istio, RBAC, and other services. We implement those or use those if we find that default resources are not enough and we need more for efficiency or stability or enhancement, etc. Now, custom controller. A custom controller by itself is just dead data. It is a record in a database that doesn't actually do anything. A custom controller is the brain or the loop of the code that makes things happen. The logic, it runs in a continuous loop called reconciliation loop. It constantly checks two things: desired state, what we wrote in our custom resource. For example, if we wrote, I want a Postgres database, and actual state is what is currently happening in the world, real world. The action would be if the controller sees a custom resource asking for a database, but no database exists, the controller executes the code to go out and build the database. So simply, custom controller is the brain that needs to be there for custom resource and custom resource definition to work. For deployment and Ingress, there exists Ingress controller and deployment controller that acts as a brain or is a brain with respect to making things work. The logic behind custom controller is that it runs a continuous loop called reconciliation loop, and it constantly checks desired state and actual state. Desired state is the state that we want and we wrote in the custom resource, and actual state is what is currently happening. The action would be if controller sees a custom resource asking for a database but no database exists, the controller executes the code to go out and build that database. Custom controller typically involves using Go programming language to prepare it. Now, summary would be component, that is CRD. The role of CRD is the setup. Real world example would be to define temperature setting as a valid concept. Component, custom resource, the role would be the input. We physically turning the dial to 22 degrees. Controller would do the action of noticing that it is cold and turning that into the temperature we defined in the custom resource. So CRD would be the concept or the service we create, and CR would be what we actually want from that CRD or to access that custom resource by specifying details of what we want to achieve. With respect to this example, it is 22 degrees, and controller is the actual brain that lets it execute and work. The topic is understanding ConfigMap and secrets, and we will also discuss Kubernetes Gateway API, its benefits, drawbacks of Ingress, and everything in between. But first, let's understand what is a config map. A config map is an API object used to store non-confidential data in key value pairs. We can think of it as a centralized configuration file that our application can read at runtime. This is best for environment variables, port numbers, file path, or entire configuration files like nginx.config. Why do we use it? It allows us to keep our container images clean. We can use the same image for development, staging, and production simply by swapping the config map attached to it. Both config map and secrets have same purpose of storing data, but config map is to store non-confidential data, whereas secrets is to store confidential data. What do we mean by non-confidential data? Non-confidential data is the data that is simply non-confidential. For example, that is environment variables, port numbers, file paths, configuration files that is stored in key value pairs. Simply, it is like a centralized configuration file that the application can read at runtime, which allows us to keep the container image clean, and we can use the same image for development, staging, and production by simply swapping the configuration map or config map attached to it. In short, config map is to store non-confidential data in key value pairs. Now, what is secret? A secret is a similar concept to config map, but it is specifically designed to hold sensitive information, which is best for passwords, OAuth tokens, SSH keys, and database credentials. The difference: while config maps are stored in plain text, secrets are stored in base64 encoded format. We can note that base64 is encoding, not encryption. For true security, we should enable encryption at rest in our cluster at etcd storage. So as I mentioned, secret is a similar concept to config map, but is to store confidential information or sensitive information, that is like passwords, tokens, SSH keys, database credentials. Config map can store data in plain text or is stored in plain text, whereas secrets are stored in base64 encoded format, so it is difficult or it is somewhat confusing to decode, which is better than plain text. Which is to note that base64 is not encryption. For true security, we should be implementing encryption of the cluster storage at etcd. Summary would be: the feature purpose of config map, that is configuration settings, whereas for secret it is sensitive or confidential data. For storage in config map, it is plain text, that is key value. For secret, it is base64 encoded. Example data: for config map it is log level debug, whereas for secret it is TB password, base64 encoded password. Size limit: for config map it is 1 MB, for secret it is 1 MB. So that was about config map and secrets. Now we will understand what is Kubernetes Gateway API, drawbacks of Ingress, and how Kubernetes Gateway API is more efficient and solves issues that were happening in Ingress. The core purpose: the Gateway API's purpose is provide a standardized, role-oriented and expressive way to manage service networking. Instead of single all-in-one configuration file like Ingress, it breaks networking down into distinct pieces that match how real companies operate. This ensures that a developer can change an application route without accidentally breaking the entire cluster's load balancer settings. So first, we must know that Ingress is not bad or it is not too efficient, but we can understand Kubernetes Gateway API as an upgrade or a level up to the Ingress simply by enhancing or fixing what Ingress was lacking. So Ingress in itself is a major success in solving a lot of issues that were already present, whereas Kubernetes Gateway API is a level up or an upgrade to what Ingress was offering and its drawbacks. That being said, the core of Kubernetes Gateway API is to provide standardized, role-oriented and expressive way to manage service networking. Where Ingress was all-in-one configuration file, Kubernetes Gateway API breaks into distinct pieces that match how real companies operate. That ensures developer can change application route without accidentally breaking entire cluster's load balancer settings, which is operated by platform engineers or senior to the developer. Now let's understand what is critical drawbacks of Ingress and how Gateway API solves them. A, that is the annotation hell, lack of standardization. The problem: Ingress only supports very basic routing. For anything advanced like URL rewriting, header-based routing, or rate limiting, we had to use annotations. For example, nginx.ingress.kubernetes.io/rewrite target. This is for one annotation. If we had to use many annotations, that would look a lot larger. The impact: these annotations are vendor specific. If we move from Nginx to AWS, ALB or Istio, our configuration would break completely because they use different annotations. The solution: Gateway API build these features into the core specifications. Features like header-based matching or traffic splitting, canary deployments are now native and portable across different providers. So the problem in Ingress is that it supports very basic routing. For something advanced or more enhanced production features like URL rewriting, header-based routing or rate limiting, although it is supported, but we had to use annotations like this syntax, which is really large or long. Also, these annotations were vendor specific. If we moved from Nginx to AWS ALB or Istio or to different vendors, that configuration would break completely because they use different annotations. Solution is that Gateway API builds these features into their core specification. Features like these header-based matching, traffic splitting, that is canary deployments, are now native and portable across different providers. B, that is the monolithic configuration, that is role conflict. The problem: an Ingress resource combines infrastructure, that is TLS certifications, load balancer settings with application logic, that is URL paths. The impact: a developer who just wants to add new /API/v2 path needs permission to edit the entire Ingress object, potentially giving them power to accidentally delete a TLS certificate or change a global load balancer setting. The solution: it introduces role-based separation. Gateway class managed by infrastructure providers, that is the AWS load balancer type. Gateway that is managed by cluster operators. For example, we define the port 443 listener and TLS certifications. HTTP route managed by developers, for example route /app to my service. The problem is that Ingress is monolithic in nature. For example, the Ingress resource combines infrastructure with application logic. So that would mean a developer who just wants to update something simple or not so complex would need permissions to edit the entire Ingress object. Potentially that would give them power to accidentally delete a TLS certificate or services or task managed by platform engineers. In short, a developer who just needs to manage simple tasks in an Ingress object would have all the permissions to potentially manipulate or accidentally manipulate those details that is actually needs to be managed by platform engineers or senior DevOps engineers. So the solution for this is that Kubernetes Gateway API introduces role-based separation. For example, Gateway class would be managed by the upper or the senior platform engineers, and they would manage all these like role balancer type, and Gateway is also managed by seniors, and HTTP route would be managed by developers. So it would provide role-based separation. So every role would be redirected to certain separation. They would manage only that and does not accidentally manipulate or change other resources. C, that is no cross namespace support. The problem: Ingress usually requires the Ingress resource and the service to be in the same namespace. The impact: this makes it extremely difficult to manage a shared gateway where one central load balancer serves multiple teams in different namespaces. The solution: Gateway API allows cross namespace routing, and HTTP route in namespace A can securely attach itself to a gateway in namespace B using reference grant for validation. So problem is Ingress usually require Ingress resource and service to be in the same namespace, meaning other namespace cannot be communicated, which makes it extremely difficult to manage shared gateway where one central load balancer serves multiple teams in different namespaces. Basically, Ingress in namespace A cannot communicate to the services in namespace B. So we would think that why did Kubernetes build this in that way? The main reason is security. It was intentional choice to prevent traffic hijacking. For example, if any developer could create an Ingress in their own namespace that points to a service in another namespace, they could accidentally or maliciously steal the traffic. And by forcing Ingress and service to be in the same room or in the single namespace, Kubernetes ensures that whoever is configuring the door, that is the Ingress, also has the permissions to manage the room or the namespace. So Gateway API solves this problem that Ingress had by allowing cross namespace routing. For example, a HTTP route in namespace A can securely attach itself to gateway in namespace B using reference grant for validation. Reference grant is like a permission that would allow this to work. D, limited protocol support. The problem: Ingress was designed strictly for HTTP or HTTPS. The impact: if we needed to route TCP, UDP or gRPC traffic, we often had to bypass Ingress entirely or use even more complex vendor-specific hacks. The solution: Gateway API is protocol agnostic. It includes specific resources like TCP route, UDP route, TLS route, gRPC route right out of the box. The problem in Ingress was it was strictly designed for HTTP or HTTPS routing. Now, if we needed to route with other protocols, we needed like TCP, UDP or gRPC traffic, we often had to bypass Ingress entirely or use even more complex vendor-specific hacks. The solution is that Gateway API protocol includes specific resources like these right out of the box, meaning it supports other protocols for routing. So that was about drawbacks of Ingress and how Gateway API Kubernetes solves this. Now let's understand advanced traffic control, which is like the benefits of Kubernetes Gateway API. First is header-based matching, that is request routing. In a standard Ingress, routing is usually limited to host, that is example.com, and path/API. Gateway API allows us to route traffic based on any part of the HTTP request. The use case would be A or B testing or internal beta testing. How it works? We can tell the Gateway API to route traffic to our experimental service only if a specific header is present. For example, X user type or beta tester. The logic would be if the header version is V2, route to V2 service, otherwise route to V1 service. In standard Ingress, routing was limited to host or path, but in Gateway API, it allows us to route traffic based on any part of the HTTP request, which is basically used for A or B testing or internal beta testing. We can tell Gateway to route traffic to experimental services or features if the specific header is present. For example, X user type, which would be like a VIP user or a standard user. That can be anything subjective to the developers that would route traffic to the beta tester. So the logic would look like if the header version, that is V2, that would route to the V2 service, otherwise it would route to the V1 service. Second is traffic weighting or canary deployments. Weighting allows us to split traffic between different versions of a service based on a percentage. The use case blue-green or canary deployments. The logic: instead of switching 100% of our users to new version and risking a total crash, we can define a split. For example, configuration would look like service A, that is stable, would have weight 90, and service V, which is new, would have the weight 10. As we gain confidence in the new version, we incrementally increase the weight of service V without ever changing the DNS or the load balancer IP. So I think it is simple. If there exists a new version, we would not want to risk total crash, so we would be splitting the traffic with respect to users. 90% would be on the service A, that is stable, and 10% would be, that is like a weight 10, would be in the new version. It is to test or to gain confidence in the new version. If we feel that the new version is secure and we gain confidence, we can incrementally increase the weight of service B or completely move traffic to the service B and make it 100% without ever changing the DNS or the load balancer IP. Third is filters, that is request or response manipulation. Filters allows us to modify the traffic as it passes through the gateway before it even touches application code. This keeps our application logic clean. There are three primary types of filters. A, that is request header modifier. The purpose: it is to add, set or remove headers before the request reaches the backend. For example, automatically adding a X forwarded client IP header or a stripping a set cookie header for security. By default, the traffic that we receive in the backend is messy, or it misses key piece of information that a backend service needs to do their job. So the request header modifier would add, set or remove headers before the request reaches the backend. So before the request reaches the backend, we can add somewhat like a rule for us to know specific information before it reaches the backend. For set, it would look like setting the traffic with respect to the users. That is, if the users are gold member, so the request would treat that user accordingly, and if the user is standard, the set rule would treat that user accordingly to the standard. And for remove, simply it is to manage security and ensure that we follow compliance rules. If the traffic that is to be received in the backend contains sensitive information, that is passwords, social security number, etc., this rule, that is remove, would scribble over that sensitive information so that the backend inside cannot see it. So it keeps the data secure and prevents the backend from seeing things it shouldn't. So you would think, if the backend is owned by us, and why do we need to remove such sensitive information reaching the backend? First, a malicious user can still fake the header For user admin, that is true, and if the backend treats that header as true, it can be hacked to have sensitive information. And many backends or tools crash or behave weirdly if they receive unexpected headers or huge amount of cookie data. So this gateway acts as a filter, so the application only receives exactly what it expects. And also there is the privacy issue or GDPR or compliance. We would want to strip out tracking cookies or personal info at the front door, so the internal logs and database never accidentally store sensitive data that they don't need. Now B, that is request mirroring, that is shadowing. Purpose: this is a silent filter. It sends a copy of live production traffic to a test service. The impact: we can see how our new version handles real world load and data without the test services response ever reaching the actual user. The user only sees the response from the stable version. So request mirroring is a silent filter. It sends copy of the live production traffic to a test service or a beta service or a new version, so we can see how the new version handles that real world load and data without the test service or the version service response ever reaching that actual user. The user only sees the response from the stable version. C, that is URL rewrite or redirect. The purpose is to change the path of the request on the fly. For example, a user request that is example.com/shop, which is https example.com/shop, but the filter silently rewrites it to /version3/commerce/shop before sending it to the backend pod. This is when we have updated the version of, for example, that is /shop to the version 3. Instead of changing the folder structure and redeploying the code, it simply rewrites the new version path to the existing path. So if example.com/shop is a older version or is simply version 2, and we have new version that is version 3 that has the path version 3/commerce/shop, instead of changing the folders and redeploying the application, we simply redirect that path to the existing path without needing to redeploy and change the folders, etc. So that was about advanced traffic control and its features provided by Kubernetes Gateway API. Now let's understand the summary of it. Feature that is primary focus. For Ingress, it is simple HTTPS routing, whereas for Gateway API, it supports layer 4 TCP or UDP and layer 7 that is HTTP or gRPC. Feature that is resource model. For Ingress, it is single resource Ingress, whereas for Gateway API, it is modular gateway class gateway routes. Feature that is portability. For Ingress, it is low. It relies on vendor annotations, whereas for Gateway API, it is high. It standardizes across different controllers. Feature that is role separation. In Ingress, it is none. Everyone touches the same file and can manipulate that Ingress file, whereas for Gateway API, it is explicit infrastructure versus platform versus developer. Feature that is traffic control. For Ingress, it is basic path or host, whereas for Gateway API, it is advanced, that is header matching, weighting, filters. The topic is monitoring with visualization. A 3-tier Node.js Express application, that is resume matcher, deployed on Kubernetes via Minikube. In this tutorial, I will show you strategies and steps I implemented to perform this monitoring. But before we begin, I am Kaif. I was previously a recruitment professional, now learning DevOps from zero. This is part of my transition series. If this resonates with you, stick around. So the mental model for monitoring this application is to first monitor total healthy targets, CPU, memory requests, and database connection, which is like the Postgres exporter. To perform all this, the first step was to form Minikube. Start with memory flag 5 GB 600 MB and CPUs of 4. I performed this command inside the root folder of my application. After Minikube was up and running, I performed Helm install monitoring Prometheus community and this command, and also created namespace monitoring, and it was successfully created with installation of Prometheus. By the way, monitoring namespace or namespace simply means we isolate an environment for a specific task. In this case, for monitoring purposes, I have isolated a namespace just for monitoring. After installing Prometheus and creating the namespace monitoring, I checked it with kubectl get pods -n, that is namespace monitoring, which shows all the required pods for monitoring with respect to Prometheus are up and running. That includes alert manager, operator, state metrics, node exporter, and monitoring kube Prometheus, also Grafana monitoring. After these pods were running in the namespace monitoring, I wanted to have metrics with respect to Prometheus in the path that is /metrics on the local host, or when the application would be deployed and running and I would perform /metrics. I wanted to see metrics with respect to Prometheus scraping. To do so, I first installed prom client by npm install, so that would help in monitoring and providing that dependencies for it. Then I created service monitor.yaml, and this is a YAML file. It has a label for app resume matcher and HTTP port with path that is /metrics and 30 seconds of interval. Then I updated server.js by adding service monitor and /metrics path. After this, I ran the service resume matcher, that was my application, by performing minikube service space the service name, which is resume matcher service. It was exposed in the NodePort with path 127.0.0.1.59484. So as you can see, the application is running on this port. Now to check /metrics, I performed /metrics path on these ports. So metrics were visible and available, and service monitoring was successfully running to provide these results. Now for Prometheus dashboard or UI for metrics, I performed Helm repo add Ingress Nginx and created Ingress Nginx namespace to run Prometheus with Ingress. Then I created Prometheus ingress.yaml, and this Ingress is for the service name monitoring kube Prometheus, which in earlier images we saw one of the pods with this name, that was the service, and the port is 9090. And to run this Prometheus thing in my system, I had to add this inside the host, which is inside Windows System 32, inside drivers, inside etc, inside host of it. I added the port 127.0.0.1 space Prometheus dot local, which would mean after doing so, if I would perform http://prometheus.local, Prometheus would be up and running with that domain is specified in the host with that port. Then I performed kubectl apply -f Prometheus ingress YAML, and it successfully created that ingress. Then I checked kubectl get ingress -n namespace monitoring Prometheus ingress. It was successful with the class nginx host prometheus.local, which we specified on the port 80. Now to check the services, I performed kubectl get services svc -n namespace monitoring, and it showed me the services that were running, which includes the Prometheus service we specified, that is monitoring kube Prometheus and other as well. As we kind of created load balancer type thing by creating a domain that was prometheus.local, and we specified that inside drivers of our system, which mimics load balancer things. And to run such type of services which we have created, we must perform the command minikube kernel, not usual port forwarding, as by default these services of type load balancer get stuck in pending because it doesn't have cloud balancer native support for load balancing. By performing minikube kernel, it creates network route to the cluster's internal service network, that is CIDR, and it dynamically updates service status, so we can access our application directly using the local host or the assigned IP address. So simply it is because we added prometheus.local and specified that with the ports inside the host, so it mimics the load balancer. To run such type of ports and service, we must perform minikube tunnel, so we are using it. And it successfully created that tunnel. Now the prometheus.local is active. That has the host http://prometheus.local, and it shows the services that are up, that means that are running, is healthy. So that was about Prometheus as it is successfully running. Now we have to perform Grafana for visualization of those metrics. But before we do that, we must know that we have already created service for Grafana and it was already visible in our SVC and in the namespace monitoring. As you can see, we have specified Prometheus service monitor in the service YAML file for Prometheus metrics on path metrics, which we have seen in the localhost application. So Prometheus is active on prometheus.local and as well as on /metrics path. So both of them has Prometheus metrics available. And now for Grafana, the command is kubectl port forward -n namespace monitoring service /monitoring Grafana with the ports 3000 mapped 8 and it is running. Now you might be wondering how come we have service monitoring Grafana already present while we have not created its service inside a service YAML file where we have only specified Prometheus as a service. It is because we have performed Helm install kube-prometheus tag, which means it has Grafana included by default after it was successfully handling connection at port 3000. Now it was to generate password or logging in inside the Grafana. The command for it is kubectl get secret monitoring Grafana -n namespace monitoring, and this command with base 64 pipe and echo statement to give us the result of the password which I have hidden. After this, I head back into the local host 3000 for Grafana UI or login in. I added the email or username admin and the password which was generated and I performed the login. It was successful and I was inside the Grafana. Now to create visualization of the metrics, I went into the connections tab and clicked data sources and selected Prometheus as a source of data. After this, Grafana automatically selected the Prometheus service that was running, which was monitoring kube-prometheus.monitor with the port 9090. It is simply where the Prometheus is actually running in the host or in the ports. So it automatically recognizes those ports and where the Prometheus is running, which is default. So I clicked inside it and I scrolled down and clicked test and it was successfully queried with the Prometheus API. How it was to visualize this data by building a dashboard from scratch. To do so, I performed or I added the queries and I created the panels. For the first panel, I performed the query sum up to show total healthy targets, and for the second panel dashboard, I performed rate container CPU usage with respect to seconds total for the time 5 minutes. Second query in that same graph was container memory usage with respect to bytes. The third query in that same bar graph was rate HTTP request total in 1 minute time frame. And for the third panel or the third dashboard inside the Grafana, it was for memory usage with query container memory usage with respect to bytes, request per second rate, which was HTTPS request total 1 minute time, PG stat activity count for database connections, which is Postgres. So these are the exact queries I entered and I created these panels with these results, which I am showing you right now. So these were the results for total healthy target. It shows 14, and second is the bar graph for CPUs and everything, and it is the third for the pie chart. So the topic is Kubernetes cluster upgrade. Why we upgrade Kubernetes cluster, mandatory architectural prerequisites of Kubernetes cluster upgrade, and step-by-step upgrade process of self-managed Kubernetes cluster versus EKS in theory. Also, we will discuss managed services versus self-managed clusters. What is the difference between them? But before we begin, my name is Kaif Mohammad Khan. I'm a recruiter in the past. Now I've moved into DevOps from scratch. This is part of my transition series. If you are making the same switch, stick around. A Kubernetes cluster upgrade is the methodical process of updating a cluster's core system components from an older version to a newer version. Example, that is from version 1.35 to 1.36. Because Kubernetes uses a distributed client-server architecture, upgrades cannot be done all at once. They must be executed in a precise layered sequence to keep applications online and prevent version incompatibilities from breaking cluster communication. So Kubernetes cluster upgrade is a methodical process of updating clusters, code, system components from previous version to the latest version of it. Because Kubernetes is a distributed client server architecture, the upgrades cannot be done all at once. It must be executed in precise layered sequence so that the applications are up and running and the updates of the versions does not cause breaking in the cluster communication due to the version incompatibility. So why we upgrade the Kubernetes cluster? Let's understand in the sense of business and technical triggers. The 1-year support window. The Kubernetes community only maintains the 3 most recent minor versions. Each version receives security patches and critical bug fixes for roughly 12 months. Running an unsupported version leaves the cluster exposed to unpatched vulnerabilities. API deprecations. Internal features and configurations like Ingress or deployment schemas transition over time from version 1 beta 1 to version 1. Upgrades ensure the environment remains aligned with modern code standards before obsolete APIs are completely removed from the binaries. Feature availability. Minor releases bring core structural upgrades such as native CG group version 2, resource handling, scheduling performance optimizations, and enhanced encryption mechanism. First, why we upgrade Kubernetes cluster? It is because Kubernetes community only maintains recent minor 3 versions of the current update. Each version receives security patches and critical bug fixes for roughly 12 months. Meaning, if you are in the Kubernetes latest version right now, it would take nearly 1 year for it to get maintained by Kubernetes community, and after it would be unsupported version that leaves the cluster exposed to unpatched vulnerabilities. Second is internal features and configuration such as Ingress or deployment or other schemas transition over time, that is from, for example, version 1 beta 1 to version 1. So upgrading it ensures the environment remains aligned with modern code standards before obsolete APIs are completely removed from the binaries. Minor releases or releases in the Kubernetes for upgrade brings core structural upgrades such as native CG groups, version 2 resource handling, scheduling performance optimizations, and enhanced encryption mechanisms. So each update or upgrade that the community of the Kubernetes provide brings core structural upgrades like native resource handling, scheduling performance optimization, and enhanced encryption mechanisms. Now, mandatory architectural prerequisites of grading Kubernetes cluster. Before altering a cluster, we must validate that the components conform the official Kubernetes versions queue policy. If this mathematical versions constraints are violated during planning, internal components will reject the communication, breaking the cluster. So, Kubernetes cluster upgrade has prerequisites, meaning before we even upgrade, there must be certain standards or certain rules or certain SOPs you must follow in order to have successful upgrade of Kubernetes cluster. If we miss out on such steps, there exists a strong possibility that internal components will reject communication, eventually breaking the cluster from working. So it must conform or follow to the official Kubernetes versions queue policies. The first is the control plane rules, that is Kube API server. The Kube API server acts as the definitive version anchor for the entire cluster. In high availability HA environments with multiple master nodes, our active Kube API server instances can differ by a maximum of 1 minor version. All the other control plane components, Kube controller manager, Kube scheduler, must match or be at most 1 minor version older than our newest Kube API server. They can never be newer. This means that in high availability environments that has multiple master nodes, our Kube API server instances can only differ by maximum of 1 minor version. Meaning if Kube API server is at version 3, high availability HA environments with multiple master nodes must be at least at version 2, not version 1. And other components in control plane like Kube controller manager, Kube scheduler must match or be at most 1 minor version older than our newest Kube API server. Meaning if the newest Kube API server is at version 3, it must be at least or at most 1 minor version older, that is version 2. It can't be less than that. That is the node rules kubelet and kube-proxy. The -3 boundary. The local agent on worker nodes kubelet can be up to 3 minor versions older than the kube API server. The overskew trap. Worker nodes can never run a version newer than the Kube API server. If we have a control plane at version 1.34 and we attempt to connect a node upgraded to version 1.35, it will be rejected. Upstream core constraints. The administrative CLI tools kubelet is supported only with one minor version +/-1 of Kube API server. Now for kubelet, it can be up to 3 minor versions older. Meaning if Kube API server is at version 5, kubelet can be at version 2, not less than that, and worker nodes can never run a version new or latest than the Kube API server. For example, if the control plane is at version 1.34 and we attempt to connect a node that is upgraded to version 1.35, it will be rejected. And the administrative CLI tool, that is the kubelet, only supports one minor version than the Kube API server. If Kube API server is version 5, it must be at least version 4, not less than that. So local agent on worker nodes kubelet can be up to 3 minor versions older than the Kube API server, and worker nodes can never run a version latest or new than the Kube API server, and administrative CLI tool kubelet supports only one minor version than Kube API server. C. System and environment readiness check. Single version jump only. You cannot skip minor versions, for example moving straight from version 1.33 to 1.35, that is prohibited. You must upgrade sequentially, that is version 1.33 to version 1.34 to version 1.35. etcd state backup. We must take an explicit standalone snapshot of the etcd distributed database. If the control plane binaries corrupt data during database schema migration, this file is our only path to recovery. Disable swap memory. Ensure swap remains completely disabled across all node operating systems, as kubelet binaries will fail to initialize if swap space is active. Container runtime interface, that is CRI. We must verify that the underlying runtime container engine, for example containerd or Creo, is validated for compatibility against the target Kubernetes release version. So we cannot skip minor versions, meaning we cannot go from 1.33 version and directly to 1.35 version. We must upgrade sequentially, that is 1.33 to 1.34, then to 1.35. For extra safety of backup, we must take standalone snapshot of etc distribution database. So if the control plane binaries corrupt the data during database schema migration, this file is the only path to recovery or to recover those data in the etcd. Although in the newest versions of Kubernetes, swap memory being active or disabled doesn't affect the upgrade process, meaning it will not affect the binaries to initialize. But for our convenience or to be on the safe side, we can completely disable swap memory across all node operating systems to avoid kubelet binaries to fail to initialize if the swap space is active. Also, we must verify that underlying runtime container engine, that is Creo or containerd, is validated and it is compatible against the newer version or the latest version we are targeting to upgrade for. So that was about the prerequisites of Kubernetes cluster upgrade or update. Now let's understand the step-by-step upgrade process. First is self-managed. Self-managed here simply means we are the owner and we manage all the services and we are responsible for its working and maintenance. Comparing it with the EKS or other cloud provider services. Self-managed means we are managing our own cluster by ourselves and we are building it. So the upgrade flow strictly is from top to bottom, that is control plane nodes first, then worker nodes. For this we upgrade the tooling and target verification, that is the step 1 admin system. and hold and upgrade the package manager tools kube-adm on the primary control plane host to the precise target patch version. We must run the kube-adm upgrade plan to execute automated pre-flight checks that verify cluster health and fetch available target components. So step 1 is admin system, where we aim to update the kube-adm, which is the package manager tools. We upgrade that on the primary control plane host to the precise target version we are aiming for. To do this, we run the command kube-adm upgrade plan to execute that automated pre-flight checks that verify cluster health and fetch available target components. Step 2, that is in the control plane node 1, we upgrade the primary control plane. We execute the command kube-adm upgrade apply version which we are aiming for. This pulls the target version images and automatically updates the static pod manifest for the core system components kube API server, kube controller manager, kube scheduler. This means that we apply the command kube-adm upgrade apply with the version we are aiming for. This pulls the target versions images and automatically updates the static pod manifest for the core system components, that is kube API server, kube controller manager and kube scheduler, meaning it upgrades or updates it. Now as we updated control plane node 1, in step 3 we aim for upgrading or updating highly available nodes, meaning upgrading secondary control plane instances. For clusters running multiple master hosts, we log into the remaining control plane nodes one by one and execute kube-adm upgrade node. This updates local configuration without reinitializing the cluster data pool. So as we did the update or upgrade in the primary control plane node 1, in the step 2 we have applied the command kube-adm upgrade apply with that version. So we do this command for single primary control plane node 1, and with the rest of the other nodes present in that same control plane, we don't need or we don't perform that same command. Instead, we perform the command that is kube-adm upgrade node, which would mean that this command would upgrade that to the upgraded version which we did for the initial first node. We do this command for each nodes or instances in the control plane present. Now step 4 is master node agents, that is to update local control plane kubelets. To do this, we drain the master nodes, we update their host level kubelet and kubelet package binaries to match the new version. We restart the system service via systemctl and uncordon the nodes. So here the drain of the master nodes and then we updating it means that updates or upgrades cannot happen when there is an active application running on that nodes. So we can either create a fresh node and perform update on it, or either we can drain or evict that node to perform the update or upgrade by performing the command kube-adm upgrade node. Now for step 5, we do the same by draining the worker nodes by this command. This safely evicts active application pods that triggers the scheduler to recreate them on other healthy nodes to maintain zero application downtime. The purpose is same. The upgrade or update cannot be done when an application is running or when the application is running in the pod. To do that, we drain or empty that pod and we perform the upgrade on it, or either we can create a new node and perform the upgrade or update. After this, there is step 6, where we upgrade the worker node components. We log into the cleared worker node and we upgrade it packages by performing kube-adm package, run kube-adm upgrade node, and we upgrade the host operating systems kubelet and kube-proxy packages, and then we restart the services to initialize the updated node daemon. So after draining and evicting the pods and emptying the nodes, we perform the command to upgrade the kube-adm package, that is run kube-adm upgrade node. It upgrades host operating systems kubelet and kube-proxy packages, and after it is done, we restart the services to initialize the updated node daemon. After step 6 is done, we perform step 7, that is the re-entry of restoring the worker node to service. We perform kubectl uncordon with the node name to mark the node as scheduling ready. This ensures that the scheduler distributes the workload back into the upgraded or updated host which we have done, and we repeat the step 5 through 7 iteratively across all remaining worker nodes in the cluster infrastructure. So we perform the drain by emptying the node so it is empty and it is fresh, and it mimics that it is a new node for making the upgrade successful. If the node has application running, the upgrade or update is affected or is manipulated and it cannot be successful. So we drain it. Then we log into the cleared or the drained worker node or the node, and then we perform the run kubeadm upgrade node to upgrade its kubeadm package, which upgrades its host operating system's kubelet and kube-proxy packages. Then we restart the services to initialize the updated node daemon, and then we perform kubectl uncordon with the node name to mark it as scheduling ready, meaning to make it ready. So the scheduler will distribute the workload across and back to the upgraded or the new host, and we repeat the steps on other nodes in the cluster infrastructure. So that was about self-managed clusters. Now for managed, that is EKS in AWS or other service providers. Step 1 is EKS control plane upgrade. AWS hosts the control plane components, that is Kube API server, etcd, Kube scheduler inside an isolated AWS managed VPC. Our application continue to run undisturbed while AWS swaps these underlying servers out in the background. So AWS is a cloud provider and it hosts the control plane components, that is Kube API server, etcd, Kube scheduler inside an isolated AWS managed virtual private cloud, that is VPC, and our applications continue to run undisturbed while AWS does the heavy lifting of swapping these underlying servers out in the background. First is pre-flight validation. We scan for all running application deployments to ensure they are not using APIs deprecated in the target version. Then we perform or to trigger the API update. We execute the upgrade request using AWS CLI or Terraform. We can only move up by one minor version at a time, which is like the prerequisite step we discussed. For example, if it is 1.31, we must do it 1.32, not 1.33. And the command to trigger the master control plane software upgrade is AWS EKS update cluster version with the region US East 1. We can do it with other which you have specified, and the flag name, that is production cluster, or it can be anything which you have named, and the flag is Kubernetes version that we are targeting 1.32 in this case. Then blue or green follower. AWS spawns fresh control plane nodes running version 1.32 alongside our current nodes, synchronizes the database, transparently reroutes internal cluster traffic to the new instances, and removes the old nodes. So in this, AWS spawns fresh control plane nodes that runs with the version which we have specified for the upgrade, that is 1.32, alongside our previous old version nodes, meaning both of them would be present. Then it synchronizes all the database and information, and it transparently reroutes the traffic to the new instance with the new version of 1.32, and it removes the old nodes. It happens quickly in the background and it almost gets unnoticed, but this is what happens in the background. And next is verification. The cluster transitions out of the updating state, then we verify the readiness. The command for checking or the verification is AWS EKS describe cluster with the flag with the region US East 1 in this case, and flag name with the production cluster name. It can be anything which you have named. And the next flag is query, that is quotes cluster dot status quotes. So we wait until it returns active as the status. Now for step 2, managed node group upgrade, that is data plane. Once the control plane status changes to active, we upgrade our worker nodes pool. EKS managed node groups automate this via a rolling search upgrade strategy to maintain zero application downtime. So we can understand control plane as the root folder, and other aspects, that is worker nodes or master nodes, are the sub-root or subfolders inside it. So in that case, we first need to update or upgrade the control plane. We have done that in the step 1. So now Now after we observe status change to active, then we can upgrade the worker nodes pool by this command, that is AWS EKS update node group version with flag of region US East 1 cluster name flag with production cluster flag node group name, that is primary node pool, we can name it anything, and the target version, that is Kubernetes version 1.32. So EKS managed node group automates this via rolling search upgrade strategy. This maintains zero application downtime. This is the command to execute it, or else there is the UI thing you can do in the interface of AWS as well by performing the upgrade. So we perform this after we have checked the status to active. Then launch upgraded instances, that is infrastructure scale up. The underlying AWS autoscaling group provisions a new EC2 instance built with the newest pre-baked EKS optimized AMI matching the target version. So after we successfully perform the step 2, the AWS autoscaling group provisions a new EC2 instance with the newest pre-baked EKS optimized AMI matching the target version which we have specified. Then for the second thing, cordon and drain old nodes, which is graceful pod relocation. Once the new nodes are registered as ready, meaning in the new instance with the latest or targeted optimized AMI matching version, once it is registered as ready, AWS will automatically trigger the cluster drain on old node, shifting pods smoothly onto the new hardware. Third is termination or terminating the legacy instances, which is resource reclamation. When the old worker node instance is entirely empty, AWS safely terminates it. This loop repeats one by one until our entire fleet is refreshed. So there would be new node creation, or that would be marked as ready, which would trigger AWS to perform drain on old nodes with old versions, then shifting those into the new upgraded nodes. And when the old instances or nodes are empty, AWS will safely terminate it. This loop will continue until our entire fleet is refreshed. Now step 3, that is EKS managed add-ons upgrade. System critical utilities running inside the cluster must be updated immediately after the node pools catch up. Upgrading them out of order can disrupt pod-to-pod networking or DNS resolution. So after the step 2 is done, where node pools are upgraded or updated and old ones are drained and deleted, some critical utilities running inside the cluster must also be updated immediately, meaning those are mandatory add-on upgrade lifecycle, which is in this order. First is VPC CNI, that is networking plugin. Second is core DNS, which is internal cluster DNS. Third is kube-proxy, network routing rules. And if we upgrade them out of the order, that can disrupt pod-to-pod networking or DNS resolutions. So first, we retrieve target patch versions. We query the AWS API to locate the valid version strings specifically compatible with our newest or the new cluster version. The command for it is AWS EKS describe add-on versions with the flag region and the region name US East 1, flag with the version Kubernetes 1.32 and the flag add-on name code DNS, and the query flag with add-on bracket dot add-on versions bracket dot add-on version. This command would look up the matching add-on image versions available in our specific region. Then second, we perform execute add-on upgrades to update our cluster components sequentially using the appropriate version strings. That is the flag resolve conflicts reserve flag, which ensures any custom configuration adjustment which we have done to the system deployments remain intact. The command is AWS EKS update add-on flag with the region cluster name flag with the production cluster name, add-on name flag with its name, that is the add-on VPN CNI, add-on version flag with the version, for example version 1.19.0, EKS build 0.1, flag resolve conflicts reserved. So the preserve flag ensures any custom configurations which we have made to the system deployments remain intact. So we perform this command changing VPN CNI to core DNS and its add-on version, and same for kube-proxy with add-on name kube-proxy and its add-on version. So after the add-ons are upgraded, we verify it. So verification confirms that our platform add-ons successfully update and converge back into a stable state. We verify that all components have converged back to an active state by this command: AWS EKS list add-ons with the flag region US East 1 flag cluster name production cluster flag output that is stable. So we check the status if it is active not. So that was about step-by-step process of cluster upgrade. First we have discussed for self-managed and then for EKS, that is AWS cloud provider. Other cloud providers would have some different commands. Now finally we will discuss what is the difference between managed services versus self-managed clusters. We must know that operational workload changes dramatically depending on where our cluster is located, meaning feature or responsibility of control plane lifecycle. Self-managed kubeadm or bare metal, it is manual. We execute all system package upgrades, image pulls and master configuration adjustments. Whereas for managed AWS EKS, Google GKE or Azure AKS, it is automated. The cloud vendor performs rolling upgrades of the control plane nodes using a single console click or API call. So as I mentioned before, like in manual or self-managed nodes, we perform all the upgrades manually, as we are claiming to be the owner or isolated ownership of that cluster. That can be bare metal. Whereas for managed AWS EKS or other providers, it is automated by single click or API call. For etcd management in self-managed bare metal, it is manual. We handle snapshot, storage limits and database schema compatibility checks. Whereas for managed AWS EKS, Google GKE or Azure AKS, it is abstracted, fully handled by the cloud platform. Users have no direct access to etcd. Now for API auditing in self-managed, it is manual. We must check and fix deprecated manifest using tools like Pluto or Kubent. Whereas for managed AWS EKS or other providers, it is shared. The provider alerts you via dashboard about deprecated APIs in use before letting us upgrade. Work on node upgrades. In self-managed, it is manual. We handle all the individual operating system package upgrades, trains and uncordon processes. Whereas in managed AWS EKS or other providers, it is semi-automated, meaning we trigger a rolling update of a node pool and the cloud orchestration automatically brings up new instances, drains old ones and tears them down. So in short, for self-managed, we manage all the heavy lifting, whereas for managed, that is cloud providers, AWS or others, it is automated, shared, and we have to do less of the work. Whereas for self-managed, we have the privacy and compliance. For AWS, it is still safe and private, but it is not having such isolation which a personalized bare metal or self-managed cluster would have. If there is such industries of financial or other like military, there would be opting for self-managed clusters, which is like having a personalized data center to manage their own database or activities. Whereas for professional or business needs, it is managed or AWS EKS, which is still secure and it is much more like automated by cloud providers. The topic is understanding Kubernetes deployment strategies. We will discuss why we need Kubernetes deployment strategies, what is ruling update, what is canary deployment strategy, what is blue-green deployment strategy. First, let's understand why do we need deployment strategies. In production, we cannot simply shut down an application to upgrade it. Doing so causes downtime, meaning users see error pages. Deployment strategies solve this by defining exactly how Kubernetes transitions our application from old version, that is version 1, to new version, that is version 2. The goal is to balance the production requirements, that is zero downtime, keeping the application available to users throughout the update. Risk management, that is to test the new version before routing all user traffic to it. Third is cost efficiency, which is to limit the amount of extra server hardware required during the transition. So simply, deployment strategy is in production environments, we cannot simply shut down the application to upgrade of that application. Meaning if your application is version 1 and you have to update it to version 2 and you are thinking you would delete or shut down the application version 1 then update it to version 2, this would be a really foolish strategy because that would cause a downtime which is really costly in production environments. Meaning in companies or organizations that has applications that has real-time users in payment applications, this is a really headache. Fix that. There is a concept of deployment strategies in Kubernetes, meaning the goal is to provide zero or near zero downtime and to manage the risk and to manage the cost efficiency. Meaning if we were to not implement deployment strategy and we would shut down the application and then deploy the version 2 manually, that would at least cost 15 to 20 minutes of the downtime, which you might think is okay because if your application doesn't have traffic then it is okay. But in production environments, when there is a lot of traffic for applications or websites, this is a costly strategy. Meaning if there is Amazon, Instagram or other platforms that had 10 to 20 minutes of downtime, that would really be costly to the organization of the company. To fix this, there is a concept of deployment strategies. By default, there is rolling update strategy and there exists canary update and there exists blue-green. By implementing those strategies, we ensure that there exists zero or near zero downtime, meaning that keeps the application available to users throughout the update, meaning provides risk management, which is to test the new version before routing all users' traffic to it. So we can test the new version by providing a bit of traffic, not 100% to the new version, so we can have the feedback of those new versions. And third is cost efficiency. We limit the amount of extra server hardware required during the transition. Now first is rolling update. This is a default strategy in Kubernetes. It replaces the old version of our application with the new version gradually, one container pod at a time. How it works? Kubernetes spins up one pod of version 2. Once it is healthy and ready to accept traffic, Kubernetes terminates one pod of version 1. This repeats until all pods are running on version 2. So rolling update is a default strategy in Kubernetes. It is to replace the old version of the application with the new version gradually, one container, that is pod at a time. This works by Kubernetes spinning up single pod of version 2. Once that version 2 pod is healthy and ready to accept traffic, Kubernetes then terminates single pod of version 1 and replaces it with the version 2. This repeats until all the pods of version 1 are replaced with the healthy pods of version 2. What are the pros of this rolling update strategy? Zero downtime, meaning it is very cost effective as it only requires a tiny amount of hardware resources during the update process that is controlled by the parameters like max search. Cons or the disadvantages of this strategy. For a brief period, both version 1 and version 2 are running simultaneously. If our database schema changed significantly between versions, this can cause data mismatch issues. If a bug exists in version 2, a portion of our users will experience it immediately until the update is manually rolled back. So there are pros and cons of every strategy. In rolling update, the pros are like it is zero downtime or near zero downtime, and it is very cost effective as it doesn't require much of a hardware resource, as it requires only tiny amount of extra hardware resource during the update process, which is controlled by parameters like maximum search that is controlled by us. And cons or disadvantages are, so for a brief period, both version 1 and version 2 are running simultaneously, meaning if there is the update with respect to rolling update happening, meaning version 1 pods are replaced by version 2 one by one, and it can be a slow or fast process depending on how many pods are running. So if that database schema is changed significantly between these versions, that can cause data mismatch issues. And also, if a bug exists in version 2, a portion of our users will experience it immediately until the update is manually rolled back. So rolling update strategy is when we already know that the application is 100% healthy and 100% production ready. If we thought that the application is 100% production ready but it was not, so that would mean that the version 2 is exposed directly to the users and that users can experience that bug or that error. Rolling update strategy is to replace the existing version with the version 2. It is not like we are testing version 2 with respect to version 1. No, we are directly aiming to deploy version 2 by replacing it with version 1, one single pod at a time. So if our application had bugs in the version 2 and we did debug it before the production, that means a portion of our users will experience it immediately until the update is manually rolled back. That was about rolling update strategy. Now let's discuss what is canary deployment strategy in Kubernetes. It is named after the historic canary in a coal mine practice. This strategy exposes the new version to a tiny fraction of real users before deploying it to everyone. How it works: we deploy version 2 alongside version 1, but we configure our router or Ingress controller to send only 90% of traffic to version 1 and 10% to the version 2. DevOps teams monitor performance logs and error rates on the 10% pool. If everything looks stable, the traffic weight is steadily increased to 100%. So canary deployment strategy is where we deploy version 2 alongside version 1, but version 1 will have 90% of the traffic and version 2 will have 10% of the traffic. We configure that using router or Ingress controller. So DevOps team will monitor performance logs and error rates on that 10% of version 2 traffic pool. And if everything looks stable, the traffic weight is steadily or gradually increased to 100%, meaning if the application looks stable on the version 2, then it can be extended to 20% and 80% would be on version 1, and if it is more stable, then it is gradually increased to 30% on version 2 and 70% on version 1. It is done until there exists 0% on version 1 and 100% on version 2. Now, what are the pros and cons of canary deployment strategy? First pro is maximum safety. If a catastrophic bug exists in version 2, it only impacts a tiny fraction of our user base. Canary deployment strategy is ideal for running real-world performance tests under actual user load. Cons are managing traffic splitting requires extra infrastructure tools like a service mesh or advanced Ingress controller like Nginx or traffic, and slow rolling process as we must wait and monitor metrics at each incremental traffic stage. Canary deployment strategy is one of the most reliable strategy in production, meaning if a catastrophic bug exists in version 2, it only impacts a tiny fraction, that is 10% for example of our user base initially. So we can fix it ASAP, and it is ideal for running real world performance test under actual user load. So that 10% which we are deploying on the version 2 is of actual real world users. So it tests under actual user load, that is real world performance. Cons will be managing traffic splitting requires extra tools that is in an infrastructure, for example service mesh or advanced Ingress controller like Nginx or traffic, meaning we require a bit of hard work to make this happen. And it is also a slow rollout process as we must wait and monitor metrics at each incremental traffic stage, meaning it is a slow process as we wait and monitor metrics of each incremental traffic stage. If it is 10% and 90%, we monitor and wait to see how it works, and if it is 20 to 80, and we also do the same. We watch, wait and monitor until it is 100% on the version 2 and 0% on the version 1. That was about canary deployment strategy. Now blue-green deployment strategy in Kubernetes. This strategy cuts risk completely by running two identical isolated environments at the same time, then switching traffic instantly. How it works: blue is our active production environment running version 1. Green is an exact clone environment where we deploy version 2. While green is completely hidden from the public, our QA team or quality assurance team fully test it. Once verified, we change the configuration of our load balancer or Kubernetes service to instantly point all traffic away from blue over to the green. So blue-green deployment strategy cuts the risk completely by running two identical isolated environments at the same time, then switching the traffic instantly. Meaning blue is our active production environment of version 1, that is like the old or current version, and green will be the version version 2 or the targeted version. In this strategy of blue-green, users will only experience a single version at a time, meaning if a single user is experiencing version 1, all users will experience version 1, and if a single user is experiencing version 2, all users will experience version 2. This is not like other deployment strategies where gradually we increase the traffic from version 1 to version 2, and some users are experiencing version 1 and some users are experiencing version 2. No, in this strategy, either users will experience version 1 or either users will experience version 2, which means there will exist two environments, meaning two resources that has the same production environment as version 1. Blue will have active production environment of version 1 and green will have exact clone production environment of version 1, that is called version 2, which is an updated version of it. While green will be completely hidden from the public, the QA team fully tests that application. Once it is verified, the configuration of load balancer or Kubernetes service is changed and it is instantly pointed towards all traffic away from blue over to the green, and it can change from green to blue while changing these configuration files. That would mean there must exist two environments, that is version 1 and version 2. Even if version 1 is in use, this version 2 environment must also be active to switch it instantly, meaning it is a costly deployment strategy. So now let's understand pros and cons of blue-green deployment strategy in Kubernetes. First pro of this strategy is instantaneous switch over, means zero downtime. The switch between blue-green is instant as we already have both of the environments already running with the resources it takes. So it is an instant switch over between blue and green to blue, which means zero or almost zero downtime. Second pro is instant rollback. If something breaks immediately after the switch, we simply change the router pointing back to the blue. So as I mentioned, if something breaks in the version 2 or the green, we can instantly change the configuration files and switch to the version 1 or the blue, as both of these will have their environments already running even if it is not in use. Third pro is no version mixing. Users interact exclusively with either version 1 or version 2, never both at once. As I mentioned, there is no users that will experience version mixing, meaning if a single user within blue-green deployment strategy experiences version 1, all users will be experiencing or using version 1, and if it is version 2, all will experience version 2. It is never both at the same time, which is in the other strategies, that is canary and rolling update, where we gradually increase the traffic and we gradually deploy the pods one pod at a time. There was strong possibility and chances of both traffics existing in version 1 and version 2. Now cons of blue-green deployment strategy in Kubernetes. This is extremely expensive because we must run two full copies of our production infrastructure simultaneously. Our hardware resource utilization doubles during deployments. As mentioned, this is really expensive strategy because we are running two full copies of our production infrastructure simultaneously. That is, version 1 is our production infrastructure that is running and version 2 production infrastructure that is running. Even if we are not using version 2 or version 1, that would still mean a single version is idle and still running. So that was about the deployment strategies. Now let's compare it in this table. Metric, that is downtime. In rolling update, this is none. In canary, this is none. In blue-green, it is also done. None means is zero downtime, or it can be near zero downtime. Extra infrastructure cost in rolling update, it is low, whereas in canary it is low to medium. In blue-green it is high, 100% extra infrastructure cost, because there is two identical production environments. Metric rollback speed. In rolling update it is slow, it recreates old pods with the new version ones. In canary it is fast, shift traffic back. In blue-green it is instant, change router target. Metric, that is user exposure risk. In rolling update it is medium. In canary it is low, isolated blast radius. In blue-green it is medium to high. Metric, that is implementation complexity. In rolling update it is native or built-in. In canary deployment strategy it is complex, that is it requires traffic control, that is Ingress controller and all this. And in blue-green it is medium, it requires environment configuration cloning. So the topic is, what is a service mesh? East-west traffic versus north-south traffic. What is a Istio service mesh and core features offered by Istio and how it works. We will learn what is sidecar containers, envoy and Istiod, and also what is Kubernetes API server with respect to Istio and admission controllers and dynamic admission controllers. But before we begin, hi, this is Kev. I have been a recruiter in the past. Now I have moved into DevOps from scratch. This is part of my transition series. You are making the same switch. Stick around. So first, let's understand what is a service mesh. A service mesh is a dedicated infrastructure layer built directly into a containerized application to handle secure, fast, and reliable service-to-service communication. In a traditional monolithic application, functions talk to each other internally. In a microservices architecture, applications are broken down into tens or hundreds of independent services that must constantly communicate over a network. Managing this communication directly within the application code, for example, writing custom code for retries, encryption, or login creates massive technical debt. A service mesh offloads these operational complexities from our application code down to the infrastructure layer. First, let's understand what is monolithic architecture and microservices architecture in application development. Monolithic is a traditional or old way of building applications. That means application is of a single service that doesn't have any breakdown of its services or functions, meaning the application itself is a single build code. Whereas for microservices architecture, application services and its function are differentiated and are broken down into tens or hundreds of independent services that communicate constantly over a network. This is really great for managing services and reducing the technical overload of applications. But managing this communication directly with the application code, meaning we aiming to write custom code for encryption, logging, retries and networking, this creates massive technical debt over the developers. So a service mesh will offload these operational complexities from our application code down to the infrastructure layer by adding an infrastructure dedicated layer directly into the containerized application to handle secure, fast and reliable service-to-service communication. Here service is microservice architecture that is broken down into tens or hundreds of independent services that must communicate with each other to let the application work. Now let's understand what is east-west traffic versus north-south traffic. To understand network traffic in a cluster, engineers categorize it into two main directions. North-south traffic. This represents traffic moving into and out of the data center or Kubernetes cluster. For example, an external user accessing a web application from their browser enters through an Ingress gateway, that is north to south. Whereas east-west traffic, this represents traffic moving entirely within the cluster between our internal services. For example, our front-end services requesting data from the authentication service or the authentication service communicating with the payment service. Key thing to note here is that a service mesh is specifically designed to manage, secure and monitor east-west traffic. So north-south traffic simply is the traffic from outside of the data center or the Kubernetes cluster. For example, an external user accessing web application from browser enters through an Ingress gateway, that is called north to south, meaning it is external to internal. And east-west traffic is internal traffic within the services. It is the traffic that is moving entirely within the cluster between our internal services. For example, our front-end service requesting data from authentication service or authentication service communicating with the payment service. And service mesh is specifically designed to monitor service-to-service communication, that is called east-west traffic. Now, what is a Istio service mesh? Istio is an open source production ready service mesh that integrates transparently with cloud native applications. It acts as an underlying control plane that manages how data is routed and secured between our services. So we understood the concept of service mesh. Now, Istio is an open source production ready service mesh platform that integrates transparently with cloud native applications. It acts as an underlying control plane that manages how data is routed and secured between our services. What are the core features offered by Istio? First is mutual TLS or MTLS. TLS means transport layer security. By default, the internal cluster traffic is unencrypted, which is HTTP. Istio automatically upgrades service-to-service communication to MTLS, that is Mutual Transport Layer Security, without requiring us to change a single line of application code. We must know that all the services and everything we deal with Istio or service mesh is related to internal communication, which is east-west traffic. So here the same concept of a TLS, that is transport layer security, which is mutual, is internal services that are by default unencrypted, which is HTTP. So there must be certain services or service mesh that would automatically upgrade it to secure, which is HTTPS. So Istio is a service or open source platform that automatically upgrades service to service communication from unencrypted HTTP to MTLS, which is Mutual Transport Layer Security, without requiring us to change a single line of application code. It handles automatic key and certificate generation, distribution, and rotation. It ensures that both client and server verify each other's identity before exchanging data, preventing man-in-the-middle attacks within the cluster. Usually when we hear about TLS, we think of it as north-south traffic, which is external user accessing the application. But here in service mesh or Istio, it is east-west traffic, which is service-to-service internal traffic, while we implement HTTPS or TLS for north-south traffic, which makes it HTTPS. It is same. We also implement HTTPS or TLS, transport layer security, but for east-west traffic or service-to-service communication. Here Istio handles automatic key and certificate generation, distribution, and rotation, and it ensures both client and server verify each other's identities before exchanging data, preventing man-in-the-middle attacks within the cluster. So all of this communication, encryption, security happens behind the scenes, where there must exist a handshake between services to verify its certificates or identities of TLS before exchanging data or communicating with each other, that prevents man-in-the-middle attacks within the cluster. Second is ease of advanced deployment strategies. Istio makes complex deployment patterns remarkably simple by managing traffic routing rules at the network layer, which, for example, canary deployments, we can deploy a new version, that is version 2 of a service, and use Istio to route precise 1% or 5% of live traffic to it. Once verified, we can scale it up smoothly. Blue-green deployments. We can keep the old production environment, that is blue, and new environment, that is green, fully isolated, then instantaneously switch 100% of the traffic to the new version with zero downtime. First, we must know that there are certain deployment strategies in Kubernetes like canary deployment, blue-green deployment, and rolling update. These strategies ensure that when an application is upgraded from a certain version, there must exist zero or near zero downtime and zero or near zero risk and minimum resources taken to achieve it. So Istio manages these advanced deployment strategies and makes it efficient and easy to manage. How it does? It makes complex deployment patterns simple by managing traffic routing rules at network layer. For canary deployment, we can use Istio to precisely route traffic 1% or 5%. Once it is verified, we can scale it up smoothly. For blue-green, it is to switch from blue to green and to route 100% of the traffic to the new version with zero downtime, or if it has some bugs or errors, and to switch it back to the blue or the old version with 100% traffic with near zero downtime. Smart observability with Kyali. Kyali is a management console specifically built for Istio. It acts as the visual dashboard for our service mesh. How Kyali benefits teams. It provides live topology graphs. It visualizes our entire microservices network in real time, showing exactly which services is talking to what. Traffic health at a glance. It color codes service relationships based on HTTP status codes, for example green for 200 OK and red for 500 server errors. Performance metrics. It integrates with Prometheus to display latency, request rates, and error rates directly on the visual graph. For configuration validation, it analyzes our Istio configuration files for errors, helping us catch misconfigured routing policies before they break production. Now let's understand how Kyali works with Istio in solving observability observability and monitoring of application. We know that we use Prometheus, Grafana for monitoring and observability for visual dashboard, etc. But by default, it has empty panels and dashboard for observability, where we manually create those PromQL dashboards, which can take time to build it. So Kali solves it by providing visual dashboard for our service mesh that is way better than manually creating dashboards or observability. It provides live topology graphs, traffic health at a glance, performance metrics, configuration validation. Simply, it provides dedicated smart visualization and observability with respect to our services and service mesh. So that was about Istio service mesh and its core features. Now let's understand how it works, meaning what are sidecar containers, Envoy and Istio. Istio splits its architecture into two distinct parts, which is the data plane and the control plane. First is the sidecar container Envoy proxy. Instead of forcing our application code to handle routing and encryption, Istio injects a lightweight proxy called Envoy into the same pod as our application container. This companion container is known as the sidecar. So instead of forcing the application to handle routing and encryption, which is MTLS and other benefits offered by Istio, or service mesh concept of east-west traffic management, here Istio injects a lightweight proxy called Envoy into the same pod as our container. That would mean our application would have two containers, and this companion container is called as the sidecar. This sidecar container or Envoy proxy will help in routing, encryption, deployment efficiency, and Kali monitoring and other benefits as well. Second is the shift in request flow. Before a service mesh is introduced, container A calls container B directly over the network. With Istio implemented, the request flow changes completely. Container A initiates a request to container B. The network traffic is transparently intercepted and redirected into container A's Envoy sidecar. Then the sidecar A establishes an encrypted MTLS tunnel with sidecar B. Then sidecar B receives the encrypted traffic, it decrypts it and passes it locally, that is over the local host, to the container B. So we must know that before Istio was introduced, our container was directly communicating with each other, meaning container A calls container B directly over the network. But when Istio or service mesh concept is introduced, that request flow changes completely, meaning now container A will not directly communicate with container B. When a container A initiates request to container B, the network traffic is transparently or behind the scenes, it is intercepted and redirected into the container A sidecar container, which is Envoy. Then sidecar container A establishes an encrypted MTLS tunnel with sidecar B. Then sidecar B receives the encrypted traffic, it decrypts it and passes it locally to the container B. Before it was container to container communication, now it is container A will try to initiate the communication with container B, but it will not happen until container A's sidecar container network traffic is intercepted, which is redirected into its Envoy sidecar container. Then container A's network traffic is encrypted to proceed communication with the container B. When it reaches container B, it first communicates with the sidecar container of the container B. When sidecar container of container B receives that encrypted traffic, it decrypts it and passes it locally to the container B. Before it was direct container communication, now the communication is through sidecar containers to implement MTLS, that is mutual transport layer security. Because Envoy handles this handshake, our application containers believe they are simply sending and receiving standard and encrypted HTTP traffic. This interception allows the sidecar to reliably enforce timeouts, handle retries, and execute split traffic deployment strategies like canaries, regardless of what language the underlying application is written in. One more thing to note is that here the word intercepted and redirected is mentioned. There is a purpose and reason to mention this word. Without Istio communication of containers, which is container to container, it was Kubernetes API server communicating with etcd for pod communication. Now with Istio service mesh, that etcd step is intercepted by sidecar containers. Now third is centralized control with Istio. While the Envoy sidecars handle the actual data plane or the data, Istio acts as the brain or the control plane. Istio does not touch individual application request. It acts as a central certificate authority to issue MTLS certificate to the proxies. It translates high-level routing configurations into instructions that Envoy can execute. It collects telemetry data and metrics tracked by the sidecar containers, passing them downstream to monitoring tools like Prometheus and Kyali. Simply, all the benefits or services offered by Istio service mesh can be considered as data plane, and Istio is the brain that is control plane, meaning Istio does not touch application request. It acts as a central certificate authority for TLS certificate to the proxies. It translates high-level routing configurations into instructions that Envoy sidecar containers can execute. It helps in collection of telemetry data and metrics that is tracked by sidecar containers, then passing them downstream for monitoring tools like Prometheus and Kyali. So Istio acts as the brain that is the control plane. Now let's understand Kubernetes API server with respect to Istio service mesh and what are admission controllers or dynamic admission controllers. To inject these sidecar containers automatically without manual user intervention, Istio relies on 4 extension points within Kubernetes. So what is an admission controller? An admission controller is a piece of code that intercepts requests to the Kubernetes API server after the request is authenticated and authorized, but before the object is persisted into the cluster storage etcd. So I mentioned before about interception and redirection. Kubernetes admission controller is responsible for implementing that or making it work, as admission controller is a piece of code which helps in interception of request to the Kubernetes API server, and after that request is being authenticated and authorized, before that object or communication exists between the cluster's etcd storage. Simply, they act as the gatekeepers. For example, an admission controller can reject a pod deployment if it violates security compliance rules. Now, what is a dynamic admission controller? A dynamic admission controller allows developers to extend Kubernetes capabilities using webhooks. There are 2 types of dynamic admission controllers. First is validating admission webhooks that can read the request and either accept or reject it. Second is mutating admission webhooks that can read the request and modify or mutate the configuration on the fly before it deploys. Without Istio or service mesh communication in Kubernetes API server would communicate with etcd. Now, while we implement Istio service mesh or Istio service mesh, that flow is intercepted, and now it is Kubernetes API server first communicating with admission controller, which is intercepted before the etcd communication or before the object is persisted into the cluster storage etcd. So after it is intercepted, it has certain superpowers in the sense of either accepting the request or rejecting it, or to read the request and to modify or mutate the configuration on the fly before it deploys. In short, it is like we are adding a barrier between direct communication of etcd and API server. Now it is API server first communicating with intercepted dynamic admission controller's configuration, then it reaching to the etcd, not directly. By doing this, we are extending Kubernetes capabilities by adding validating admission and mutating admission webhooks that helps in either accepting or rejecting the request and to modify or mutate the configuration before it is deployed. Now let's understand how this actually works, meaning auto-injecting sidecars. Istio utilizes a mutating admission webhook to inject sidecar containers seamlessly. As I mentioned, there exist 2 types of dynamic admission controllers. One is validating and second is mutating. For sidecar containers injection, mutating dynamic admission controller webhook is utilized by Istio. How it works? First, user or the CICD deploys standard one container pod manifest, which is Kubernetes API server, then communicating with Istio mutating webhook. How it inspects namespace for Istio injection is equals enabled label. If this label exists, then mutating admission controller webhook takes place, providing sidecar containers. If this was not enabled or present as a namespace, then it would be a normal pod-to-pod communication without sidecar containers. Then manifest of the pod is updated dynamically without us trying to update it, which means injected pod manifest, which means it adds envoy proxy container, that is sidecar container plus wet init containers to manifest. So after it inspecting or finding Istio injection is equals to namespace label, it injects or adds envoy proxy container. So now we have both containers, which is init containers of the manifest of which we have provided, and new container or sidecar container added in the file, which is envoy proxy container or sidecar container. So this were the steps between Kubernetes API server finding or inspecting namespace Istio injection enabled before it even reaching persisted etcd and scheduled. So if Istio injection would not be present, it would directly communicate by Kubernetes API server and persistent etcd and scheduled. Now as it inspected or found out Istio injection is equals to enabled, which is Istio mutating dynamic admission webhook, it intercepts and modifies the manifest file dynamically by adding another sidecar container into it. So now we have two containers. After all this, it reaches persisted to etcd and scheduled, which means pod spins up with two containers running inside it. So again, if it will not find the Istio mutating admission controller webhook or simply Istio injection that is enabled label in the namespace, it would be direct Kubernetes API server to persistent etcd communicating with each other. Now as this namespace is inspected, the communication between them is intercepted by Istio adding or intercepting mutating dynamic admission controller webhook, which modifies the manifest file dynamically by adding proxy envoy sidecar container into our containers manifest file. Then finally it reaches the persisted etcd and scheduled. Then it spins up two containers running inside it. One is of our application or manifest file and second is of envoy sidecar proxy container. So how this looks: submission engineer or CICD pipeline sends a standard, that is a standard deployment manifest containing only our application container to the Kubernetes API server. Then interception takes place, which is the API server passes the manifest to the Istio mutating webhook, which is Istio sidecar injector. Evaluation: the webhook checks if the target namespace has the label Istio injection is equals to enabled. Then mutation: if it is enabled, the webhook actively modifies the deployment configuration on the fly. It injects an init container to configure network routing rules via IP tables and the envoy proxy sidecar container definition directly into the pod specification. Execution: the API server stores this expanded mutated configuration. When the kubelet runs the pod, it starts up with both our application container and the sidecar container running side by side automatically. The topic is how to secure Kubernetes cluster. We will discuss how is Kubernetes cluster security is managed and how it is secured. But before we begin, hi, I'm Kev. I have been recruiter in the past. I moved into DevOps from scratch. This is part of my transition series. If you are making this same switch, stick around. So securing a Kubernetes or K8s cluster is not just an administrative best practice, it is a fundamental requirement for production environments because Kubernetes orchestrates containerized workloads across multiple machines. A compromise in one area can lead to a full cluster data exfiltration or malicious resource hijacking like crypto mining. Securing the cluster protects the underlying infrastructure, the hosted applications, and sensitive business data. So securing Kubernetes cluster is not just a basic or administrative best practice. It is a fundamental requirement for production environments, meaning it is a really important step and we must make sure that Kubernetes cluster and Kubernetes environment is secure and follows the best security practices. It is because Kubernetes orchestrates or operates between containerized workloads across multiple machines. A compromised or hijacked or malicious attempt in one area of a cluster can lead to a full cluster takeover, that is data exfiltration or malicious resource hijacking like crypto mining. So securing cluster protects the underlying infrastructure like hosted applications, sensitive business data. Now how it is secured? First, it is by securing API server via TLS. The Kube API server is the gateway to a cluster. Every administrative command, internal component, communication, and deployment goes through it. If it is unencrypted or exposed, attackers can take absolute control. So Kube API server is a gateway to the cluster, and every command that is administrative or internal component communication and deployment goes through it. So if Kube API server is unencrypted or exposed, so that attackers can take the absolute control. So how this API server can be encrypted or secured or have security best practice? By default, production clusters encrypt API traffic using TLS or transport layer security. This is enforced by modifying the static pod manifest file for the API server that is typically located at /etc/kubernetes/manifest/kube-API-server.yaml on the control plane node. So we ensure that specific flags point to the valid X509 certification and private keys. So that is like the commands for TLS certification file, TLS private key file, client CA file. So these are the updates that need to be made in the Kube API server YAML file that would have valid TLS certificate. By default, Kube API server is not encrypted. So to encrypt it, we must provide TLS certificate inside the Kube API server YAML file. By doing it, it would be secured and encrypted. So the difference you can understand it by knowing HTTP is not secured and HTTPS is secured in a website. So HTTPS would have TLS certificate and it is secured. It has also the same mechanism of providing TLS certificate in it. So we are securing Kube API server by adding or providing TLS certificate. So the internal communication, every communication or commands that are being made via Kube API server is encrypted. It provides transport layer security. So when we modify this YAML file, the kubelet automatically restarts the API server pod to apply the secure configuration. Second is role-based access control or RBAC. Not every user or service needs administrative privileges. Role-based access control ensures the principle of least privilege, meaning users and software applications only get the exact permissions that they need to do their jobs. I've already explained role-based access control in detail in my previous Kubernetes videos. You can also watch those if you want to know role-based access control. But simply role-based access control is providing the required or exact permissions to the users or services to do their job and not providing more than that permissions to have better control and security over our services, applications and its data. So administrator or admin will have all the permissions and rest of the users and services will have permissions only that is needed to do their job. So how it is done? Role-based access control or RBAC uses 4 core components of Kubernetes objects to map who, that is subjects, can do what, the verbs to which resources, meaning role or cluster roles. It is to define permissions. For example, a role might allow a user to only get list and watch pods. That is, cluster role apply, cluster-wide roles apply to a specific namespace. So role-based access control is a concept where we outsource or offload the user management by using the services of OAuth, by providing users information in the OAuth or IAM of the AWS, and then we provide the login for those users that has already been created inside the AWS or other cloud provider services. That was about user management and user being created. But users will also have certain job to do. Like if it is a DevOps engineer, that would have certain role. So role is, you can say, YAML file or a permission file which has certain permissions that can be list or watch pods, and that can be assigned to users so they can have that much permission with respect to the information provided in it. Simply role or cluster role are set of permissions like that defines actions like read, write or delete with respect to a user, group or an application that can perform on specific Kubernetes resources. Role is restricted to a single namespace and cluster role is cluster-wide, meaning it is across all namespaces. Basically, cluster role is not limited, but role is limited to a single namespace. Now, role or role bandings or cluster role bandings. So these are attaching those permissions to specific users, groups or service accounts, meaning role are the specific roles and permissions in a file. Cluster role banding or role bindings is a step where those permissions are attached to the users, groups or service accounts. So both roles, cluster roles and role bindings or cluster role bindings go hand in hand. Role is like the specific file of permissions and role bindings is a step to bind those with the users to have better role-based access control. Third is network policies. By default, Kubernetes networking operates on a flat structure, meaning all pods can talk to all other pods across the cluster. If an attacker compromises a front-end application, they can easily traverse the network to attack the backend databases. So in Kubernetes, by default, all pods can talk to all other pods across the cluster. So this is not a healthy or secure step or the structure that Kubernetes follows. So if an attacker compromises a front-end web application, they can easily traverse or hack the network to attack the backend databases. So it must be secure and follow certain rules or practices to avoid it being hacked or get malicious attempts. How it is done? Network policies act as an internal firewall for our pods. They allow us to define explicit ingress, that is incoming, and egress, outgoing traffic rules based on labels and namespaces. So this pod-to-pod communication or all communication within the cluster, that is networking, is solved by implementing network policies. Network policies is a similar concept to role-based access control, meaning we don't allow the default every traffic or all traffic to be spread across all the namespaces across the cluster. Instead, we only allow specific traffic or traffic based on the labels and namespaces that is only needed for those resources. So that would allow us to define explicit ingress, that is the incoming traffic, and outgoing traffic based on the labels and namespaces we specify in the network policies. So how it will look like? We must use a container network interface, that is CNI plugin, that supports network policies such as Calico, Calium or Weave. So we can use CNI plugin, that is container network interface plugin, that supports this network policies concept. And a standard production strategy is to be implemented by a default deny all policy for a namespace, and then we explicitly write policies to allow only required traffic. For example, front-end pod can talk to back-end pod on port 8080, but back-end pod cannot talk to the front-end. First would be a CNI plugin that supports network policies should be implemented, and also by default we can implement a deny all policy for a namespace for a network, so it would not allow any traffic by default. And then we specify certain rules or certain policies to allow required traffic that we need. For example, if we need front-end pod to talk to the back-end pod on 8080 port, but back-end pod should not talk to the front-end. So we specify these rules or policies in a namespace. So we would be implementing deny all by default. It would not allow any traffic by default. And then we specify certain rules or permissions that we want to have. So it would operate on those permissions. Now fourth is encryption at rest, that is etcd. etcd is the source of truth and the key value database for Kubernetes. It stores configuration data, cluster state, and crucially Kubernetes secrets, that is passwords, tokens, API keys. By default, etcd stores this data in plain text. If an attacker gains the access to the backup storage or the master nodes file system, they get all our secrets. So we know that Kubernetes architecture has certain components, and one of them is etcd, that is like the database that stores key value data, and it stores configuration data, cluster state, and crucially Kubernetes secret, that is password, tokens, API keys, all those data as well. So by default, the data that is stored in etcd is in the plain text. So if an attacker gains the access to this etcd at rest, attacker can easily understand the passwords that is in the plain text and eventually get the secret or API key information. So how it is solved? We configure the API server to encrypt data before writing it to the etcd using an encryption configuration object. So it is solved by encrypting the data, specifically sensitive data, which is Kubernetes secrets, API keys, passwords, in etcd using encryption configuration object. How it is done? We create a configuration file specifying which resources to encrypt, typically secrets, and the encryption providers such as ACE GSIM or ACE SCBC. Then we pass this file to the API server via this flag. So to encrypt the secrets or sensitive information stored in the etcd, which is like the database for Kubernetes, we can take the help of encryption providers like ASGCM or SBC by creating a configuration file and specifying the resources like secrets for it to be encrypted, and then we pass this file to the API server via encryption provider config flag. And for enterprise environments, it is best practice to use a key management service KMS provider like AWS KMS, Azure Key Vault or HashiCorp Vault. So the encryption keys are rotated and managed outside the cluster. And for enterprise or production environments, the best practice is to use key management service that is provided by cloud providers like AWS KMS, Azure Key Vault or other providers like HashiCorp Vault. So they would manage the keys for us, so that keys would be encrypted, that would be rotated outside the cluster, and it is managed by these providers. Fifth is using secure container images. A cluster is only as secure as the applications running inside it. Container images frequently contain outdated operating system libraries with known vulnerabilities, that is CVEs, or worse, that is malware. A cluster is only as secure as the application running inside it, meaning if the application running inside a cluster is not secure, then the cluster will not be secure. So the application running with outdated or vulnerable container images or outdated operating system libraries with vulnerabilities or malware will eventually affect the security of the cluster. Then how it is managed? Minimal base images. We use minimal base images like Distroless or Alpine Linux instead of full Ubuntu or Debian images. This drastically reduces the attack surface. Or simply we use the specific images or with specific patched or fixed versions that doesn't have vulnerabilities in it. And second is vulnerability scanning. We integrate automated scanning tools like Trivi, Claire or Grip into our CICD pipeline, which blocks deployments if images contain critical or high vulnerabilities. I've already made a complete video on DevSecOps, image scanning and scanning in general for the application, which is Trivi and all this vulnerability scanning, and I make sure that my application was almost like 99% vulnerability free. Third is private registries and image signing. Storing images in secure private registries and using tools like Cosign to sign images. This ensures that the cluster only pulls verified, untampered images, and we can store the images in the private registries so it is secure, and we can use the tools like Cosign to sign the images, ensuring the cluster only pulls verified, untampered images. Sixth is cluster monitoring and runtime security. Prevention mechanisms like role-based access control and network policies cannot stop zero-day exploits or malicious inside behavior. We need real-time visibility into what is actually happening inside our running containers. So role-based access control and network policies are great in solving a lot of issues with respect to security of the cluster, but it cannot stop day-to-day exploits or malicious inside behavior. We need real-time visibility into what is actually happening inside the cluster or inside the running containers. How it is solved? We use runtime security and observability tools like systemd, or that is 6dig, which is built on open source Falco. These tools hook into the Linux kernel, that is often via EBF, to monitor system calls. They detect anomalous behavior in real time, such as containers suddenly spawning a root shell, changing system binaries, or attempting unauthorized outbound network connections. If malicious activity occurs, the tool triggers immediate alerts or automated containment actions. For real-time security and observability, there are certain tools like systemd or sysdig, which is open source. These tools hook onto the Linux kernel, that is the root of the Linux, often via EBF, to monitor system calls or how we communicate with the cluster or the system. They detect anomalous behaviors using AI or other within it in real time, such as containers suddenly spawning in a root shell, changing system binaries, or attempting unauthorized outbound network connections. So it detects or checks the suspicious behaviors real time using certain AIML concepts within these applications, that is open source systemd. So if certain malicious or suspicious activity occurs, this tool triggers immediate alerts or automated containment actions to fix or solve those vulnerabilities and issues that is happening real time. Now, seventh and the final is keeping the ecosystem up to date. Kubernetes moves fast. They release new minor versions regularly. Older versions stop receiving critical security patches. Furthermore, the underlying operating system's container runtimes like containerd and KDS components accumulate vulnerabilities over time. So, one of the key aspects of keeping Kubernetes cluster secure is to keep everything that is within the cluster and its components, including Kubernetes components, up to date within the patched or fixed versions, that is the latest versions. And with respect to Kubernetes, the Kubernetes releases minor versions regularly, and older versions of Kubernetes stop receiving critical security patches or fixes. Furthermore, the underlying operating system, container runtimes, containerd, and all these components accumulate vulnerabilities over time. So it needs to be updated or kept up to date by upgrading it. So how it is done? Regular patch schedule, establishing a lifecycle management plan to upgrade Kubernetes clusters systematically, that is control plane first, then worker nodes, then staying within the officially supported versions, that is the latest 3 minor versions, then node operating system patching, that is to use managed Kubernetes offerings like EKS, GKE, AKS to automate node operating system patching, or using automated tool like Cure, that is Kubernetes reboot daemon, to handle safe rolling operating system updates on self-managed nodes without disrupting application availability. So that was about Kubernetes upgrades thing, but we must make sure that other components, Jenkins, Terraform, or other tools that we are using or implementing within the CICD pipeline or in general are upgraded or up to date with the latest or near latest versions, so it is vulnerability free. The topic is creation and enforcement of Kyverno policies inside a Kubernetes cluster. I will explain how I created and implemented those policies and importance of those policies inside a Kubernetes cluster. First, let's understand what is Kyverno policy, meaning what is the purpose of Kyverno and where does it fall in the Kubernetes concept. First, we must understand that there is a concept of Istio service mesh where it says that there exists north, south and east-west traffic within the cluster, meaning north-south traffic is the traffic that is outside, meaning outside users accessing the application, and or east or west traffic is the traffic within the cluster, interpersonal communication between the resources, that is pods and everything, that is known as east-west traffic. So service mesh is a concept where that east-west traffic is managed, meaning it is managed by providing TLS certificate security and monitoring benefit. How it does? There is a concept inside the Istio service mesh or service mesh, that is admission controllers or dynamic admission controllers. Istio mesh providing its services or benefits comes by it creating a sidecar container besides our main container, meaning there would be two containers that is running. One is the main container or your application and another would be the sidecar container, and it is created hand in hand on the fly, which is related to admission controllers, that is dynamic admission controller. Dynamic admission controller is a concept where request to the Kubernetes API server is intercepted before it reaches the etcd, that is the database. By doing so, it gives us more privilege and more powers to either validate or to mutate, which is creation, deletion, modification of objects and requests. Basically, the concept of service mesh and dynamic admission controller and everything in between is related to giving us more powers and privilege to access and control our Kubernetes cluster. It provides TLS security, enhanced monitoring, more control in managing the compliance and security concept related to Kubernetes cluster. Now, as we know about service mesh and dynamic admission controller or admission controller concept, we can understand the Kyverno policies. Kyverno is an open source tool platform that is used to enforce and provide policies and security, which replaces or is a simple alternative to us writing the complex admission controllers by ourselves. Meaning, if we were to write admission controllers or dynamic admission controller webhooks to implement those validating or mutating and interception of Kubernetes API server to enforce certain policies or related to security and storage or compliances, we would have to learn Go language and then implement and create such policies of admission controllers and dynamic admission controllers. So Kyverno is an alternative, that is where we create a YAML file with certain syntax of Kyverno which is provided in their website, and we enforce such policies which replaces the headache of creating dynamic admission controllers or admission controller policies. Now in this tutorial I will be implementing 3 Kyverno policies. First is disallow privilege policy, meaning it is a set of rules that is enforced by Kyverno to prevent workload from gaining administrative control over containers and underlying nodes. So this policy will prevent containers from running in privilege mode or in the root mode. Second is Kyverno pod CPU and memory policy. This is a set of rules and policies enforced by Kyverno to restrict or ensure containers inside the Kubernetes cluster are deployed within defined computing resources. Meaning instead of leaving resources allocation or not specifying such information while creating deployments or YAMLs, this policy validates that every container must specify request and limits for both CPU and memory. Simply, it will not let you create a pod if its resources, CPU or memory is not specified in the deployment file or the YAML file. And third and final policy is Kyverno image policy. This is a set of rules that says container images running inside our Kubernetes cluster must meet the organization's security, compliance and supply chain integrity standards before they are allowed to be created or updated. Simply, it is specifying authorized resources, more specifically defining your organization's image registry, and it only allowing you to pull images within those specified sources. If it is besides that or not specified, it will not pull the images. So these are the policies. Now let's begin. First command is to start the Minikube. I performed Minikube start with the memory and CPU specification, that is 5.6 GB and 4 CPUs. It was successfully started. Now next is to add and install Kyverno. The command I used was helm repo add Kyverno with its link and helm repo update, then followed by helm install Kyverno with this command and creating Kyverno namespace within it. It was successfully created and deployed. I confirmed it by performing kubectl get pods -n for namespace Kyverno, and it showed all these required pods with respect to Kyverno, that is up and running. Next, we will perform all these 3 actions without these policies, and we will confirm that it is letting us create or perform these commands without those policies or rules. Meaning I will create a pod with privilege true, meaning I will add privilege that is true inside the YAML file of the pod, and I will run the pod with no resources specified, and I will pull the image without specifying the repository or image registry. For this, I first created privilege.yaml to create a pod with privilege access. This was a pod specification file. Then I switched into Kubernetes directory and I applied YAML file with Kubernetes kubectl apply -f with privilege.yaml, and it was created, and I confirmed it with kubectl get pods, and it was up and running with privilege access, that is true. And for second, I performed kubectl run no resource pod with the image nginx, meaning no resources has been specified while creating this pod. I confirmed it with kubectl get pods, and now both of these pod are up and running, meaning privilege access pod and no resources specified pod, both are up and running. And third and final was kubectl run docker hub pod with image nginx latest, meaning there is no specification of registries. I confirmed it with kubectl get pods, and all these 3 pods were up and running, meaning these 3 policies were not applied until now. So without these policies, these pods are running. Privilege pod with privilege true, meaning it is having privilege access or permissions, and second is no resource specification while creating the pod. We have not specified memory and CPU allocation while creating this pod, and it is up and running. And third is no direct specification of registries authenticated and within the compliance of your organization, which is nginx, that is created. Now let's implement these policies, that is Kyverno policies, one by one and apply these commands again to see if this policies works or not. So the first YAML for this policy is disallow privilege official YAML. So this is the format which is officially available in their Kyverno site. I have also used the same format from it, or the template from it. This policy is to disallow privilege access or permissions to run in privilege mode. Simply, this policy ensures pods do not call or run in privilege mode. Here's the important part. We can observe that there is a statement validation failure action which is mentioned enforce. It is by default audit. Audit means it will allow you to run this or perform your commands and everything, it will work fine, but in the background, in the logs, you will see that this policy is working. It will allow you to perform the actions, but in your logs you can see that policy is working, but when it is enforced, it will not allow you to perform the action. So I kept it as enforced so we can observe this policy in action. That was the first policy. Now for second policy, this is the same template or the format on this site, and I kept it same enforced so we can observe that it is working or not while performing the command. So this policy, which is required resources YAML, it is to ensure every container is defined by CPU and memory request and limits to prevent resource starvation or node crashes. So it also has the message CPU and memory request are required. Now let's apply this YAMLs or these policies. I performed kubectl apply -f required resources YAML, kubectl apply -f disallow privileged official YAML, and it showed that cluster policy Kyverno, these two policies are configured, meaning it is running. To confirm it, I performed the same commands again. First, I deleted the previous pod performing kubectl delete pod privilege pod, and I applied that same privilege YAML pod again. Now it shows error from the server, and it shows error when creating privilege.yaml. It says admission webhook validate.kyverno.svc fail denied the request, and it says it was due to the following policies. The policies is disallow privilege containers. It says validation error privilege mode is disallowed. So the pod which we have created in the YAML, it has privilege that is true, so it is not allowing us to create the pod that has privilege access or mode that is true. Now for the second policy, I performed kubectl run node source pod with the image nginx, and again it showed the error from the server with the admission webhook validate.kyverno.svc fail, that is denied the request because it is enforced. So it says it is due to the following policies: require resources, require request limits, validation error CPU and memory request or limits are required. So these two policies worked and we have implemented it. Now for the third policy, which is specification of registries, simply image registries in specified compliance authenticated by your organization or company. In my case, I would be implementing this image within my GitHub account registry. To do that, my plan is to first push the image from Docker Hub to the GitHub repository and then create a policy that enforces to only pull images from the exact same GitHub account of mine or GitHub image registry of my account. To perform all this, first it is to create personal access tokens. So I head back and logged into my GitHub account and I created the token with the name image push with read and write packages checked. Then I created that personal access token. Then I head back into the Docker Hub. I logged into it. Then as you can see, there is the image that is being pushed, which is Kaif Mohammad Khan 123/resume DevOps. My aim is to push this image into my Docker image registry. To do that, I perform the command that is echo with the personal access token created or generated by GitHub pipe, that is followed by Docker login GHCR.io, which is GitHub container registry, followed by -u, that is username of my GitHub account, which is Kaif Mohammad Khan, followed by password of GHCR GitHub. Then it was successful login. Then I performed Docker tag with Docker tag Kaif Mohammad Khan 123/resume DevOps latest, which is my Docker pushed image into the GHCR.io, that is GitHub container registry, followed by my username and the name of the image, that is resume matcher DevOps latest. After tagging it, I perform docker push. Docker push GHCR.io followed by my username and the image name. It was successfully pushed. After this, I head back into my GitHub account and I checked the packages section, and it was successfully pushed into the packages section, meaning it is successfully pushed into GHCR GitHub container registry. Then next is to update deployment file to only use images within that registry. To perform that, it is for us to create a secret. So I head back into the GitHub account again and I created the token with read packages, and then I created the secret by performing kubectl create secret, which is docker registry aiming GHCR secret, which is specifying docker server, that is GHCR.io, username which is Kaif Mohammed Khan, and docker password, which is the token I created or generated. The secret was successfully created. Then I updated the deployment.yaml file with default image pull with image pull secret section. So I added image pull secrets with name GHCR secret. Then I applied this deployment file by kubectl apply -f deployment.yaml. It was successfully configured. Then I created the restrict image registries YAML file, meaning Kyverno policies to restrict image that is outside our organization. The same, I enforced it, and the policy says that images from unknown public registries can be dubious quality and may not be scanned and secured, and it will give a message unknown image registry if it shows error. And in the rules you can see it is validate the registries, and below we can see or observe that we have specified GHCR.io with our username Kaif Mohammed Khan. It is for ephemeral containers, init containers and containers with the pipe docker.io library and Postgres. So if it is not within these specified registries, it will not allow us to create or run with other images. I saved this YAML and I applied it with kubectl apply -f with the name restrict image registries.yaml and cluster policy kyverno.io, which is with this name was created. Then to validate or check it, I perform the command kubectl run docker hub pod with specified image nginx, which is not within the specified registries, with the command override, and the below is to specify container size and memory because of the other policies we have implemented. Meaning if we were not to implement the memory and CPU resource policy, I wouldn't need to specify this information while performing this command. Since we have created another policy for specifying CPU memory, I have to specify with these constraints and information, that is memory and CPU, to run this. I ran this command and it showed error from the server, that is admission webhook validate Kyverno SPC fail, which is denied the request, which says it was due to the following policies: restrict image registries, which says validate registries, validation error, unknown image registry. So since it was not within the specified image registry, that is ghcr.io/Kaif Mohammed Khan, which is within the docker.io library and Postgres database, is not allowing us to run this pod with other images. The topic is understanding and deploying 3-tier Node.js application, that is resume matcher, on kind, that is Kubernetes in Docker, exposing its NodePort via port forwarding, and we will understand the concept and apply node affinity, taints and tolerations, labels, and I will also perform GitHub actions workflow to build and deploy image into the GHCR, which is GitHub container registry. But first, let's understand what is Kubernetes in Docker. Simply kind. Kind is an open source tool designed to run local Kubernetes clusters by using Docker containers as cluster nodes instead of spinning up heavy virtual machines to act as control planes and worker nodes. Kind packages an entire Kubernetes environment into a lightweight Docker containers. So when we hear about Kubernetes environment and running it, we think of Minikube and actual cloud platforms like AWS or Azure, and cloud platforms are paid. When you would run applications or deploy applications and run Kubernetes in it, you would have to pay for the charges on how much time you spent on. And also on Minikube, it takes quite time to spin up and start the Minikube cluster, and also Minikube offers single node architecture, and it also takes quite a good amount of space to run it. Whereas Kubernetes in Docker kind is an open source tool designed to run Kubernetes locally and its clusters by using Docker containers as cluster nodes. So it would be a lightweight Docker containers acting as a cluster nodes. That was about kind, that is Kubernetes in Docker. Now, what is node affinity with respect to Kubernetes? Node affinity in Kubernetes is a scheduling mechanism that constrains or restricts which nodes your pods can be scheduled on based on the labels attached to those nodes. Simply, it is like a preference or requirements that attracts pod to specific machines or with respect to the nodes specified in the cluster. And there exist hard constraint and soft constraint in node affinity. Soft is a soft constraint, meaning the scheduler will try to find a matching node. If no matching node exists, it will schedule the pod elsewhere anyway, meaning it is not strict. Whereas the hard constraint, this means rule must be met for the pod to be scheduled, and if no nodes match the labels, the pod will stay in the pending state. I will apply the hard constraint later in this video. The purpose of hard constraint is to ensure that workload is viable, cost efficient, and we follow the legal or regulatory compliance, because it acts as a strict guardrail for applications that simply cannot run or should not run on just any machine or nodes. Node affinity concept in Kubernetes is used with respect to hardware dependency, which is workload viability. Some applications require specialized underlying hardware to function. For example, GPU requirements. An AI machine learning model needs an NVIDIA GPU, and scheduling it on standard CPU node will cause the application to crash instantly. Also, for cost and licensing optimization and data sovereignty and compliance, meaning legal regulations often dictate the geographic and physical location of the user data. Geographic compliance, that is GDPR. European user data must be processed within Europe. So we can use hard constraint node affinity to force the pod onto the nodes physically located in the Europe West Cloud region. So it follows the geographic compliance GDPR standards. And for data privacy, some payment processing software might be legally required to run only on high security, single tenant or dedicated bare metal hardware. So node affinity hard constraint helps in those areas. That was about node affinity and kind. Now let's understand the importance of taints and tolerations in Kubernetes. Taints and tolerations is a similar concept to node affinity, meaning it is related to scheduling of the pod with respect to nodes, but taints and tolerations are quite different, meaning taints are applied to nodes. Think of them as repellent or the lock that restricts which pods can schedule on a node, whereas tolerations are applied to the pods. Think of them as the key that allows a pod to ignore a node's taint and schedule there. So taints are applied on the nodes, which makes them repellent to every pods other than the tolerations that are applied to it, and tolerations are applied to the pods. Pods that have tolerations applied can schedule anywhere and also on the nodes that have taints applied. So simply taints restrict every pods except the pods that have tolerations applied to it, and pods that have tolerations applied can be scheduled anywhere, even on the nodes that have taints applied. So it is to physically isolate workloads and protect the node health in a shared cluster. And there are many real world use cases with respect to taints and toleration. First would be dedicating expensive hardware, that is cost control. What if there exists a specialized node with expensive GPU for machine learning or massive RAM for databases? It exists for certain GPU resource allocation, not for regular applications. And what if a developer deploys a miner or a simple web application on it, and Kubernetes places it on that GPU node, wasting its resources and costing a lot in the cloud resources. So purpose of taint would be to apply it on the GPU node, which would be hardware GPU no schedule. Now regular applications are locked out, and that specific hardware or GPU resource is strictly reserved for actual machine learning workloads that hold the matching tolerations in it. that, and also to protect the system's infrastructure, that is cluster stability. We know that Kubernetes cluster has two components, that is control plane, that is the brain, and the worker nodes where applications run. What if a developer's web application has a memory leak and it crashes the node it is deployed on and takes down the Kubernetes master API with it? So the purpose of taints and tolerations would be that Kubernetes will automatically taint control plane nodes with the no schedule hard constraint, which guarantees that the user application never run on the cluster's brain, that is the control plane, which keeps the infrastructure safe even if the user's application crash. So simply it is to isolate the worker node applications that run on it to not utilize control plane for its use. That was about taints and tolerations, kind, and node affinity. Now let's actually learn how I performed all this practically. First, I switched into the resume matcher DevOps root folder and I performed the command to install the kind.exe, which is to install kind. I performed it with curl command. After it was successfully installed, I copied that exe file of kind and I pasted it in the local disk tools folder and I deleted it from the resume matcher root folder. Then I head back into the environment variables path and I added the tools/kind.exe folder into the path section of system variables. After doing it, I checked the kind version by kind.exe version and it was successfully installed. After successfully installing the kind, now it was to set up the cluster or create the cluster. First, I created the kind node YAML. You can see the YAML file. It is a multi-node cluster with one control plane, 3 worker nodes. I saved that YAML and I performed the kind.exe command to create the cluster. Command is kind.exe create cluster flag name with the name of the cluster you want to name. I have named it kind node and space the config flag, redirecting it to the kind node YAML which I just created. Space image flag. I have provided exact image which I want to use of the kind and it was successfully created. I confirmed it with the command kubectl get nodes -o wide and one control plane and 3 worker nodes were successfully created, meaning cluster was successfully created. Then we have to perform the node affinity concept. So we have to label the nodes with respect to certain labels. So I performed the command kubectl label node a single kind node worker with zone equals east, and for other worker nodes it is zone equals to west, zone equals to central respectively. So now we have 3 worker nodes that are labeled east, west and central respectively. So it is easy for us to label them in the deployment file for checking and verifying the node affinity concept. After successfully creating the cluster and labeling the worker nodes with east, west and central respectively, now it's time to build and push the image into the GHCR GitHub container registry. To do so, the first step is to create the Docker publish YAML file. This YAML file is used to build and push the Docker image into the GHCR. That means I decided to perform and build this image via GitHub workflows, that is GitHub actions. So I created that YAML file which is Docker publish YAML within the .github folder inside the workflows of it. So the root folder has .github folder. Inside that folder is the workflows and inside that workflows folder is the Docker publish YAML with these specifications. As the name build and push to GHCR branches is main. It runs on Ubuntu latest. Permissions are read for contents and write for packages. And here are the steps to build and push the image into the GHCR. After saving that YAML file, I also updated a Docker file so it supports the network configuration and timeout, so it efficiently performs the GitHub actions. I saved the Docker file and I logged into GHCR or GitHub container registry by performing echo and a personal access token which I have generated to log into the GHCR. Then to start the workflow of GitHub actions, I perform this command on the root folder, that is git add space dot with git commit -m, that is message flag, which is featuring add GitHub Actions workflow for multi-architectural GHCR push and git push origin main. I performed this command and I checked into the GitHub account and actions. The CI pipeline for this workflow was successful and it took 13 minutes to complete it. And you can see the steps, that is set up the job, check out the repository, setting up of the QEMU, setting up the Docker builds, log into the GitHub container registry, extracting the metadata, tags, labels for Docker, build and push Docker image, post build and push Docker image, post log into the GitHub container registry, and all these steps until it is complete job. It was 100% successful, and we can observe within packages that resume matcher DevOps image is successfully pushed into the GitHub container registry. We will use this GHCR image into our deployment file for deploying and exposing our application. After successful push of the image into the GHCR, next is to update the deployment file, which is resume matcher GHCR YAML with respect to node affinity. So as I mentioned, I applied the hard constraint node affinity, which is required during scheduling, ignored during execution. Worth noting is the values. It specifies east, which means our deployment file specifies the label as east, so it will be deployed into the node that has the label east in it. So after this, I performed the command kubectl apply the deployment YAML file, and I performed kubectl get pods -o and pods were successfully running, meaning resume matcher GHCR deployment pods, that is 2 pods, are successfully running. Now let's confirm if it is actually running on those labeled nodes. So I perform the command kubectl get pods -l app equals to resume matcher GHCR space -o wide grep command, that is to filter out with respect to resume matcher GHCR filter. That command showed that the pods with resume matcher GHCR are successfully running, and it also showed the name of the node, that is kind node worker. Now let's see the label on that node. I perform the command kubectl get node kind node worker, which we just saw, and space the flag show labels with the flag grep zone, and as we can see, it is showing the zone equals east, meaning we have applied the node affinity in the deployment YAML file by specifying east as the node label, and now the application deployment resume matcher GHCR pods are running on that labeled node. That was about node affinity and running our deployment application pods on that node with east label in it. Now let's confirm if the application is even running or not. Before checking it, I have created these configuration files. You can observe it. It has secrets, service YAML file, configuration YAML file, and 2 shell scripts as well. So you can observe the service YAML file. I have specified the image name with GHCR, GitHub container registry, and path of it. Then I created the secret by performing kubectl create secret Docker registry and naming that secret GHCR secret. Because the image pushed into the GHCR, that is GitHub container registry, is private, it is not public, so we must have GHCR secret, which is specified in the deployment file, and that secret will have the personal access token in it. So that secret will have personal access token, which will help deployment YAML file to access that private image pushed into the GHCR. After successfully creating the secret, I perform the command kubectl apply -f space dot into the kind folder that has all these configuration files. All of these configuration files were configured after this command. Then I confirmed the services that is running with respect to resume matcher GHCR. So I performed the command kubectl get service with the name resume matcher GHCR services, and it was successfully running on the port, that is NodePort. It has ClusterIP address and ports. Then I performed the command kubectl port forward deployment resume matcher GHCR with port 8080 mapped with 3000. So now the application would be running on the port 8080. As we can see, the application is running on the port 8080. Now let's test the application. I uploaded the resume You can see it shows the results, which is matched jobs. We can also observe the logs. It shows that the application is running. So by now we have applied node affinity with the label east. Then the pods with the deployment resume matcher GHCR were deployed on that label node, that is east, and the application was successfully running on that node. We have performed it with east label. Now let's change the deployment YAML file value with west. Previously it was label east, now we will do it west. So now pods, that is resume matcher GHCR pods, will be deployed on the nodes that has the label west in it. So I updated the deployment YAML file with west and I created the node affinity check shell script, so it is easy to perform these commands. So the shell script has the kubectl restart of the deployment YAML, and to get the pods with the application resume matcher GHCR grep filter with resume matcher GHCR, and to show the label on the node by performing kubectl get node with the kind node worker2, and show labels with the flag grep zone. I created that shell script. I performed and gave permissions to that script by chmod space -x and that script name, so it has permissions to execute it. By default it doesn't have permissions. And after that I ran that shell script by // with the shell script name, and we can observe that pods are now successfully running in the zone label west. Previously it was running on east, that is east labeled node. Now it is running on west label node. So that was about node affinity concept. We have successfully checked the east label and deployed application with respect to it, and we have changed that label from east to west and deployed application on that labeled node. Now let's understand the concept of taints and tolerations. For that I have updated the deployment YAML file by adding tolerations section in it. So we are applying the hard constraint, that is no schedule. So we have updated the YAML file with the toleration section. We have applied the key dedicated operator equal value db and effect, that is no schedule, which is hard constraint. We save that and I have performed the command kubectl taint nodes with specifying the kind worker node 2 space dedicated equals to db with no schedule, and it was successful. It showed node/kind node worker node is tainted. Then I performed kubectl describe node kind node worker node space flag pipe grep taints. We can see that taint equals dedicated db no schedule. Now let's do the taint toleration script for the same, and this script has kubectl apply resume matcher GHCR YAML for applying the deployment of the YAML file and restarting it, and to get the pods with the label resume matcher GHCR, the grep resume matcher GHCR, and to describe the pod with the name kind node worker node 2 pipe grep taints to filter out with that keyword taint. And I gave permissions to the script by chmod space -x, that is execute permissions for the script, and I performed and ran the script, that is /taint toleration.sh. Script was successfully running and it showed the taints, that is dedicated db no schedule, and the application deployment files resume matcher GHCR was successfully running. It is because we have applied toleration section in the deployment file. If we remove the toleration sections from the deployment file, then the application would be in the pending state because it is not exempted with the tolerations. To check that, I have removed the toleration section from the YAML of the deployment and I saved it. Then I ran the script again of the taint tolerations sh. We can observe that the taints is available, meaning it is dedicated to db no schedule, and now the pods of the resume matcher GHCR are in the pending state because it doesn't have tolerations in it. Tolerations gives permissions to run even on the tainted nodes. Now let's untaint that nodes and see what happens. So I perform the command kubectl taint nodes kind node worker2 dedicated equals db no schedule. Note that after this command there is a minus sign, which means it performs untaint. After performing this command, the node which we have tainted previously is now untainted, meaning there is no taints and the application would be running as usual. So I confirmed it by performing the same shell script again of taint tolerations sh. We can see the application resume matcher GHCR pods are running and there is no taints available or node taints applied. So simply, if we apply taints into a node, that node becomes untouchable unless we specify tolerations that gives it permissions to access that tainted nodes to deploy on that tainted nodes. So by now we have understood kind, taints and tolerations, and we have also understood the concept of node affinity. So, and also we have understood GitHub actions, and we have built and pushed into the private GitHub container registry, created a secret to follow the compliance and security. So we have dedicated a private registry to access images privately from that repository, and we have accessed that image by creating a secret GHCR secret which has personal access token, which gives permissions or accessibility of that image into the deployment file and other service files within our clusters. The topic is Helm. We will discuss what is Helm, and I will explain you step by step how I implemented Helm and deployed application using it. My application ResumeMatcher is a multi-tier Node.js application that has the front-end, back-end and database with API keys to help it run. I have used GitHub as a repository to pull and push my application deployment with the help of Helm repository and its charts and templates. We will discuss all of this. Let's begin. First, let's understand what is Helm. Helm is an open source package manager for Kubernetes that automates the deployment, scaling, configuration, and management of applications within a cluster. It functions similarly to a traditional operating system package managers like apt, yum, or homebrew, but it is custom built to manage complex Kubernetes YAML manifest as a single version unit. So simply, Helm is an open source package manager for Kubernetes. It helps in automating the deployment, scaling, configuration, and management of application within a cluster. The core problem Helm solves is when we deploy an application via Kubernetes, we would be manually writing and executing dozens of distinct and different YAML files like deployment services, configuration maps, and all of these YAML files, and perform the command kubectl apply to apply those and create a deployment pods. While this is a great step, but managing these files across different environments like development, staging, and production often leads to hard-coded configurations, duplication errors, and complete lack of deployment history. So Helm addresses this issue and problem by bundling the configuration files into customizable and parameter-driven application templates. So Helm charts, and building your application around Helm has certain templates and charts and values.yaml files. So you build your application around those parameters, so you don't have to change your deployment and other configuration files or many configuration files, and you only need to update or prepare values.yaml. I'll explain that while performing the project, but let's first understand the three big concept in Helm. Helm operates using three core components outlined in the Helm documentation. First is charts. Helm charts is a structured bundle of YAML template files that fully defines a set of related Kubernetes resources, or simply your resources of application. And second is repository. It is a public or private collection point where Helm configurations are stored, versioned, and shared. For example, it can be in the artifact hub or it can be into the GitHub repository. Third is release. It is a living active instance of specific chart or configuration of Helm which you have created, deployed into your Kubernetes cluster, meaning you prepare certain configuration files with respect to Helm and its templates, all of it, and that serves as a living active instance when we deploy that into the cluster. So you build your application around Helm, prepare charts, templates with respect to your default configuration YAML files, and push that into the repository, for example artifact hub or GitHub repository, and it builds a living active instance of that application. And you bring that application by performing Helm repo add or by Helm installing after adding that repo into your application or the folder using the CLI. Now let's understand what are the key benefits of Helm. First is dynamic template engine. Instead of copying entire YAML directories and its configuration for different server environments, Helm uses Go template logic, meaning you change a single file called values.yaml which is present inside your packaged application folder. That values.yaml is to produce or populate dynamically configurations like replica counts or environment passwords, meaning you would obviously be having certain YAML files before reaching the concept of Helm. For example, if you have deployed your application using kind and multi-node cluster or single node cluster using Minikube, so you would be having certain deployment files, ingress files, service files, and you certainly would have port forwarded at least, or you have created load balancer to run that application on ports. So if you have done that, you would be having certain YAML files. Now with respect to Helm, you don't use those YAML files or those all configurations directly, meaning you would update your existing YAML configuration to not have hard-coded values, meaning you will be preparing and updating all those YAML configurations to have placeholders or keywords, and those keywords would be directly added into the values.yaml file. I hope it makes sense. So values.yaml would be having that keywords, and you specify those values in the values.yaml, meaning you don't have hard-coded values inside a deployment or other configuration files. You will be having a single values.yaml file that would have those values specified inside it. So all those configuration files would act as a template to the values.yaml file that has the actual values and keys for that configuration files. But here's another thing. If you are intending to create or prepare values.yaml file, that's great. You can add all those values, meaning environment variables and everything. But if you are preparing it and planning to deploy it on the GitHub repository, which is to be public, to perform Helm project of this, then your API keys will get revoked if it is a public repository. So simply values.yaml will have all those values that are required or to run. Now, if you plan to have a public repository and you add those values.yaml inside a public repository, meaning those API keys will get revoked, and it is not a best practice to have your secrets or API keys exposed into a public repository. So instead, you can create values.yaml with all of the values in the deployment configuration or other configurations, but you can create another YAML that would be values override, that would have all the API keys or confidential variables in it. So you have values.yaml that would have configuration related information of your other configuration files, but doesn't have the confidential or secret or API keys related information, and you will add certain placeholders and variables inside that section of API keys or confidential information that is not supposed to be in the public repository. So you would create another YAML in the root folder that will be having API keys or such values that are confidential, and that would override the values.yaml. So you will be having values override.yaml to override the values.yaml file. So meaning you will be deploying or pushing your application on GitHub, but you will not add values override that would have the API keys in it. So you will add values YAML, all those other files, and you will create values override YAML in the root folder, but you will only use that values override as a key to the log that is your application. There is a certain command I will explain you in the project section. We will install the application by using values override as a key explicitly locally. So you will not have values override deployed anywhere. You will have that file values override locally, and you will use that file as a key to override and install application with respect to it into your local machine. So that way you have your secrets or API keys related variables defined in values override, and it will run your application smoothly, and it will not give you errors or revocation of your API keys if you had them publicly in the open repository or public repository. I hope it makes sense, but I will explain you further in the project section explaining this. You will get more idea of it. So simply you can understand Helm and its repository concept as place store. Instead of building or preparing application and its deployment files one after the other for new projects, we can package the application, prepare Helm charts and everything. We can test that by running the application on port forwarding or load balancer. If it is working, that's great. And we push that application into the repository, and we prepare the Helm repository and Helm install. So what you have prepared would be like an application, just like an image, meaning when you deploy into the Helm repository and also install your application with respect to it, instead of you preparing all those deployment files in other projects, you would directly be running the pods while installing from the Helm repository. I hope it makes sense. So you will not be copying all those configuration folders files and add them into your new project. Instead, you will package the application once for all and you would perform Helm install, and you will have that pods and deployments running while you perform installation of your application with respect to Helm repository. So that was about kind of theory part of how Helm repository works. Now let's understand and see how I have done all of this step by step. So first step to perform Helm or to begin this project, to create the cluster, I'm using kind multinode cluster. As you can see, this is the YAML file of kind node YAML, which means it has one control plane node, which is master node, and 3 worker nodes. Then I perform the command kind.exe, create the cluster with respect to the configuration file which I have created, that is kind node YAML, and the image I am using would be kindest node version 1.27.3, and it is created. We can perform and confirm it by kind kubectl get nodes -override. The nodes are up and running. After we have created the nodes and the cluster, let's now create Helm repository folder, and inside that Helm repository another folder, that is resumatcher. I perform this on the root of my project folder, meaning after this command I will be having a folder that is Helm repository. Inside that folder would be another folder resumatcher, and cd Helm repository to get into that Helm repository. After this, the command is Helm create resumatcher. Resumatcher is the folder which I have just created inside the Helm repository. As you perform Helm create with respect to your project or folder name, this command will create templates Helm ignore chart.yaml and values.yaml. I already had deployment and other configuration files from my other projects of resumatcher, so I have just copied and pasted them in the template folder. And one more thing to remember is I have not provided all those YAML configuration screenshots or details how I updated it, but simply you have to update these configuration files of yours with respect to your application in such a way that it redirects them into the placeholder values of values.yaml, meaning you will have certain keywords. Instead of you mentioning or specifying it in the deployment YAML, you will redirect those values inside values.yaml. So values.yaml will have all those specified details, not your templates folder. So as it says, it is a templates. It will have the structure of your application, not exactly the values, and values.yaml will have the actual values. And if you have certain confidential values such as secrets or API keys, you can create another YAML file which is values override, or you can name it anything .yaml, which will act as a key value install, and it will have all those confidential keys and related information which you will not add them into your public repository. It will act as the key for you to perform and run or install Helm repository locally. So simply this is the template folder. Now next you can see I have pv YAML, that is persistent volume claim YAML file, and as I mentioned values.override YAML file, which has all the related API key information of my application, which I don't want it to be present in the public repository. This values.override YAML will act as a key to my application, and .git ignore has values.override.yaml mentioned, so it doesn't accidentally push this file into the GitHub repository. As you can see, .git ignore has this values.override YAML, so it doesn't accidentally add this YAML file into the GitHub repository. And now we will understand the values.yaml file. As I mentioned, values.yaml file simply consists of values you don't specify in the other configuration files inside templates folder. So typically your deployment configuration or other configuration file has all these details which is to be mentioned inside the values YAML. So templates only have structure and templates or with placeholder values, and this values.yaml will specify those information which is missing there. So your Helm repository will rely on values.yaml to prepare the application. This values.yaml and all this template thing is to simplify the deployment and creation process. Typically you would need to update all those configuration files one by one, but in this case you only need to update the values YAML file and its values, meaning you can scale up or down, change the CPU capacity, memory capacity by just changing values YAML file, not your other YAML configuration files. So first it is app replicas, meaning 2 parts of application deployment. Image is within the repository GHCR, GitHub container registry, my username Kaif Khan, and resumatcher DevOps. So I already have pushed image of my application in a private GitHub container registry, and I have mentioned that tag is latest image pull policy always, and image pull secrets, that is GHCR secret, meaning I have created a secret GHCR secret that has personal access token to access this private GitHub container registry. If it was a public container registry, I wouldn't need GHCR secret to access it. As it is private container registry, I need GHCR secret. It contains personal access token to access this repository. And these are related to ports, environment variables, resources, CPU, memory, database related information, image, PG vector, PG50, persistent volume claim, PVC, that is name, Postgres, PVC, storage class, standard. And here is the important part. Here I mentioned secrets with all those placeholder values, that is DB secret, Google API secret, and all this information. Now you would assume that you should have mentioned the secret values here, meaning you should have mentioned the API keys, DB secret here, as it is a values.yaml file. Your observation is great, but as this deployment file or values.yaml file will be in the GitHub repository public, even private, so it shouldn't be that your values are exposed that way. So instead I created the values override.yaml that has all those secrets, keys, and its values mentioned in it. So it is the file that is not present in the repository or anything. It is only present in the root folder, and I can only access it locally to install it with respect to Helm. And next is configuration map and its information and its values. This is all related to database configuration. Service type is NodePort. So that was about values.yaml file. I mentioned that it has secrets section which doesn't explicitly specify the values of secrets, meaning it doesn't have API keys and everything or DB secret mentioned in it. It has values override that overrides this as a key which I will use to access the application locally. After this, the command is helm package resume matcher, and you can see successfully packaged the chart. And next is helm repo index dot the URL with respect to my GitHub repository, that is helm repository. After we perform these commands, we can observe that resume matcher tar gz while is present and index file is also created. After this, now it's time to push application into the created empty GitHub repository, meaning I already have created Helm repository which is empty. Now we will push those configuration and these files inside that repository. So first let's confirm the origin. We can observe that it is present in the resume matcher DevOps origin. We need to change it to Helm repository in order to push those files. So I performed git remote set URL and this command. We can see that now it's changed to Helm repository. Then I performed git add dot git reset values dot override dot YAML, meaning it will add everything but it will not add values dot override YAML. As I mentioned, reset command. We can see git status that on branch main these are to be committed, meaning all these files. And I performed the command git commit -m with the message performed git push without values override dot YAML, because it has API keys and confidential information which is not to be present in the repository. It should only be present as a key inside your local folder. After committing the git, then the command is to push origin main force. It was successful. However, as you can see in the Helm repository of my GitHub, all of the files which is inside the resume matcher DevOps, not specific to the Helm repository, all of it is pushed inside my Helm repository, which shouldn't happen. My only aim was to push Helm repository which had 5 to 10 files in it, but it has pushed all of the root folder of resume matcher DevOps inside this Helm repository. In order to fix it, I perform the command git subtree split prefix Helm repository be Helm repo branch, and I created the branch Helm repo branch. Then I pushed origin Helm repo branch main force, meaning only Helm repository folder will be pushed. After this, we can see that all of the other files are removed and we only have the required files, which is resume matcher and all these folders index.yaml. Inside the resume matcher, we will be having templates folder and other folders as well. After you successfully add the required files of yours within your created repository of Helm, the next step is to get into the pages section of your repository and update the branch section to main. After you change it to main, save it. After this, the next command is to Helm repo add. You can give any name I have given it my application name, that is ResumeMatcher. You can give it ResumeMatcher version 1, your application name version 1, version 2. Next, it is to specify your GitHub account username. You can change the username with your username. I will be specifying it with Khan with the Helm repository and Helm repo update. After performing Helm repo update, it is successfully updated. I performed Helm search repo ResumeMatcher. ResumeMatcher is present inside the repository. After we successfully added our application into the repository and locally do your folder or application. Next is to perform the installation. The command is helm install. The name you want to give, I have named it ResumeMatcher service space ResumeMatcher slash ResumeMatcher -f values.override.yaml. As I mentioned before, I haven't specified explicitly all the values inside the values.yaml. So I needed values.override.yaml to act as a key that has the specific and the required API keys and secret information. So to do that, I have performed -f values.override.yaml, meaning it will install with respect to the values.override.yaml files. It was successful and it was deployed, but we can see the pods are still in the pending state, meaning we have specified the API keys and secrets with their names in it, but we haven't actually created secrets. We can see that one secret is missing. We have DB secret, API secret, CX secret, which is great, but one secret, that is GHCR secret with respect to my image GHCR private repository, is missing, meaning private image in the GHCR which I am using to build the application here is missing. Even if one secret key is missing, yours will be in the pending state. To fix that, I performed the login first into the GHCR by echo space personal access token and this command with my username, password, and it was successful. Then I created GHCR secret, which is present in the values.yaml and inside the values override.yaml. After it was successfully created, then I confirmed the pods by performing kubectl get pods -w. We can observe that now the pods are successfully running as we have created all the required secrets, and it also has the API keys that we have specified inside the values override.yaml. After we observe that pods are successfully running, the next command is to perform kubectl port forward service slash ResumeMatcher app port 8080 map to 3000. Application deployment would be running on the port 8080. As we can see in the local host 8080 application UI is available. I will add my resume and see if it works or not. It was matching the resumes and it provided the results, that is match jobs. We can see the application is successfully running while installing it with respect to Helm install. We can see the company name and all the job. Let's see the logs. I performed kubectl logs -f with the application pod. We can see the logs Google API key, meaning API keys is loaded and all those information, indexing, embedding with respect to the application. And in the next talk section, we can see that the title, the job title and other information is available. And it also shows my name, that is Khan. It is due to the database configuration I have done. So I successfully managed to pull off this Helm repository charts and this concept. You are seeing just the result of the application, not the debugging, which I have performed and failed few times, meaning it took me around 1 week to actually make it happen. I had a deprecation of the API keys while performing this project, so I had to rewrite all the configuration of my application in the backend and rebuild all these images. First I rebuilt a Docker Hub image and I pushed it there, and I created CICD pipeline of GHCR private image, which you have seen in the values YAML. I built and pushed that image after fixing the API keys and the backend issue. It took me like around 1 week to even realize that it was the API keys that was causing the issue. So it was a really roller coaster ride while performing this project. I hope you understood and had the idea. You can let me know in the comments if you have any questions. The topic is understanding the concept of Kustomize. I will explain you the definition and theory of the Kustomize and a practical project in which I will be implementing the concept explained in this theory part. So let's begin. First, let's understand what is the definition of Kustomize. So Kustomize is an open source template-free configuration management tool for Kubernetes that allows you to define and manage applications resources natively. Instead of introducing a complex templating language like Helm, it uses a purely declarative plain YAML YAML approach to customize and layer environment-specific configuration options without altering the original files. Basically, when we implement the concept of Helm, we are certainly providing or using more effort in preparing the YAML files, even though we are thinking that we are only doing it for once. In short, even if we deny, we are still preparing the template folder by preparing the YAML files in Helm, which means we are providing a little more effort to prepare the repository or whatever. But Helm has its own benefits. For package management, it can be great, but with respect to only manipulation of YAML files, with respect to environments like production, development, or base, there comes the concept of Kustomize, where we don't need complex configuration like Go language to prepare the deployment files, which is the case in Helm. In Kustomize, we don't need templates, and it's a configuration management tool which allows us to define and manage application resources natively. So irrespective of Helm, which has Go language templates or YAML files which are complex to prepare it for once, in Kustomize, it is purely a declarative plain YAML approach to customize and layer environment specific configuration options without altering the original files. This is just a definition. You will understand it better when I explain you in the tutorial or practical part later in this video. That was a definition. Now let's understand the core concepts in Kustomize. First is base. Base is a directory containing raw Kubernetes manifest. For example, deployment YAML file, service YAML file, and every YAML file which you prepare to run your application. And also it contains a additional YAML file, that is customization.yaml. That customization.yaml file represents the single source of truth for standard generic settings. Next is overlay. This is a separate directory containing a customization.yaml file that refers to the base which we just created before overlay. Overlays define target environment variations such as development, staging, or production, and patch specific fields on top of the base. Third is customization.yaml file. This is a central configuration file that lists resource fields, references bases, and instructs Kustomize on how to transform the manifest files. That sounds too complicated, but I'll explain you in a simple way. Kustomize has the concept which is base, overlay, and customization.yaml files. These three are the core concepts. First is base. Base is just a folder in customization where you keep your deployment or all the YAML files which you have already created. Meaning, if suppose you have at least deployed one application or by performing Kubernetes concept of YAML files or whatever. If you have watched my other videos where I have implemented tons of projects with respect to Kubernetes, even if you have done one of those projects in your own application, then you would have certain YAML files that is already present in your folder. So that YAML files would be considered as the base inside the base folder. On top of that, there exists another YAML file that is customization.yaml file. I will explain customization.yaml file in a bit, and that was about base. Now let's understand what is overlay. Overlay is the same as base. It is another folder that is named as overlays, but instead of having all the YAML files present which was in the base, it doesn't have those YAML files. It only has customization of YAML file and the YAML files which you want additionally for patching or changes you want to see from the base configuration. Meaning, if you are not happy with the base configuration and you want to have certain replicas or whatever you want to change, you specify that specific YAML file by creating a patch YAML file inside the overlay folder, by creating a development production environment folder, and inside that you can define another YAML file with patching of the replicas. And if you want some more changes like for service ports change or changing of like load balancer or ClusterIP or NodePort, whatever, you can create another YAML file to change from base to the overlay of the development folder. I hope you get the point. And you can create another overlay inside the overlays folder, meaning that was our dev, and you can create another staging folder in which you can specify more changes into the base folder. So simply base folder is the reference point where you provide changes in the staging folder, and you have customization.yaml file that references that you are using which YAML file from the base folder. I hope you get the point. So overlays will be having folders that would be naming development, staging, or production, and you will define the YAML files with respect to the change you want in your deployment or services. You will understand it better when I will show you the practical session. It will be really simple when I do that. But as of now, you can understand this as a theory concept. Third is customization.yaml file. This is a central configuration file in which we list the resource fields, reference bases, and instruct Kustomize on how to transform the manifest. Simply in the base folder, there exists customization.yaml file in which we define all the resources we are specifying in the base folder. Meaning if you have added deployment, service, configuration, ingress, YAML files, you will specify those in the customization by mentioning that you have these in your base folder. So that was about definition and understanding what is base, overlay, and customization.yaml file. But I can explain you in a better way by giving you an example. Meaning you can imagine how a professional painter paints. Meaning they would not entirely paint on a single sheet of paper and consider that as their original or end product of their painting. A professional painter would paint in a way that is, first they would create an outline of their painting that would serve as a base. So they would be creating outline in a single page that would be the base of the painting, and next they would be using another sheet of paper above it that would act as an overlay. So they would enhance that base in the next paper by using base as a reference point to enhance the painting. And they can also add a next paper above that second paper of overlay, so they can enhance the painting even more. That is the simplest analogy I can give for you to understand the concept of customize. We are using base as a base configuration to enhance or customize our application with respect to the environment, that is development, staging, or production, by creating a folder named overlays where we use base configuration YAML files as a reference point to update or enhance or change the configuration by providing or creating new YAML files and referencing those base YAML files in the customization YAML file and adding the patches inside it. I hope you get the point. You will understand it better when I show you in the practicals. But that was about the theory part of understanding what is customized and definition, key features, core concept, and analogy. With respect to my application, that is multi-tier database, front-end, back-end, Node.js application, that is ResumeMatcher, I first created a customized folder. Inside that customized folder, I created another folder that is base. Inside that folder, I pasted YAML files which I already had from my previous working deployment of the application. Meaning if you already have the deployment YAML files of your previous deployments, you can simply paste those all working YAML files inside the base folder. I did the same. I added all these. Apart from adding all these YAML files, I also created a new YAML file that is customization.yaml file. You can observe in this YAML file of customization, it has API version customize.config.kdes.io/v1 beta 1. The kind is customization. Resources, as I mentioned, we will specify the resources which we are using, or at least what we have mentioned inside or what we have added inside the base configuration files. As we have added ConfigMap, DB secret, Google API secret, Google CXID secret, Postgres, PVC, ResumeMatcher, GHCR, service YAML. And as I've added all these YAML configuration files inside the base folder, I need to specify them inside the resources of the customization YAML file. Here, ResumeMatcher GHCR is the deployment YAML file. That's it. We have created the configurations which we need to create. This is the basic configuration. You can enhance it even more by adding more details which you can find in the official documentation of Kustomize. As of now, I only needed these to perform the task which I intended or needed to do. So next is to perform the command. I performed kubectl customize./base. You can see the YAML configuration of all our YAML files. Then the command is kubectl apply -k./base. You can notice that we have not mentioned -f, which we usually do while performing kubectl. When we perform customize, we change the command from F to K. So the command would be kubectl apply -k./base. So we are applying the base folder. It was successful. As you can see, everything is configured or unchanged, meaning it is configured or applied. After applying, we can confirm it by the command kubectl get pods -w. We can observe that all pods are up and running. This is the default configuration of my application, meaning I had the default configuration in the base folder of having 2 pods for deployment and 1 pod for DB. After I observe all pods are running, I perform the command kubectl port forward service resumatcher GHCR service on the ports 3000, meaning the application will now run on the local host 3000. Also, one more thing to notice here is that the deployment configuration or service of the application in the base is NodePort, not ClusterIP. Usually when we perform port forward, we do it if the service is of the type ClusterIP. But if it is on the service type NodePort, the application would simply run when the pods are running. If it is on the service type ClusterIP, you need to perform port forward command to run the application on the specified ports. When the service type is of NodePort, it will always run when the pods are running on the specified ports of your application deployment file. But my application was of NodePort, but still I performed the port forward. So I performed the port forward, and after I uploaded the resume, the results are visible, meaning the application is up and running. We can observe the logs of our base configuration. Application is up and running. We can see the Google API key is loaded and all the embedding and backend stuff is also working. So that means our base configuration is configured and our application is healthy and running on the base configuration. That is a great, but that is the base configuration. Now we need to perform overlays concept where we can create development production environment, meaning we create development folder, we can create production folder, which will have certain changes, patches by referencing to the base configuration. Let me explain that with an example. Now you can see that I have created the new folder inside the Kustomize. So Kustomize is a root folder. It will have base with those configuration, and Kustomize will also have overlays folder, which will have another folder that is development, that is dev. Inside that dev folder, I have created deployment patch YAML, customization YAML, service patch YAML file. Here deployment patch and service patch is the changes which I want to have or which I intend to have from the base configuration. So meaning the scenario would be like I am not certainly convinced with the base configuration and I want to change it right now. So I have to change it by referencing those in the customization YAML files and the changes which I want. I want change in the deployment patch and service patch. So I want change in deployment and service. So I will create these two YAML files with customization YAML files. We can observe the deployment patch YAML file. So this is the deployment patch YAML file. The API version is app/v1, kind is deployment. The metadata and the name is resumatcher GHCR, namespace its default. The change I want is with respect to replicas. Previously it was 2 replicas, now I want only 1 replicas. And image pull secret is GHCR secret, meaning I have a private image repository GHCR. I will create a secret and access that image from the GHCR. As you can see, the image is from the GHCR Kyverno resumatcher DevOps latest, which is private GHCR in the Github container registry, and I have specified the resources that this deployment should use, that is CPU, memory, LAN limits. That is about the deployment patch. You would assume that this looks like the usual lengthy deployment YAML file. It doesn't look like we are doing something really effortless. But let me explain you. This is not a complex YAML file. The actual YAML file of my application, which is in the base folder, has even more information mentioned here. So this is just a reference point with a change I want to see in the replica set. So I only want 1 replicas in the development environment. Next is service patch YAML file. Here I defined that API version is version 1, kind is service. I want change in the service configuration. So metadata would be resumatcher service name, and selector is resumatcher GHCR, type is ClusterIP, ports is defined same as it is defined in the service YAML file. Here the thing to notice is that, as I mentioned, base configuration had the service type of NodePort. Here I want to have a change in the service type, so I changed it from NodePort to ClusterIP in the development of overlays. And this is the customization YAML file. The kind is customization. Resources, it is referencing to the folder of base, that is //base. Patches means changes which I want to see. Target, kind, that is service, name, resumatcher service, patch. With respect to the configuration of patch segment, I have not used basic strategic merge patch, which is usually used while performing customize, because the change I want to see in the overlays development environment from the base configuration is kind of complex, like changing the port or service type, which is kind of like a immutable feed that has the potential to break the logic or to not let it work. So to prevent that, I have created patches segment for only the service patch by using the concept of JSON 6902 patches. So these patches has the standard for replacing, adding, removing, moving, copying, testing, where replace will override the value at given JSON pointer path, add will insert a new value at the specified path, remove will delete the specified key or the element, move, copy or test. These are other supported benefits or operations to shift the values, copying the path and verifying the existence. We can use JSON 6902 patch when we are performing immutable or logic where the application can break. So I had to use this JSON 6902 patch with respect to the service ClusterIP change. So I performed the configuration by OP replace. I want to replace it with ClusterIP. Previously in the base it is NodePort. I want to change it with ClusterIP, and OP replace. It is a path that is selector. Selector is resume matcher GHCR, which is same. Simply we are specifying or hard coding these values in the development. Resume matcher GHCR is the same in the base, but we are still specifying so the application doesn't break. And we are performing OP replace with the same values as the base. So the application is hard coded and has the basic configuration files intact, so the application runs. That was about the service configuration by using JSON 6902 patch. With respect to deployment, increasing the replicas to 1 from 2, I have implemented the basic usual strategic merge patch, meaning usually we would be using this patch, and when certain configurations are immutable that can break the logic, then we switch into the JSON 6902 patch. Now for deployment patch, I have specified path, that is deployment patch.yaml. Target is kind deployment. I want to have change in the deployment, and the name is resume matcher GHCR. For basic strategic patch, we don't specify the immutable or changes which we want to see in the customization YAML file. We just reference the YAML file that has the configuration details. As my deployment patch YAML file has the configurations of change, that is one replica set, I have patched or created a patches with the path, with specifying the path, that is deployment patch YAML file. Target, that is deployment, I want change in the deployment, so it is a deployment. The name is resume matcher GHCR. So that is the customization YAML file of development environment inside the overlays. As we have prepared these YAML files, now it's just a simple job to apply and run our application. Next is to apply the command, that is kubectl apply -k overlays/dev, which will apply the dev configuration YAML files. Now one thing to notice here is that we haven't specified DB secret YAML file, API key YAML file, CICD, Postgres. All these YAML files we haven't specified in the overlays dev folder. As I've shown you, we only had a patch for deployment and patch for service type and customization YAML file. But still we are seeing changes or configurations in overall YAML files to run our application. Meaning, as we have referenced our base YAML file configurations, the customization YAML file, so it is referencing all those information from the base and only patching or changing what we have only specified in the deployment patch and service patch, and details we have specified in the customization.yaml file. So it will use all the information, all the configuration from the base configuration YAML files of base folder and only apply the patch change which we have specified in the development folder YAML files. I confirmed it with kubectl get pods. Pods are running, and we can observe that only one pod is running for resume matcher GHCR, meaning previously it was 2 pods or base or default configuration YAML file. Now it's only one pod that is running on the deployment side, meaning our patch has worked. We have changed the replicas from 2 to 1 and it is successful. I confirmed it with the command kubectl get deploy resume matcher GHCR. We can observe that only a single pod deployment is running. I wanted to check the services to see if it is running on ClusterIP, which we applied the change for. So I perform the command kubectl get svc, meaning kubectl get services. We can observe that resume matches service is now of the service type ClusterIP, not default that was NodePort. So our change from NodePort to ClusterIP was also successful. Now I wanted to confirm the endpoints of that service, resume matches service. I perform the command kubectl get endpoints resume matches service. We can observe that endpoints are also visible and available, meaning we can now perform the port forward to access our application on localhost. Then I perform the port forward command, that is kubectl port forward service slash resume matches service. Ports are 3100 mapped to 3000. The application would run on the port 3100. I head back into the local host 3100 and I uploaded the resume. We can observe that the results are available with respect to the resume, meaning the application is successfully running without breaking anything. I confirmed it with the logs of the pod. We can observe that the application is successfully running with all this embedded or backend information available in the logs of the application pod. So that was about the bare overlays development environment. Now we can also create another environment as we wish. If you want staging environment, and you can create another patch base referencing to the base configuration and the change you want to see. Now I wanted to create a production environment patch. So I head back into the overlays folder, which already had development deployment files of before. Then I created another production folder, that is prod, inside the overlays folder. This also has the customization YAML file, deployment patch YAML file, service patch YAML file, meaning YAML file has the same name, but the configuration will be different here in the production environment. Now, with respect to the deployment patch, I only wanted to change from the replicas 1 to 3. For the base configuration, it is 2, and for development overlays, it is 1, and for production, I wanted it to have 3 replicas and increase in the memory CPU. Other than that, all the details of the configuration is same. Then for change in the service type, I wanted it to have service type load balancer. In the base configuration, it is NodePort. In the development environment, it is ClusterIP. And for production, I wanted it to have load balancer service type. Rest the configuration is same as development. Then customization YAML file is still the same. I only changed it with the value load balancer. Previously it was ClusterIP, and everything is same. So now by default, Kubernetes in Docker, that is kind, doesn't support the endpoints for service type load balancer. So now in order to have service type load balancer active, or at least mimicking the service type load balancer, we must create namespace and install MetalB. So MetalB is simply an open source network load balancer implementation designed specifically for bare metal Kubernetes cluster. So when we run Kubernetes on public cloud providers like AWS, Azure, GCP, the cloud provider automatically provisions or provides us with a network load balancer type when we deploy a service of load balancer. However, an on-premise or bare metal environment, or simply in our case that is kind, or if you are using Minikube, this native automated integration, that is load balancer service type, is missing. That will leave our services stuck in the pending state. So MetalB solves this exact issue by integrating directly with our standard local networking equipment. Simply it will provide the service type load balancer. To perform that, I perform the command kubectl create namespace MetalB system. So it created the namespace MetalB system, and I installed the MetalB by performing kubectl apply -f with the path of installing the MetalB. You can use the same command to install and perform the MetalB. It was successful and configured. So next was to confirm the network of kind, subnet. I performed the Docker network inspect kind with respect to subnet. So I was getting the information with respect to the subnet name. Now I had to create another YAML file for MetalB configuration. So I have not created this YAML file on the customize folder. I created this in the main or the ultimate root folder, that was resume DevOps. Resume DevOps had the folder Kustomize, where we performed all of the before configuration and folders. But to perform or configure MetalB, I head back into the root, that is resume DevOps, and I created a new folder that is cluster add-ons. Inside that, I created the configuration YAML file of MetalB config YAML. Now, as we can observe, this YAML file, it has the API version with respect to the metalb.io v1 beta 1. Kind is IP address pool metadata, that is referencing to the namespace that is not default. It is MetalB system which we just created. Name is kind pool. Specification, we have specified the address. API version metalb.io, same. Kind is L2 advertisement. Metadata referencing your namespace MetalB system. Name is kind advertisement. Specification is IP address pools kind pool. You can also use this same YAML file if you want to configure, or there are other configuration templates available with respect to MetalB. You can also use those YAML configuration of MetalB. You don't need to scratch your head around how to create this YAML files. You can get all those templates and references to prepare this configuration YAML file, which is not so complex if you use Google search and those templates available on the official documentation. So I perform the command kubectl apply -f with respect to the configuration metalb config.yaml inside the cluster add-on folder. It was successful and it created IP address pool metalb.io kind pool, and it created advertisement metalb.io kind advertisement. Now, since we have successfully created or built our own service type load balancer using MetalB and its configuration YAML files, we can now apply our overlays production folder. Now I head back into the Kustomize folder again and I perform the command that is kubectl apply -k overlays production. Now again, it referenced to the base configuration of the Kustomize base folder, and it used all the other configurations of base and also configured our new or patched deployment and service YAML files and customization YAML files. I confirmed the number of replicas of resume deployment pod. I perform the command kubectl get deploy resume GHCR. We can observe that it is not 2, it is not 1, it is 3, and 3 replicas are up and ready, meaning our deployment patch worked. Now I wanted to confirm the service type change. It should be load balancer. I performed kubectl get services by performing kubectl get svc. As we can observe, resume service is now of service type load balancer. Previously it was ClusterIP. By default it was NodePort. Now I wanted to confirm the endpoints to access it on the port forward. I performed the command kubectl get endpoints resume service, and the endpoints were available, so that means I can access the application by port forward. Then I perform the kubectl port forward service /resume service with the ports 3100 map to 3000, meaning the application will now run on the local host 3100. Then I head back into the local host 3100 and I uploaded the resume, and it was successful. The results were available with the matching jobs. I confirmed it in the logs, which means the application is healthy and up and running, which means we successfully configured production, deployment and service patch. So that was about understanding customization theory, customization concept in practical. I hope you got an idea of basic understanding, at least while I explained you the concept of production, development, base, overlays, and the definition core concept of customization. Summarize the video. Base configuration had replicas of 2, meaning 2 replicas or 2 pods of the deployment resume would be running, and it was successful. And by default, or the base configuration had the service type of NodePort. So to change it, to create a patch or to have change in the development overlays, we performed or created deployment patch and service type patch, and we performed and we aimed for the change in those areas, meaning we wanted to change deployment from 2 to 1 and from service type NodePort to ClusterIP, and we were successful in doing that. The application was up and running with respect to development overlays. Then with respect to production overlays, our aim was to change from base configuration that was NodePort into the service type load balancer. We installed and created configuration of MetalB to have the service type load balancer, which is inherently or by default missing in a kind or Minikube environments, and we perform the change in the deployment of the replicas from by default base configuration that was 2. We wanted to have 3 and increased memory and CPU capacity as it is a production environment. We were successful after we performed the apply command and the application was up and running. So by default it was NodePort. We changed it to ClusterIP in the development environment, and we changed it to load balancer in the production environment, and we have changed the replica set. So that was about the concept of customization, theory and practical. I hope the lesson and this concept was insightful to you. The topic is understanding KEDA, that is Kubernetes event driven autoscaling. I will explain the theory part of it and as well as a project in which I will do or perform the practicals and do the KEDA project. Let's begin. First, let's understand what is the full form of KEDA. It is Kubernetes event driven autoscaling, which means KEDA is an open source CNCF component that automatically scales container workloads in Kubernetes based on exact number of events waiting to be processed. It safely extends native Kubernetes autoscaling beyond CPU and memory. So simply, KEDA or Kubernetes event-driven autoscaling is a component in CNCF or component in which we use or enhance the concept of autoscaling. We know that Kubernetes offers autoscaling, which is great. Like, it offers autoscaling, which means if certain resources and CPU memory is, it will create new pods and resources. Eventually we're doing autoscaling. Kubernetes does it, which is great. But event-driven autoscaling is an enhanced concept where Kubernetes event-driven autoscaling KEDA performs autoscaling where it is triggered by an event, not due to CPU and memory, which is a part of it, but it is triggered by events, not solely due to CPU and memory, which is the default of Kubernetes without KEDA. So what are the key features and use cases of KEDA? Unlike traditional autoscaling, which only checks pod resources usage, KEDA, that is Kubernetes event-driven autoscaling, continuously monitors over 60 external event sources. It can be either Kafka, RabbitMQ, AWS SQS, Azure Service Bus, and Prometheus, and all other external event sources. This simply means that it doesn't operate solely on CPU utilization or memory utilization, which is the default of autoscaling in Kubernetes, which means that if we would be performing or adding certain details in the YAML file, that would mean if certain threshold of resources are hit, pods must be created after certain threshold is hit. It can be either 80%, 70%. It depends on your needs. If that certain threshold of memory or CPU is hit, then new pods are created, which is default of Kubernetes autoscaling concept. But we can enhance that autoscaling by making it event driven, which is simply to provide better user experience rather than user waiting for 1 or 2 minutes more. You can reduce that to few seconds depending on how you create or manage events. So it offers scale to 0, meaning KEDA supports scaling applications completely down to 0 when idle, saving significant cloud compute cost. So if your application has certain microservices or services where it doesn't need to be present when no user is using it, meaning if there is no one accessing that resource, there should be no point of that resource to exist. If that is in your application or your website, then event driven is a great concept to implement. What it does is, if that microservices is to be triggered or is to be present in the queue of access, then KEDA will detect that and it will trigger the event driven autoscaling, which would create pods depending on how much queue or how much traffic is present, not specific to the threshold of CPU and memory, which is the default of pods. That simply means if it was usual default scenario of Kubernetes autoscaling, that would mean a single pod to be present. It can't be a 0 pod, and certain threshold of 80% or whatever, that must exactly be hit, or it must hit that threshold in order to trigger a new pod or autoscaling. Whereas with respect to KEDA, it is not like that. With respect to KEDA, it is somewhat like it is triggered by events and traffic or queues that is present, which is kind of related to memory or CPU, but it is not limited to it. It is just like traffic is being in the queue or in the backlog, so it triggers with respect to that traffic being present, which necessarily shouldn't be like it is occupying certain resources. It could occupy, but Kubernetes autoscaling is a reactive approach, whereas KEDA event-driven autoscaling is an proactive approach to autoscale. It is event-driven, meaning as soon as an event enters the queue, example a new message or an API request, KEDA will instantly scale up the pods required to process the load. And it is native integration. It works alongside standard Kubernetes mechanism like the horizontal pod autoscaler HPA, translating our custom metrics into scaling instructions. How does it work? KEDA operates using two main components, which is KEDA operator and the metrics server. There exists scaled object CRD. We define a custom resource in our cluster called scaled object. This maps our specific deployment to an event source and sets minimum or maximum replica boundaries. Monitoring. KEDA polls our event source to see how many events are pending. Then exists autoscaling. KEDA feeds this metric count into the Kubernetes horizontal pod autoscaling, that is HPA, which then scales our pods up or down accordingly. So simply it has the core components of Kubernetes and it uses it in order to provide enhanced user experience. So it is not different from Kubernetes, but it uses core of the Kubernetes autoscaling concept and provides enhanced or better user experience related to scaling and availability. That was about the theory concept and an overview on KEDA as an open source service for event-driven autoscaling. Now let's understand the practical of how I performed KEDA concept as well as cron. So first, it is the root directory of my application, that is resume DevOps, and I created a new folder in which I added the default or the configuration YAML files, simply the YAML files of my previous project that was already working. So these are the default YAML files of my application, which include service YAML, deployment, database YAML, and API secret and database secrets. Then I updated the deployment YAML file for replicas that would be 0. Previously it was 2 replicas, and I wanted to apply the concept of cron jobs and as well as KEDA. So I made the replicas with respect to crons, which would be 0. So there would be 0 pods that would exist by default, and it would only be triggered to the desired pods with respect to the cron jobs I will prepare a few moments later. And it is same with respect to the deployment of the database. It is replica count 0. I saved this deployment YAML with 0 replicas of database and application deployment, and I applied the kubectl apply -f with all these YAML files. And as you can observe by kubectl get pods, there is no pods that is running, meaning our apply command really worked with 0 replicas. So by default, we can observe that there is no pods that are running. Now to perform KEDA as well as cron jobs, next is to install and add repositories for KEDA, and for queue or streaming of events, I am using NATS Jetstream, which would mimic the users entering or triggering the queue or the load. I'll explain that later, but let's first understand the repository I'm using first. Repository I'm adding, that is Helm repo add KEDA core, that is with the link KEDA core GitHub charts, and I performed Helm repo update, Helm install KEDA from KEDA core /KEDA. I created namespace with KEDA create namespace, and it was successfully deployed. Then I confirmed kubectl get pods with the namespace KEDA. We can observe that all pods related to KEDA are up and running, which is admission webhooks and KEDA operator. Then I added repository for installing NATS Jetstream. So I performed the command Helm repo add NATS with the link of the NATS GitHub with respect to Helm charts, and I updated the repository, and I created the namespace NATS system, and I installed it within the NAT system namespace, and I set the jetstream.enabled is equals to true, which means that jetstream is enabled. It was successfully deployed. I confirmed it with kubectl get pods within the namespace NAT system. We can observe that NATS 0, it is up and running, and NATS box is also running. After doing it, here's the important step. We need to install NATS CLI, that is NATS command line interface, which gives us access to certain commands which will work to create streams or load, which would mimic users entering my application and triggering the event-driven autoscaling. Simply, it doesn't operate on default CLI or the commands of what we usually use. We need certain commands with respect to NATs, so we need to install the command line interface of NATs registry. In order to perform that, I head back into the GitHub of NATS.io and I installed NATS 0.40 Windows AMD zip file. I already had tools folder in the local C directory. I created NATS CLI folder and I pasted nats.exe file, which I just downloaded from the GitHub, and I head back into the system properties and environment variables to add NATS CLI path of that exe into the environment variables so I can access this CLI. This is the prerequisite of accessing or using the NATS CLI. After it was successful, I want NodeSnap to create a cron job or a YAML file to trigger the pods or auto scaling. To do that, I created a new YAML file naming KEDA-cron.yaml inside the KEDA folder. Now by default, as we change the configuration, it is running on 0 pods for deployment of application as well as deployment of database. So by default, there is 0 deployment files. Now, as we have performed or installed KEDA, which supports scaled object and other components, which says that we can scale up from 0, not from a single pod. So as we have observed before, by default, we have changed the configuration into 0 pods. Now we are preparing a YAML file to trigger the desired replicas of our application with respect to the timings which we want to trigger at, which is the concept of event driven. Event is like the certain timings in which I want the pod or the replicas to be present on the desired replicas. To perform that, I created this YAML file. We can observe this YAML file. It says API version keda.sh/v1alpha1, which means it is operating on KEDA. The kind is scaled object. Metadata is name, resume matcher, cron. Specification, it is targeting towards my application deployment resume matcher GHCR. It would change with respect to your deployment file name. As of now, my deployment name is resume matcher GHCR, so I named it. Minimum replica count is 0, maximum is 3. Trigger type is cron job, meaning it should trigger with respect to the timings of the event. Certain time is triggered, then the event driven auto scaling will scale the pods. So the metadata is time zone Asia, Kolkata, which is in Indian time zone IST. Start, which is 00 ***, which means 12 AM IST until 12 of the noon, which means 12 hours of the time frame. In this time frame, if this event is triggered, the desired replicas would go from 0 to 1. So that was the resume matcher GHCR, which is application deployment file. The same is for database. I added the same API version, kind, metadata name is changed to dbcron, which is with respect to database. Specification, target is with the name db. So in the deployment YAML file of database, it has the name db. Minimum replica count is 0, maximum is 1, trigger type is cron, same, time zone is also same, 12 AM to 12 noon, desired replicas is also same, 1, which means I want the event to trigger replicas of 1 when the time is from 12 AM to 12 noon. Then I confirm the pods. By default, it is no resources, meaning no pods are running in the default namespace. Then I perform the command kubectl apply -f, this new YAML, that is KEDA-cron.yaml, and we can observe the result that says scaled object.k.sh/resume matcher cron created, and same db cron is also created. I confirm the pods. We can observe that db pod is up and running and resume matcher deployment pod is also running, which means our cron scaled object KEDA is working, meaning we successfully managed to perform Kubernetes event-driven auto-scaling with respect to cron, that is time-driven. Certain time zone or certain time frame is provided in the YAML file. Within that time frame, if the event is triggered, the desired pod will be present. That was about cron. Now let's try or perform the stream or queue or load related auto-scaling, which is event driven. But first, let's delete this scaled object and cron jobs. So we are starting it as fresh for NAT jetstream concept. So to do that, I performed kubectl delete scale object, resume matcher cron and db cron. So scaled object is deleted, meaning resume matcher cron and db cron is deleted from the default namespace. And I scaled the deployment db to replica 0, and same for resume matcher GHCR replica 0, which means it is now down to 0 pods. I confirmed it with kubectl get pods. You can observe that no pods are running. So let's now perform or do the NAT jetstream. In order to do that, I head back into the KEDA folder and I updated the deployment YAML files again. Now by default I don't want it to be 0 replicas. I want it to be at least 1 replicas to be present. I will explain why in the later part. So I changed the YAML files with the replicas 1 for database and for deployment of resume match or GHCR application. Both have 1 replicas present. Previously it was 0 replicas, now it is 1 replicas by default. I'll explain the reason later part of this video. Then you will understand why I made it from 0 to 1. Then in order to save some time, I created this shell script to apply the default or YAML files that are not related to KEDA concept or any other thing. So this is a default configuration YAML files which I mentioned earlier in this video. So I pasted all these commands, all this apply of configuration YAML files, that is default configuration files of my application. That includes deployment of application, database, secrets and service configuration map YAML files. Then I performed chmod-x to give execution permissions to this shell script which I named without keda.sh. Then I executed this shell script, which means now the pods would be running with 1 replicas, not 0. I confirmed with kubectl get pods. Now you can see it is up and running with 1 pods each. Previously when we performed the same command, it was 0 pods. Then it's time to create the YAML file for jetstream. API version is app/v1, kind is stateful set, metadata is named nats, namespace is nats system, specification, service name is nats, replicas 1, match label with nats name, containers name nats, client container port is 4222, cluster port is 6222, monitor container port is 8222, and there exist volumes, ConfigMap. Added the configuration map with respect to NAT jetstream, which says it to listen at the ports 4222 and 8222. Memory storage would be maximum 1 GB. Now for exposing the monitoring port, this is the service YAML which is inside this same YAML file. Now it's service configuration with respect to opening or exposing the cluster IP of monitoring port. It's in the namespace NAT system, name NATs, and the client port is 4222, cluster port is 6222, and monitoring port is 82222. And this is the configuration for service headless stateful DNS. And here's the important concept, that is scaled object for KEDA jetstream. I added the API version keda.sh v1 alpha 1. Kind is scaled object. Metadata is named resume parser jetstream. Namespace is default. Specification, it targets the application deployment file resume.GHCR. Minimum replicas is 1. As I mentioned, I am now aiming for minimum replicas, that is 1, not 0. Maximum replicas can be 15. Cooldown period is 10 seconds. Polling interval is 10 seconds. And this is the fallback and auto scaling configuration. Then important part is triggers. The type is NAT jetstream. Metadata is lax threshold, that is $streams is resumes. Consumer is resume parser. Account is $G. And the host namespace monitoring path is nats headless dot nats system dot svc dot cluster dot local with the port 8222. So this is the configuration file that includes stateful set of memory only jetstream configuration map with jetstream enabled memory store, cluster IP service exposing monitoring port configuration, headless service for stateful DNS configuration, and file and the most important scaled object with explicit connection and safety fallback and rapid scale down configuration. You can do the configuration with respect to the official documentation of KEDA, but this is with respect to my application. It totally depends on how your application works. After successfully creating this YAML file, I created another shell script which is kubectl apply of this YAML file -f keda.jetstream.yaml and kubectl get svc-n namespace NAT system to name the services within the namespace NAT system, and kubectl get scaled object resume parser jetstream, and this command is to see the status of scaled object resume parser jetstream. And final command is kubectl port forward, that is pod/nats-0 within the namespace nat system within the ports 4223 map to 4222 and 8222 map to 8222. So this kubectl port forward is port forward both monitoring and NAT server. Then I gave permission by performing chmod-x with this new shell script KEDA jetstream.sh, and I ran this shell script. This shell script is for applying the YAML file of jetstream, which is event driven with respect to the triggers and the queue load of users, or triggering not just CPU or memory, just the queue and load. Then kubectl get service to name the services within the NAT system to see the ports and everything, and get scale object to see the update of resume parser jetstream scaled object, and port forward to port forward the client and monitoring of NAT's jetstream. Then it was successful. As you can observe, stateful set.apps which is configured, ConfigMap is also configured, service nats is also configured, service nat headless is also configured, scaled object resume parser jetstream is also configured. We can observe the desired services, that is NATs and NATs headless, which is both ClusterIP. We can observe the ports, that is desired 4222 and 6222 and 8222. Get scaled object. We can observe that resume parser jetstream is also available. We can see the status, that is ready, true, active, that is true, triggers is with respect to NATs jetstream, and finally port forward, which is 4222 and 8222. As of now, we are done with almost everything. Now it's just time to trigger the events to see if it is working or not. But first, let's observe the default status of pods and pod autoscaling. I performed kubectl get horizontal pod autoscaling, that is HPA. We can observe that KEDA HPA resume parser jetstream is created. Targets is unknown/5 average, meaning it is not triggered right now. Minimum pods can be 1, maximum can be 15. Replicas is currently 0, meaning nothing is triggered as of now. Then you can observe the kubectl get pods. As I mentioned, it is replicas 1 for both resume matches deployment and database deployment. Then you can observe the services, resume matches service and Kubernetes and DB service. So I performed the port forward for the deployment, resume matches GHCR to access the application. It was successful. We can observe that in the logs, Google API key is loaded, environment variables is also loaded. It is running on the port 3000. I head back into this port and I uploaded the resume. Results were available. You can see in the logs as well. So now you understood the purpose of adding at least one pod. Meaning if I would have made it default 0 pods, I wouldn't be able to perform the port forward the desired time, because the trigger for this KEDA jetstream is with respect to the queue and load, and my aim with respect to the load was to mimic the users entering quickly and users leaving. So it was not like every user is staying in the application. If it was that, I would have kept it many pods, but I wanted to make it like the load is quite high in a small moment of time and it is low in just few moments, and it is like pods are scaling and pods are scaling down with respect to those load and queue happening. So if it is that configuration, I wouldn't have time to perform the port forward to see if my application is even working with those configurations. In order to debug this configuration or to see if it is working or not, I would at least need 1 replicas of each pod to at least access my application and see if it is working. As I observed that the application is working, now I can update it. And after I observed that the pods are up and running, I changed it back to 0 replicas for resume matcher GHCR, meaning resume matcher GHCR is now same as 0 after I checked the port forward and working of my application. It was just limited to seeing and working of my application. After this comes the most important concept of applying the jetstream. Now you would understand the importance of installing the CLI, which we just did, because NATs commands are not limited to the usual Linux or other commands. It has certain NATs specific commands which needs to be mentioned to trigger and create events for our application. To create a scenario where we are opting for streams or to see when many users enter your application and it triggering the events for auto scaling, we must first create the NAT stream with the desired username or the name which you want. I gave it the name resumes and consumer name, that is resume parser, and the message or the trigger. So for triggering those commands, it was a manual process. In order to not make it manual, I created a shell script. It would just be a shell script I would be running, and it would be prompting me to enter details within the script while it is running, and I provide the details and the stream would be performed and completed. So first command is to create NAT stream. So the command for it is nats stream add resumes. You don't add this command into the git bash. Even if you want to do it manually, you would need to use this command in the command prompt of your Windows if you are opting for manual. If you are opting for the shell script method, you can try the same script. I'm pretty sure it would work in yours as well. You can change the environment variables and variables which is related to my application and it would work. Simply the same command is nat stream add resumes and it will prompt into subjects. Then it is automatically entering resumes dot star, and storage, it is memory, retention is limits, max messages is -1, max byte, which means limited, max bytes is unlimited, max age is also not limited, max message size, discard old, dupe window 2 minutes, server is nat server, which is the environment variable which we mentioned in the YAML files. Then it is a fallback of if it doesn't respond in the 2 minutes of the time frame, then it would echo the command error step 1 failed, could not create resumes. Then if it is successful, it is this echo statement. Then it is nats consumer add resumes resume parser. Then we are adding the consumer, that is resume parser, which we specified in the YAML files. We specified resumes and we have also specified resume parser in the YAML files. So it is limited to my application and the configuration files. It depends on what you prepare for your own application, but the format and the template is similar. You can also try to create your own as well. But these are the specific commands. Looks complicated while you observe, but it is simply 3 to 4 commands. First is nat stream add resumes. Second is nat consumer add to add consumer to add stream. Then third is to trigger the response or add the messages, so it acts as a stream or queue, which means publishing the 10 text messages or 10 messages. Simply 10 triggers to mimic 10 stream or 10 users entering your application at the same time. This is the fallback statements. The main command is nats pub nats pub resumes dot text. It is code hello message. Server is nat server. If it doesn't perform this command, then it is a fallback statement. Then it is successful. Then it shows message published successfully. Till now it is great. Like we have added a stream, we have added the consumer, we have triggered the messages too. But by default the queue was not leaving, meaning the queue was acting as if it was a permanent user that was accessing the application. If it triggered 10 messages or 10 users, it was acting as if 10 users were permanently present in the application, which is not what I wanted. So in order to make it event driven, like users entering the application and just leaving it, to make it realistic to the auto scaling of event driven, I added another command which is in the step 5, which is to purge or delete the existing queue. It is not like the users are entering the queue and leaving. So I added this nat stream purge resumes. Server is nat server, meaning it would trigger the users and it would wait for some time, which is mentioned here, sleep 0.2, which means it waits for 25 to 30 seconds. Then it creates a purge, which means it deletes those queue which we just created, meaning it creates the consumer, it creates the stream, it triggers 10 messages or 10 users accessing your application, 10 streams accessing your application at one time. Then after some time, 10 to 25 seconds, mimicking those 10 users are accessing application for 20 seconds. Then it creates an event to purge those users in the queue. So it would be like users entered for 20 seconds and they just left, and performs events or auto scaling with respect to this scenario. I hope you get the point. After saving that shell script, I gave permission for execution, that is chmod-x with KEDA stream run.sh with this script of running the application, with creating the ran this script to create stream, create consumer, add the stream or the queue, delete or purge the queue or streams. After I performed it, it looks like this. We can observe that it says life cycle of the test is successfully finished. We can observe that it published 15 bytes to the resume.test. And it also says 10 test messages, meaning 10 streams or 10 load is triggered, which is an event in itself. Then we can observe the step 4, which says it is holding the queue, holding those 10 test messages or 10 queue for 25 seconds, which would give us the time to observe that the pods are creating. Then after 25 seconds, it is automatically deleting or purging NAT stream or this queue, mimic that the users just entered the application and just left. So it is completely like event driven and cost effective strategy. Then it says purged 18 messages from resumes, meaning it was successful, and we can observe the state as well. Messages is 0 and we can see the stream wiped successfully. We can watch the status of the pod to see how it works. So that was the backend part of how the script worked. We can observe the real-time situation of how it happened. For running the script, I already had these commands in separate terminals, so I could see how it was working. So I had performed this command kubectl get hpa-w, which is like watch. So by default, KEDA hpa resume parser jetstream, which is referencing to the deployment of resume GHCR, was default, which we already observed. It is 0 replicas, unknown pi average, but after some time the event was triggered with those messages and wait for 25 seconds. So it went from unknown to 10 out of 5 average, meaning it triggered 1 replicas. Then it also triggered 5 out of 5 average targets, meaning it also triggered another replicas. So it went from 0 to 2 replicas. Then after 25 seconds, it was purge and delete of those existing test queue or the messages, whatever stream. So it went from 0, 1, 2 replicas to back to 0 replicas after those queue was purged or deleted. That was about HPA status or kubectl get HPA watch. We can observe the real time of the pods, what happened to them. I performed this same command before running the script. That was kubectl get pods -w. DB was already at 1 replicas. I only changed resume GHCR to 0 replicas, so it was by default 0. So we can observe that it triggered pending init pod initializing and triggered 2 pods that are running, and after 25 seconds it is terminating those pods. And after some time I performed kubectl get pods and it was only DB pod that was running, not resume GHCR, meaning it went from 0 pods to 2 replicas of those pods and back into 0 pods. That was the life cycle of stream or users entering the application for some time and just leaving, and it triggering the event driven auto scaling and auto scale down. And when I encountered errors and I was debugging, I had to perform certain commands to delete scaled object, stateful set, pods and deployments. So it was 3 to 4 commands that I was constantly performing. To save some time, I created another script to refresh the jetstream information and perform the commands. I created this another shell script which was kubectl delete scale object, resume parser jetstream, kubectl delete stateful set nats names within the namespace nats system, kubectl delete pod nats -0 within the namespace nat system, which is force grace period is 0, and kubectl scale deployment resume GHCR replicas 0, meaning this script is to refresh the KEDA jetstream results. If the results were not as what I supposed would happen, then I would perform this command so it was fresh, and then I performed the commands again and the scripts again to see the application until it worked. So that was about the concept of KEDA, that is Kubernetes event driven autoscaling. I have explained you theoretically how it works, what is the purpose of it, and we also observed how I created and managed Kubernetes event driven autoscaling. First we have observed cron, which was within the certain time frame and time range when replicas would be scaled, and we observed the nats jetstream to mimic the stream's load of users entering and leaving the application, and events that would trigger the pods creation, pods autoscaling, and pods autoscale down with respect to those events. So that is it for the video today. I hope it was simple and insightful. Thanks so much for watching. Have a great day. Bye.